Morning, Ellen.
Oh, you can unplug it too. I'll let you unplug it. Yes, I am here. We should be studying for 122 though. I don't know if you can. So we have the 122 midterm on Monday.
He's already, he's out, yeah.
Hello. Hello. I left. Oh, you did. But I could hear things and I could see things. How's the camera? It was kind of tough. You'll probably need to zoom in because it is a little grainy. So just if you zoom in generally, I guess the screens of the slides are being shared, so like it's not a big deal.
Yeah. Oh, I didn't see you.
Oh, it's supposed to be 30.
Just sign.
Oh, you're clearly not ready. I don't see the clock. Why not? That's it.
Yeah. Some calculations.
But like, the comment yesterday.
Yeah, so you'll stuff. Would it just be easier?
So then.
I'm just worried about.
I even know that entire version sensors before.
These guys.
So,
I guess
You look into that.
Yeah.
Yeah.
I know.
So why were you gonna turn this?
Yeah.
So.
But that's-
What did we have done last year? So anyway, that's a little.
They knocked us out.
So he goes down there on there, so that.
Okay. Thank you so much.
Okay, sure, it's just.
June 27th week. Oh, 70, sorry.
Oh, no, it's just people on.
Like you use like short lap. Oh, no, are we on those ones?
Give me game change.
That's
Oh, he's here.
That's right there.
Walking.
Where do you get going?
Basically. What's came through and just getting out. I don't know. You're gonna do a lot of electronics things. Can't pass. So if there's something that we could peel away a couple. Don't have anything to do with that. Chassis,
Okay.
different things like that. I don't know, so I'm gonna spend time with like you.
Yeah,
Curtis,
yeah.
But I need to test tomorrow.
Yeah.
I can go over some of this.
Sure.
stuff. So
There's definitely no. Arrow will be here still. I think I could even use it. That is great. I'll have to write my microphone.
So.
Yeah.
There's some minor things going on, but just like change direction.
Yeah.
Just like they're expensive.
Mhm.
But easy.
Thank you.
Yeah.
All right, not taking too much time. I think we're gonna let Arrow get started. Thank you everyone for coming again to CDR. We have a couple of people, but I expect people to kind of come in as time goes on. So I really appreciate everyone coming. Yeah, so we're gonna hit off with aerodynamics and then we'll dive into the particular section. I wasn't able to make the agenda yesterday, but we'll follow the same order as it is there. And I'll probably make an updated one in the meantime. So thank you guys. Let's have the arrow go up.
Good morning, everyone. My name is Kelvin, and I'm one of the Aero team leads. Okay, so I guess I'm gonna try and keep everything brief and efficient just because we want to get through everything real quick. So this is our aerodynamics agenda. We'll be going over our sub-team, comparisons between GR25 and GR26, our components, simulations for our components, mounting, manufacturing, as well as our validation and testing plans. So yeah. And in terms of our aerodynamics, we're responsible for building the car's rear wing, side pods, side diffusers, nose cone, body panels, and front wing. And our objectives for Gaucho Racing is to improve mechanical grip with downforce, as well as increase the cooling to the radiators, and achieve a center of pressure in accordance with vehicle dynamics.
So to go over some of the rules that restrict us and what it is we can do, the main ones are the ones that define the aerodynamic bounding boxes that we are allowed to operate within. There's a nice little diagram in the top right corner showing what that looks like visually, as well as kind of what we see in the rule book. I did omit most of the text because it's very long, but for the most part, this is the bounding box that we're working within. And we are pretty generally maxing out a lot of the space that is available to us. The other rule applies to mounting, and that is that the aerodynamic devices do not oscillate rapidly while the car is moving. If we are driving endurance and they see that our car is like flapping around, they will black flag us. Or I think there's a black and orange flag that they might wave to check our car in the middle. So it's really important that we stay within this step. So this is an overview of what some of the feedback we got last year was, as well as what worked and what didn't. We did end up passing the aerodynamic portion of technical inspection, which was great. That was really good. We also had very strong mounting. We were able to have multiple members stand on the car at once. We could even have two people standing on the front wing at the same time. Our manufacturing process, from what I hear, was a lot better than it was in previous years. We got things done quicker. We didn't have to remake as many components, and it was overall, we had higher quality components that we made. Some of the specific positive design feedback that we got is we had a very highly efficient aero package, meaning we generated very little lift for the, very little drag for the amount of lift that we generated. And then our car was also not particularly sensitive to state changes. So pitching, rolling, yawing, we still generated, you know, an adequate amount of, or we generated within kind of reason of what our, what amount of downforce we would generate if we were just going in a straight line, which is good. There was a lot of room for improvement though. We only scored 6 out of 15 of the total points available for the aerodynamic portion. We were extremely overweight last year, coming in at 53 pounds. We were unable to validate any of our data that we had or any of our CFD with real life data. Our wing structure was overbuilt. It, in the design feedback, it's described as being like a belt and suspenders, where we have both a core to our airfoils as well as ribs and other mounting stuff. That kind of was unnecessary and overcomplicated. We also did not have the cooling system installed on the car last year. And then for the actual things they had to say about our aerodynamic performance is that we did not have enough overall downforce to justify the package. We had an issue with the diffuser where it looked like we had a very steep outlet angle on the diffuser, and the judge had told us that most likely that would have seen flow separation. And then excessive rear wing pressure. Just means that we had a lot of downforce on our rear compared to our front, and our aero balance was kind of poor because of that.
Was your diffuser outlet angle? That wasn't in your CFD, right? It wasn't showing flow separation.
It was not showing flow
So it was
separation.
just the judge looking at it saying
Yeah.
that seems extreme. Okay.
But our CFD is very optimistic, so we have a feeling that if we had actually ran it, we definitely would have seen flow separation just from all the turbulence and stuff that's going on.
We've done the same thing. We had diffuser flow separation that didn't show.
Kind of our overall goals for this year that what's going to drive us is we want to reduce the amount of understeer and move the center of pressure forward. We want to simplify mounting because mounting did end up taking kind of a long time to take on and put on and take off last year at comp. We need to develop a method for aero validation. We need to reduce the weight of the overall package, and we need to actually increase cooling to the car. I do have some hard package targets that we came up with. We want to achieve about 600 newtons of downforce while generating less than 190 newtons of drag. We want to achieve a total package mass of under 30 pounds. We want to be able to remove our nose cone without taking off the suspension. And we want to be able to improve the flow to the radiators by 50%. And that is measured in mass flow.
So how did you come up with, I think, 3 numbers there, the 600 newtons, the less than 190, and the 50% increase to the radiator?
So for the 600 newtons of downforce, that was, we looked at year-over-year improvements from GR23, 24, and 25. And it was a pretty linear increase of about 180 newtons a year. And because we were going to go with a more complex package, and last year we had decided intentionally that we weren't going to go with a particularly complex package, that there was still significant room for improvement. So this seemed like something that was achievable and that would give us a good solid number to work towards without kind of being just, oh, let's go for as much downforce as we can get.
What speed is that?
This is all at 35 miles an hour. Thank you. I should have definitely clarified that.
Always have those together.
Yeah. I guess for reference, pretty much every value that we show you will be taken at 35 miles an hour. I do mention it in the CFD part of this presentation. However, it essentially, when they design these endurance tracks, they're all designed to be taken at an average of 15.6 meters a second or 35 miles an hour. So all of our simulations are at that speed. As for the drag number, We were told that we could generate significantly more drag than we had last year. We had a very low drag package, and they had mentioned that the design judge had mentioned that our powertrain was more than capable of outputting enough power to overcome it. But the 190 Newton was just kind of, you know, something to give us to stay underneath so we didn't start like running away with it. And it's about a 25 Newton increase over last year at the same speed. I think we were at 165, I think. Okay. And then the total mass, we worked with suspension and vehicle dynamics to kind of cut down on that. We looked at what our individual component weights were last year, and we decided what was reasonable based off of, you know, manufacturing, where can things be improved. So we came up with a target of 25 pounds, which is half the mass, which is kind of ambitious. And then we decided to go with side pods as well. So we factored side pod mass into that weight, and we assumed that we could probably get side pods for about 5 to 6 pounds. Without the weight, not including radiators.
The other one I cared about, the ones I'm caring about are the ones where I think there's an impact on other teams. And so far, I'm liking your answers. How about the radiators?
So for the radiators, that is very much kind of just, we have no idea. We've never done side pods before. We've never even really done like CFD on radiators. So we have no kind of prior knowledge. So this was just a number that I came up with as something, how could we justify the existence of side pods and justify that added mass? Well, if we can increase our cooling by 50%. So there's not a whole lot of kind of thinking behind that number because there's just no one on the team really knows how to.
So who does thermal on the team?
So for the actual cooling, that would be over there.
So how did cooling look in the past?
Well, we really got to try it for the first time last year, but we're gonna have one loop that had a radiator with it for the motors and inverters, and then one last year that didn't have a radiator. This year, I think because of the side pod, we were looking into trying to add the radiators to both of the loops because it does make a significant difference with the mass flow rate. Yeah, I mean, are you looking for specific values or?
Well, what I'm looking for is where do we stand on temperatures, allowables? How much margin do we have? We even need. And what does it allow us to do? Does it allow us to save mass someplace else? Does it allow us to run hotter because we can dissipate more heat?
Yeah, so it allows us to run hotter because we can dissipate more heat because the flow rate out of the radiators is going to be higher. The power that's coming out of the radiators, it keeps flowing out of the radiators faster because we have an improved heat transfer coefficient.
So is that going to keep the batteries cooler?
Keeps the batteries and the motors, or batteries, motor, and inverter. It keeps them all cooler for longer. And we'll get more into that in 2 hours.
Because you'd like to see all of that tied together with some numbers.
Yes.
So that your 50% is not just out of the air, it's tied to, it does something for the system. It probably does. Sounds like a good thing, but definitely needs to get some numbers tying the teams together.
Yeah. I guess kind of a little more background for that number is we were told that the current, like the cooling systems that we were developing weren't going to be able to get the car through endurance without throttling the batteries significantly. So I was like, or I had talked to the people who were responsible for cooling. And I was like, okay, I'll see if we can get, you know, side pods to improve the cooling. And that's when we talked about numbers a little bit and I had brought up 50%. I said, do you think that we could get through endurance without throttling the batteries if we do 50%? And we all seem to think that that was a good number that we could shoot for.
Okay, good. I like how you're thinking. That story is not just pulling it out of the air as much as we've got positive feedback that we wouldn't make it through endurance. We're going to overheat. We need to do something. This is our current engineering rough idea of what might be good enough. Okay, that's valuable. That's engineering. That's not just throwing a dart at the board and seeing what number pops up. So thank you.
So currently on our package, this is what we look like compared to last year. We have a coefficient of lift times area of negative 3.43, which is about 17% higher. We are producing about 5.5% more drag, but we did improve our efficiency even further by 10 or by 11% just because we were able to produce significantly more downforce for not very much increase in drag. we only added 9 newtons of drag for our additional 76 newtons of downforce. So we actually did really well in still maintaining a high package efficiency. Any questions? So moving on into the components themselves, front wing is probably the area of biggest.
Actually, can I stop you for a second? Do you have any sort of drag lift to lap time correlation?
At this point, we do not have any aero maps or anything like that. That would be something that is gonna be worked on in probably the coming weeks.
Okay,
But yeah, we're definitely behind schedule this year for aero, so.
Right.
For the front wing, one of the biggest change that we're making to this year is the addition of a third element on the inboard part of the wing, between the tires. This is going to allow us to produce a lot more downforce, but it comes with a few significant drawbacks. So while it will help us achieve our goal of moving the center of pressure forward, it will generate significantly more drag, and then there's also a factor of increased wash that gets sent up into the rear wing that we will have to manage. So you can see that we are producing 167 newtons of downforce at 35 miles an hour, which is about, I think, 40 newtons higher than last year on this component specifically, which does serve to help us achieve our goal. And then some of the other considerations that we made this year is that we have in the past had our front wing scrape the ground a little bit when we were moving it out at top. And we decided that if we were ever to run the car, it was definitely going to bottom out. So we need to spend a lot more time, trying to figure out what our max pitch and roll are and what our ground clearance is. So we did work with vehicle dynamics and with suspension. And we gave them kind of estimates for what it is in ground effects that we were going to need in terms of distance off the ground. And they talked to us about what it is that their max pitch and roll is. And we decided that this current package that we have should be able to clear the ground even in the most extreme conditions.
I think, sorry,
Yes.
Forrest, right?
Yeah.
I think you can probably calculate your drag limit instead of saying judge even at some point. At some point, your car's gonna be drag limited versus power. If you're look at your max speed and your power output, you can say, hey, look, I've got more than enough power, that drag isn't a major factor. And that'd be a good parameter you guys can calculate. And that's I know I've talked to judges and they hate it when I say, well, somebody told me, without some kind of a backup, so you can have a story about that calculation.
Okay. Thank you for that. For some of the major changes that we will be needing to make still in the future, is the addition of a positive lift winglet that will be directly above the trailing edge, kind of and slightly back on the third element, and that will serve to help keep the wash out of the rear wing, which is something that we are seeing in CFD, is that we're having air get sent up from the front wing. It's traveling past the open cockpit where that air is stagnant and not moving. And then the interaction there creates a lot of turbulence, which continues up into the rear wing, which loses us performance. Additionally, we will be working on end plates and trying to adjust them to push air off to the sides to block tire weight, or I guess block air from hitting the tires and creating weight, as well as kind of a final element tuning to achieve a better aero balance. That aero balance is still yet to be fully determined, but we're leaving ourselves options for being able to kind of hone that in towards the end through just altering our elements. Moving on to rear wing, there's not many changes to this from last year. It's pretty much the same amount of elements, similar size. We are changing the geometry of it and the specific elements that we're using. But the reason for that is due to the driver position this year, the head and headrest are planted directly in front of the leading edge of the main element. So when we use something like last year's rear wing, we were actually seeing massive performance losses because the driver's head was in the way. And that flow separation from the turbulence would just propagate throughout the entire wing. So we had to alter our rear wing geometry to be more resistant to flow separation. So this current geometry that we have manages that a lot better. It doesn't produce as much overall downforce on its own, but within the context of the car, we're producing more downforce than we would. The other thing is that we need to focus on mass production for this a lot. This was the most overweight component last year on Aero. It had lots of metal, lots of 3D prints. We'll get more into manufacturing later, but that is going to be a primary concern with the rear wing is how light can we make it, especially since it's very high and very far away from the center of mass. So every effect that it has is, multiplied. Changes that we still need to make to this is the addition of a manual drag reduction system. So all this is it's really simple. In the end plates, we'll put these kind of metal plates that we can then select a different kind of angle of attack with on the rear wing and have it be fully open for things like the acceleration test, where we don't want to be producing any downforce, and we just want as little drag as possible. Additionally, more end plate add-ons and other stuff to try and get rid of the large vortices that we're seeing off of this. For side diffusers, this is the most complex component on the car right now, or for Aero at least, not in terms of the whole car. So immediately we have a less aggressive outlet angle. Even though we weren't seeing flow separation in our sims, we still went and turned down the outlet angle. And then we're doing a more complex geometry. So instead of just having a straight diffuser tunnel, we have it kind of expand out in the middle to provide more area for the air to move into. And then also the actual underbody of the car will have a flat panel underneath it that can be quickly removed for accessing anything that needs to be there. But the addition of that flat panel will improve our downforce and kind of help clean up air under the car. So those are the major changes to our side diffusers. Things we still need to do is for the tire wake deflector, we would like to have actual airfoils in front of that to kind of produce a little bit more downforce, produce less drag, but still achieve the overall goal of moving air around the tires instead of into them. And then also we were seeing some issues with the diffuser where it's too far back and it's catching tire wake off that front tire. So moving the inlet up or further up towards the A-arms would help hopefully mitigate that and give it cleaner air off the front wing. For the actual kind of vanes on the wing right here, not the wing, but the diffuser, those we tested with and without, and there was no difference for this setup in terms of that. So in the CAD, we do have them as being there, but they should not be there on the current model and not on our current sim models. We just did not have another render to use. But overall, the geometry is identical to this. It just doesn't have the veins.
So you mentioned that you changed the angle of the exit. What did you change it to?
It's based off of an airfoil profile, so I don't know exactly what we do right now. I couldn't tell you the airfoil profile off the top of my head.
I wouldn't know it if you did.
But whatever profile it is, it was meant to be. I believe it's about 2 to 3 degrees, just based off of guessing by looking at it.
Oval,
Well,
with respect to the ground, or?
with just that, it's 2 degrees less.
Okay.
Something around there. As for the body work, we're mostly focusing on how we're actually going to manufacture this year. It took a very long time last year. It took over a month just for the nose cone itself. So instead of trying to have a more only do 3 layups, we're kind of splitting it up into even more flat panels to hopefully simplify mounting as well as manufacturing. Other than that, really, we just have a more rounded nose cone head to hopefully more smoothly direct air. We did see a little bit of kind of weird artifacts on last year's because of it was more flat faces for the tip. Other than that.
Please don't take this personally, but in a design review, I really don't like hearing hopefully.
Okay.
Heard it a few times yesterday. Engineering is not about hope. Right? So you've made changes to make this easier to appreciate, yes or no? Not hopefully.
Okay.
Okay? There's just nothing in engineering that's about hope. That's for everybody. So like I said, don't take it personally, just.
Thank you for catching me on that. Other than that, there's nothing to really talk about for the nose cone and body work. it's mostly the same as last year. Still needing to be done on this, if you guys noticed, our nose cone interferes with where decoupled would be. This is something that we expected and have been working with them on. But because there needs to be a closeout for the actual, nose cone by rules, you can't have any holes into the cockpit opening. We will need to have an additional kind of structure that goes underneath where the decoupled mounts to the car. If we are cutting a hole in the nose, which we will need to. Also, we will be cutting out a section of the nose cone for suspension to mount through. So then you can remove besides that small panel that the suspension mounts through, the rest of the nose cone can be taken off and it won't interfere with suspension. Yes, and then there will be a sensor, there will be a camera in the nose cone from electronics. And we will need to work around that for our actual kind of shape of this. For side pods, this is the brand new component we were talking about. The design is, very simple. We had some more complex designs early on, but we decided to kind of scale back and go to a much more simpler, just have a larger inlet than your radiator face, at the most basic principle. And what this does is it increases the amount of air that we can catch into the side pod and increase the mass through the radiator. And then there's a smaller outlet, so the air gets accelerated as it leaves. And there's less kind of wash from the radiator. We see cleaner air, less drag. Radiator cooling, we get more mass flow rate through the radiator, so that will improve the cooling efficiency. And some changes to do is, hone in our final design and optimize it, especially since we're learning right now kind of what it is that works and what doesn't work. So by using kind of what we've seen so far, we can create better and better designs. And then finally, design for manufacturability. This was something that we had just come up with, but now we're going to focus on how are we actually going to manufacture this? What steps are we going to take and what's possible and what isn't? For actual numbers from this though, we did increase the mass flow rate by about 46% in our preliminary sims. So we're very, very close to that target. And because this was our first time actually simulating this, there are some very simple fixes that don't even involve changing the geometry, just changing the way we sim. So those improvements could potentially bring us up to over 50% very easily. And then some other improvements that do involve changing stuff is we are seeing air that flows around the radiator in CFD because there's gaps. So just something to seal that up would still increase even further the amount of flow rate through the radiator. Any questions?
So by the way, I don't like questions charts because I like to be looking at data when I'm thinking and talking. I really like how you're approaching the problems and how you're thinking. But what I worry about is basic interferences, both static and dynamic, and how well all of this is going to fit. Yeah, I mean, you were in the room yesterday during the conversations about how this chassis is going to come together and what kind of tolerances we've got and how much of it's going to be sort of build to print or build on the shop floor and have to adjust. It's not clear to me how all of your custom components are going to integrate with all the uncertainty around the rest of the mechanical structure of the vehicle. So, and I don't think you could convince me with any amount of presentation at this point that it's all going to come together any more than I think most of us didn't leave convinced that we knew how this chassis was going to go together and whether the jigs were going to be able to be accurate enough to tie everything together. So what I would suggest is a program plan on how you're prototyping early and building early and figuring out how to adjust early after the chassis and some other pieces have been put together. So what I fear is you're going to have some beautiful components that just don't fit this vehicle.
So for that, there are a few considerations that we do have because we know that chassis isn't perfect. We undersize all of our components in the bounding box by a few millimeters, like maybe 15, 20. Depending on what bounding boxes we're running into, sometimes it's bigger, sometimes it's smaller. But that does allow us to have a little bit of play depending on, you know, how the chassis tubes are, where, if we can get our mounts put correctly. But that is a really good consideration to make, and that's something that we should probably be more aware of in the future, and especially right now. Because in the
You
past,
mentioned you were behind schedule, and that ends up being disconcerting because of what we're just talking about. The way to do that is build early, plan for a second build, maybe even a third build. But it's got to be in sync with what everybody else is building. It's complicated integration here. You've got to push yourselves to be getting product built early enough to do real world integration. You obviously aren't doing a prototype, but it's sort of too bad you can't. So that schedule, how you're going to integrate early and give yourself a chance to recover if it turns out some components don't have enough leeway.
so on that, at competition, actually, last year, we did not have enough clearance in one of our bounding boxes on the front wing. So yeah, we had to sand down the front wing and kind of bring it in. It was only a couple millimeters, thankfully, but that is something that we need to be more aware of.
Yeah, I mean, just assume it's going to happen on pretty much every component you've got. And figure out how you're going to learn early enough to adjust.
One of the things he said there is about the rads in the side pod and the area around the rads and how it fits in there. Foam tape is going to be your friend, but that has to be perfectly sealed. All the air has to go through the rad. There cannot be anything that goes around. It has to go through the rad, and that is going to be one of your priorities, because, as you well know, it's going to take the path of least resistance, and you will lose massive amounts of cooling just by a few millimeter around the rad. That's going to be massive. So everything is going to have to be really well sealed. So know that that's like, you need to go into it knowing that like everything has to be perfectly sealed. If it's not, then a lot of what you're doing is academic, and it's not gonna translate to the racetrack. I like the fact that you're up to 100% improving in cooling. I'm assuming you're talking about 100% improvement in cooling from prior. Is that, or 100% improvement in what?
I should have specified, from not having side pods at all, so assuming with just radiators in the air and then radiators.
Okay, so once you get a duct made, right? It doesn't really matter what it is, but get a duct made and do something simple to show the judges what you're talking about, right? So literally have some sort of bench set up where you are blowing, I don't care if it's a leaf blower, right? Blowing a leaf blower at an open rad and come up with some way to want to give a quantitative value on the heat rejection, right? Then put your duct on, and you know you'll have a pressure before and after the rad, so you can show, here's my flow through the rad, here's my heat rejection, and you know this doesn't have to be whatever you have that's making the water hot and whatever you have that's pumping it. It doesn't have to be tricky. It can be something pretty simple. But if you can show, okay, now we have X amount of heat rejection, we put this ducting on and we have Y amount of heat rejection. That's going to be exactly what the judges are looking for. And it doesn't matter that it's not on the whole car. It gives a value. The CFD stuff, I'm going to take that with a grain of salt, maybe less. So anything that you can do that shows a practical quantitative value on anything. And in terms of, you know, do the same thing with your front wing, like put it on some sort of scale. I don't care if it's bathroom scales, and shoot a leaf blower at it. And here's the values that we make. You know, anything that is practical and shows the judges that you're not just looking at a computer screen, you're actually trying to do something, which is, here it is. It pushes the car down. Those type of things, you know, everybody, you'd love to go to a rolling road tunnel and give them some great numbers, right? But obviously that's not gonna happen. So you'd be surprised if you take a leaf blower and blow it towards the front wing, be damned if the thing doesn't go down, right?
Yeah.
So you can do that type of stuff and it doesn't have to be tricky. It can be super practical and you know, just a dirty thing like that is gonna impress the shit out of kids.
That's definitely in line with, you know, the goals of Aero this year, which is 100% validate what we've done.
Yep.
Because we've never done that, so.
There you go.
Then that is one of the main reasons why we only scored 6 out of 15 points.
Fair
because
enough.
We just had no validation. Thank you for the idea. I have it written down and I'll look into doing that.
I think you also need to look at, I mean, what Tim was saying, I think cooling is gonna be critical if you guys are running. In your endurance, you gotta decide how important it is downforce, right? In terms of like, what's gonna increase the performance for your car, and there's certain things you wanna focus on, so maybe sealing is number one, and that is gonna be something super important, and your diffuser layout. It's like, what, 2 feet long, I'm not sure how much downforce you're gonna go, so understand what's sensitive to the performance of the car, so when you're actually there, you focus on what's actually gonna improve. Because I know aero guys love your downforce, but in some ways cooling is probably getting more important when you're trying to do certain things too.
Yeah.
Cooling is gonna be more important to your primary goals.
And that's actually where that 100% comes from is like, if we were to alter the actual front wing geometry to be direct more air into the actual radiators and the side pods, we're confident that we would see more and more, a significant amount of increase, because as it stands right now, the front wing is channeling air up and around the radiators.
Yep.
So,
As they do.
yeah. Moving on, we do have some flow or path lines of velocity, again, all at 35 miles an hour. I don't know how much this means to people, but you can see that we are obviously having a lot more wake off the front wing, as well as a lot more turbulence around the side of the car, and that's stuff that we are kind of developing to manage. There's lots of different setups coming up for front wing to try and bring that down, add-ons.
Are your wheels spinning?
Yes.
Okay.
Here is probably the most useful visualization is this is the flow as the car moves towards us. You can see that there's a lot of air going into the diffuser opening right here of turbulent air. So overall, there is definitely room for improvement in actually how we manage our weight and where we generate it. But that's my favorite visualization for what happens with the car and what happens with the flow. Anyone have any questions about that?
Why do you have your, and have you have your biggest front wing, you have your multi-element on the inside as opposed to the outside?
That is bounding box regulated.
Okay.
So they don't want you blocking the airflow in front of the tires with the front wing.
Okay.
Anyone else?
Okay, so I'll be covering mounting for aero. Our front wing mounting last year was good. It was in fact too good. It was able to hold our drivetrain lead standing on it. So yeah, so that's why this front wing mounting this year will take a lot of inspiration from last year, but also be much lighter than last year's, because last year's was too good, but it was also too heavy. So I think we could cut down on the weight, but also have it still be good. So the front wing mount, as you can see here, will be mounted under the front chassis. We're going to reduce the bracket size as well as have it so that the nose cone can be removed with the front wing on. We're also gonna be sticking to single shear mounts to help reduce our manufacturing complexity and reduce the factor of safety. So as I mentioned earlier, to have lighter components while still meeting our structural requirements. So yeah. And then we have our rear wing mounting. Last year, it's gonna take a lot of inspiration from last year because last year's was also too good. Our current suspension lead, Curtis, was able to stand on the rear wing and have it be perfectly fine. So that's why we're gonna try and wait. Last year we used aluminum swan necks, but this year we're gonna switch to carbon fiber swan necks, and the core of it is going to be Nomex with a carbon fiber tie rod brace between the swan neck, as you can see in that image below. Yes.
Do you have some numbers for how stiff last year's brackets were and how much they actually were measured to be? How stiff or how less stiff you're gonna make these ones? Use something to compare to.
This would be something that we would create kind of like, we don't have any numbers on what last year's was. But for this would be something that we create kind of a model of, and we test it and we see, okay, is it strong enough for the actual purpose that we're gonna have? And if it's not, we'll abandon it, but.
But not okay, because.
Yeah.
Because, yeah, I mean, I was waiting, but since we're talking about it, too good, not good enough, will be good enough. Good, sort of like the word hope, right? Good doesn't tell me what the engineering is.
Yeah.
So I'd like to know what the factors of safety were last year. What were they calculated? If it turns out the calculations were way off and it ended up being a lot stronger than possible, I'm assuming when you tell me somebody's standing on it, I don't know what that means for factor of safety. But does that mean it was 2x what we calculated, 3x? Did we not even bother to calculate? I mean, so I'm looking for the engineering on what you're changing with numbers.
So by that, hang a known mass, whatever, 50 kilos from the edge of that or the other, measure the deflections. Right, that's what we're gonna be looking for. And when you tell me something's too stiff, no, it's not. No, it's not. The fact that a guy is standing on a wing or standing on a rear wing, that sounds just about right to me. Like, there's no such thing as too stiff.
All right, that makes a lot of sense. Thank you
But
guys.
there is something that's too heavy. I'll go with you on that, right? But there's too heavy, but there's not too stiff.
Yeah, just to reiterate, looking at these slides, I'd be a little concerned about how stiff all the mounting is gonna be. In GR23 and 24, it was not stiff at all. And obviously, that led to a lot of issues, so we over stiffened it last year specifically. I would recommend like, these brackets are something you can order from Senka10, or you can lay up these carbon fiber brackets. You can test the stiffness, see how stiff, come up with some actual targets, and then test it out, see how stiff it actually is, adjust it. This isn't like the most complex system, so it should be pretty easy for you guys to test and validate.
Yeah, that was the goal. We were working on that. So once we actually have,
Just one more thing, looking at it, I think those bolts would probably shear out first before those brackets yielded, in the front maybe at least. So just keep that in mind when you're signing.
all right, yeah, we'll take that into consideration. But yeah, as I was saying, that's something we're still working on. We're gonna do much more testing later on once we actually build these. So we're gonna be applying loads to it similar to how or what the rear wing and front wing would be applying to the to our mounts. So yeah, and of course there are 2 half-inch carbon fiber tie rods that would be attached to the rear, as you guys can see in that image. And next up, our side diffuser mounting. One thing last year was that our side diffuser mounting was too inadequate, as in that it wasn't able to hold up the side diffuser that well. So that's why this year we'll be switching to a half-inch carbon fiber tie rod that would be attached to a main hoop, and it'll be the main primary lateral support for our side diffuser. Last year we had cables which wasn't able to provide the lateral support that the side diffuser needed. So yeah, and in addition to that,
Just a historical thing, I would say from an organizational perspective, the reason I'd say our diffusers were not stiff enough is mostly because we said we would remove it for once we make them, so we just said, we'll attach cables, it'll be fine. I feel like that is kind of what you guys are saying right now with all of the mounting, which makes me a little scared. Like, I think last year was definitely a little over designed, but like Tim was saying, having someone stand on it, there's no such thing as too stiff. So I would just implore you guys to really come up with some targets now, come up with some specific systems and integrate them. Don't just like leave it for later, because that's, you know, you have the time now. Leaving it for later will leave you with a lot of pain.
Yes, of course. Yeah,
Did you have carbon fiber tie rods last year?
no, we had cables for our,
Okay, because GR24, they tried carbon fiber tie rods and the rod ends were not like staying in. So that's something you should test as well, to make sure you get fast enough and they don't come out.
yeah, definitely.
I don't hate the idea of cables because they're gonna take the tensive load, right? But they're not gonna take the compressive load. So if you do bottom, if you run over a rock, or if you do anything like that, it will allow the side pods to move a little bit up, right? And then when they'll come back down to wherever they need to come down to. But cables in and of themselves are not a bad idea. I would do more than just one. Probably need 3 as you go down.
Specifically, the reason why we're going with the tie rod instead of the cables is because they went up too much, and that they would oscillate when the car was moving.
Okay,
which
all right.
is- Yeah,
That's good. All right. So it's maybe potential you have a combination of the two or something like that. Like if you have your one central rod there and then you have maybe a cable in the front and a cable in the rear or something like that.
Cable in a sleeve or something.
Yeah, I mean, you literally can just order the cable with threaded ends on each end that's crimped on, solid. It's not gonna go anywhere. You put your rod ends on either end and you can set it to the length you need. But cables in and of themselves are not a bad thing. It's you know, how you're gonna implement it through the system.
That'll be something we'll take into consideration. Yeah, we definitely thought about that, but this is a very preliminary side diffuser mounting
Sure.
CAD, so
Sure.
yeah. In addition,
Are we gonna see any numbers, any factor of safety numbers?
for the mounting slides, I don't think so, just because, yeah, we haven't gotten there yet.
Yeah. Okay, I mean, because you gotta get to there.
Yeah.
Because I look at that and I go, I wonder what the loads are there, and I wonder how well that single rod attachment is. Maybe you need the other two just to help, spread the load a little bit. I don't know.
Yeah.
But without some numbers and some factor of safety, it's just, we're putting something together, and I don't know if it'll fall apart or not. And unfortunately, the load cases that are probably the most disconcerting are the dynamic ones that you won't get till much later.
Yeah, exactly.
Thank you for pointing that out. We'll most definitely work on that for the upcoming weeks.
How far behind schedule would you guys say you are?
we're further ahead than we were last year, but as for like how far, I don't know, probably like three to 4 weeks, I'd say. We ended up having to redesign a whole bunch of stuff because we got it put together, and we didn't see what we wanted with it, so we had to go back and kind of start over with some stuff.
What will you cut if you run out of time?
It was originally side pods, but for now it would be probably, the flat floor. Then we'd probably look at cutting side diffusers, and then all the way down until probably the last aero component would be the side pods. If it is shown that they work the way that, we claim.
Yeah, I guess in addition to that, we'll be having 3 mounting trig tabs that will be mounted to the underside of the chassis, as you guys can see here, and they'll be attached directly with the side diffuser flanges. And of course, we would probably need more testing and validation for that. And yeah. Something that worked really well last year for our nose cone mounting was Zeus fasteners. But because our last year's Zeus fastener ran the risk of potentially loosening or falling off during the drive, fortunately, none of that happened, but it potentially could have happened if the car had actually driven. So yeah.
What makes you say that?
Because our Zeus fasteners last year were like, it wasn't really, it was attached to the spring that was in the Zeus fastener, and all it takes to put the Zeus fastener on was just a twist. And potentially, there by chance that they could fall off, just given like the right circumstances. But that's why we're trying to mitigate that with self-eject Zeus fasteners, which will attach to the parts of the bodywork.
Sorry, so what were you saying the failure mode would be, that they would vibrate out?
Yeah.
Did you guys do any testing or anything on that? They're held in by quite a bit of tension.
I
There was-
despise his fasteners. Like, they are always popping out.
Okay.
They are always popping out of everything. I hate them. Like, I hate them.
So the difference with what we have now and what we did last year was that these Zeus fasteners have these, forgot the name of the rounded shape around it, but they will be attached to the bodywork and it will stay on the bodywork, so it won't be falling off as easily as I believe Tim mentioned. So yeah, and of course they're much better than nuts and bolts because they are quick to remove / install during our maintenance. And another thing, or onto our body panels mounting, we're gonna try and use Velcro that will be attached to the chassis tubes. So this sounds a little weird, but we've seen other teams do it and it worked pretty well for them. So that's why that's something we're gonna be trying. Last year we stuck to nuts and bolts, but we felt like that was overdoing it. And I know that's probably not the best explanation for a switch, but it's something that we are willing to try out because it's lightweight and low cost.
You're talking about just the side panels that go.
Yeah, just the
along
side
chassis?
panels.
I don't hate that.
Okay. Then our side pod mounting, we're just gonna be using trick tabs that will be attached to the chassis rear side. And it'll just ensure that this chassis stays stable during even under load and to prevent it from experiencing any vibration or oscillation. We used trick tabs for last year's body panels and they work pretty well, so that's why we're gonna try and do it for our side pods this year. And in terms of our manufacturing process, we're gonna be sticking towards with what we already have because as the judges said, our manufacturing process were much better this year than previous years or GR25. And this involves laser cutting wooden profiles for accurate mold geometry, as you guys can see on the top right. Those are the wooden profiles for our nose cone. And then we would use a CNC hot wire cutter to cut for XPS foam cutting and shaping, as you guys can see in the top left, and apply putty to fill gaps and imperfection. And then we finally sand to smoothen the surface. And for our composites application, something we'll be changing this year in order to help with weight reduction is using vacuum bagging and peel ply. So kind of like what you see in that bottom right picture, vacuum bagging helps with epoxy usage by controlling how well it spreads across the carbon fiber threads, and in turn that helps reduce part weight. Last year we used carbon fiber wet layups, and that was just by feeling whether or not this part of the carbon fiber threads had more epoxy or did not have enough, and we just put more on that. So our epoxy usage was just kind of by feeling, and that could have resulted, or that most likely resulted in the increase of weight for our aero components, and that's why we're looking into, or we're planning on using vacuum bagging and peel ply for it.
So for that, I guess you could compare GR24 to GR25, because GR24 was vacuum bagged and baked, or is that different material?
I believe that this was just an attempt on vacuum bagging, but because one of the surfaces came out really rough, that's why we're gonna also try and use peel ply to help with the surfacing of it. So yeah,
Where are you guys gonna do this?
that's, well, we're looking into that right now because, well, the people that sponsored us last year for their space was the Art Foundry, but we no longer have that. So that's why we're still looking into places right now and asking around.
We just got the news like this week, so,
Yeah.
yeah.
Yes.
So I think your peel ply is gonna leave you a very nice bumpy, rough surface on everything. So what's your plan for dealing with that?
Probably brush more epoxy on and sand it down for a surface finish. That's what kind of the standard is for using epoxy and peel ply for wings.
Okay, and then can you still control like an even surface finish?
It's very thin, so we'd probably the impact it would have is much less than just the error in creating the molds. So it's pretty much negligible because it's such a thin layer of epoxy you're putting on.
So are you using this as your mold? At the end of the day, you're using this as your mold for your nose.
Yes.
All right, that needs to be the mold for your buck. So you need to be able to pull your mold off of it. This needs to be buck for your money, right? So you need to pull the mold off of this.
Yeah.
So your rough surface, like he's talking about, is the inside, not the outside.
Oh, no, I was talking about for the wings. I think,
Oh, same thing.
yeah, no, for this is fine.
It's the surface finish on, say, the inside of the nose doesn't matter, right? The outside of the nose, pretty important. The outside of the wing is everything. So, that's how you have to read it. If you, because you got to get the surface, especially on the wings, you have to get that surface nailed, right? So when you're doing this, that's the first half of the job. And you can take this to some sort of, local fiberglass boat place, and they take a chopper gun and they'll shoot, chop fiberglass all over it, and they'll come up with this ugly thing on the outside, but on the inside, it'll be a nice gel coat finish. And that's where you're gonna be able to get your surface finish. So you're missing one step right now.
Okay.
Yeah. We'll take that into consideration. And then something that we did not have in our previous years, but plan to have in our current this year for GR26 is aero performance validation. So these are the three methods that we're looking into, and they include surface cuts, which is basically yarn attached to the car to show airflow and separation or turbulence. You can kind of see on the top right, once the car is driving, we just take a picture of it with the yarn on, and we could see the airflow around the car. And we have our linear potentiometers. They help measure deflection or movement of suspension components under load. And we could use them to compare data with and without aero to see how much downforce aero is actually generating to the car, with some calculations as well. And then we have pressure sensors, which help measure local surface pressures to calculate downforce, lift, and validate our CFD predictions. And this is just one of the pressure sensors that some of our team members look into for aero validation. Yeah.
How are you gonna mount the pressure sensor? So you're gonna drill holes in your aero surfaces and mount them that way and get localized pressure drop across it, or?
Yeah.
You're gonna have to sacrifice, you're basically have to make two full kits, drill holes in one and mount it. You're gonna have to have a test piece. It's just something to think about in your build process. And then you're gonna have to wire the whole thing out for data acquisition. It's a decent amount of work.
Yeah, that's a real job.
Yeah, it's a lot of work. It's a great way of doing it, but that's maybe more than you want to bite off.
That's something we're still looking into and that some of our team members is gonna look into, but yeah, I'll address this to them, or.
I think your suspension, like, it's a quick and dirty, right? Like you get an AB, you know, you gotta take the weight of your parts off and then you can run it and see, you know, what it looks like, but it's a way of proving you have some downforce on a car.
Yeah.
Potentially also your COP, right?
Of course.
Do you have locations for the pressure sensors? Where you want to put them?
Not yet. I guess questions for the. Yes.
Do you have any calculations for how stiff you want your component to be, like the composite parts, and like what your layup is going to look like?
The layups and all that stuff will be very similar to last year, aside from the addition of fuel plier and kind of changing the actual layup. But the structure of the elements themselves shouldn't change. And I mean, we don't have calculations for it, but we have stress tested our wings themselves, and they can support way more weight than we ever would expect them to. The way we did this is we very simple. We put it between two chairs and we like jumped on it. And we jumped in the middle and it didn't break, so it didn't really flex at all either, so. It's not very scientific, but.
Is that how they're loaded when you're driving?
They're loaded, like, it's distributed across the span, mainly kind of underneath the thickest part. It's pulled down, but it's nowhere near as much, and there's no like shock loading, so.
So the way to have a look at that is, you can do something like water balloons or sandbags or something like that that gives you an evenly distributed weight, right? Again, it doesn't have to be tricky. It's simple stuff, but I feel like when I'm looking at the car build, I'm seeing engineers build the car, and when I'm looking at some of the design, I'm looking at mechanics doing the design. You need to flip that, right? So you have to have something that quantitates what you're doing. So do the sandbags so you can put an evenly distributed mass on the wing and get a deflection. So now you have real numbers. This is the deflection of the wing with this amount of load. And that way, you know your real targets and you know your real ideas on how do we need to, what do we need to stiffen, what do we not need to stiffen? Do you have honeycomb and things like that in your?
No, it's.
Yeah, okay.
Yeah.
So it is a honeycomb core or something like that?
Not in the wing itself,
Yeah.
it is a core of just XPS foam,
Okay,
and then it's 2-ply carbon fiber.
okay. So, now how about the nose cone?
Nose cone, last year was, I think, 3 or 4-ply of fiberglass, but this year will most likely be 2-ply of carbon fiber.
Okay. So, bring that stiffness up with some sort of honeycomb. And again, it doesn't have to be tricky. Also, what is nature's honeycomb? Stick balsa wood panels in on everything between your plies, the layup, and that will stiffen things up significantly. And it's cheap.
Is that your last slide?
Yeah.
Yeah, I agree. You should have numbers, at this point, I think. You have CFD, you have overall downforce, you can calculate your overall stress. You know, you can figure out what your allowable stiffness group you want to have on the car under load. You're gonna have shock load. I mean, you're gonna have things come up and kick your parts. Just take a look at that. You're doing manufacturing to prove that you can meet the benefits that you guys have calculated. Right? Ultimately, that's what we're looking for in a CDR.
And your team and the cooling guy and Curtis, along with the other things, but it goes back to the kind of the first thing I said, where you have the big five, right? You have your tires and dimensions, mass placement, aero, power. So the aero is going to feed into the mass placement because if you move your CG, if you change your mass distribution on the car fore and aft, that's a mechanical change, but that's actually an aero change, right? Because your aero and your mass distribution of the car have to match. They can't be exactly the same, but they have to correlate, right? So what you give Curtis has to be able to work with. And what you give the cooling guides, well, the cooling guys has to work with the power guy, right? And so those things, it's a huge feedback loop. The tires that Curtis is choosing will affect your aero package because of the deflections that we're going to see. The dimensions of it, the wheelbase and track, are going to affect the package that you can produce. So all these things are working so closely together. The ride height sensitivity, particularly with respect to that front wing, is going to be a vital thing, right? If you make it ride height sensitive, in this particular situation, you want 0 ride height sensitivity. Like, reduce it as much as you possibly can. Because that's going to allow Curtis to then work things with the suspension that he can't do if you have a car that is particularly pitch sensitive or roll sensitive, right? And then in terms of your aero balances that you need to hit, you need to probably have an adjustment on front and rear, right? The rear wing is the one you don't want to touch. You want to keep as much rear wing as you possibly can on it and tune with the front if you can. Because if you're dropping the rear wing, then your overall downforce is gonna suffer. Because you start dropping your rear wing, now that's gonna work with your floor. Those like, it's a mess, but they all work together. And that goes back to the systems that we've been harping on. But none of these are done in an isolation. They are all done all together. Has anyone read Adrian Newey's book? All right, Dad, there's a Christmas gift. Listen to what he says. Like, that guy is a freaking genius, right? Like, you've got to listen to what that guy says. But one of the big things that he does is he works on his ride height sensitivities, right? And that's why his cars can go to whatever, Monaco, and they can go to Spa, and they're fast at both places because they don't have these huge aero peaks. And when you have to work with a car that has, like, oh, it's great in CFD because we have this huge aero peak where, man, if all we got to do is hold the car just like this, and we're making 10 billion newtons of downforce. Well, great. I thought we're Governor Nick, you can't get that, right? We have to, you have to make it as numb to those motions as you possibly can. So when you're looking at it, I could care less about the track. Like, honestly, don't care. I could not care less about what the track. If you're giving me this car to run, the first thing I'm going to do is I'm going to go to Home Depot and I'm going to get some 1.5 by 1.5 aluminum. I'm going to tape it to the rear wing. That's the first thing I'm going to do. Now, I don't know if you can do that because of your rules package. I know there's some radius things that you have to play with that limits you on that. But I don't care about drag. Your maximum speed is 60 miles an hour. How much is it going to be? And what's that drag going to do? That drag is going to allow you to brake later. It's going to allow you to have more stability in the car. In this situation, there is literally no negatives. And that goes for almost every racetrack in America, with the exception of maybe Daytona. Maybe Watkins, but not really even Watkins. So Daytona. So unless you're running a Daytona, don't give a shit about drag. stick it to the ground. That's, I'll get up myself on that.
Thank you so much.
You know, this is gonna, your approach is gonna be more ad hoc than I'm used to. That's just the nature of this beast. So in addition to all that conversation, I don't know how much of it you'll be able to incorporate, given where you are and the timeframes you've got. So I turned to thinking about risks a little bit. I mean, what you heard is the drag's not a risk at all. What are the risks? I didn't see anything on where the system wants the CP to be and where your current best estimate of where it is. Is there a point in time that you become a problem for the car's stability? And if there is, focus on that. Is there a risk that you cause the car to fail in some other way? Well, parts falling off, vibrating off, flapping in the wind is. So focus on those high-risk areas where you can really impact the overall system team. And do as much of everything that we're saying as you can. But make sure you know, and a systems view, where the risks are, where you can end up in a disaster for the team. I've mentioned the two that I can think of, but there are a few others.
In terms of the stability, that's gonna be like, if you make too much rear, then you've got a car that's too stable. Big deal. If you make too much front, if the thing's on the nose all the time, now your boys that are driving it are gonna have to be on their toes, right? You don't want that. So, there's gonna be some other things that I talk about Curtis that is gonna affect you guys, but, make the thing, in terms of your aero package, make it as user-friendly as you possibly can.
You mentioned aero balance. We do not have like a formally calculated one right now, but I estimated it to be about, I think we're at like 55, 45 or something. I think it might be a little higher than that. But for the reason why we're not designing around a targeted one is because that center of gravity is constantly changing throughout the year. We'd constantly be redesigning. So our goal is to give ourselves a package that we can kind of hone in at the very end to kind of hit that target, at least now. And then in future years, we'll actually start to be able to design.
But as a systems guy, I get what you're saying. As a systems guy, what I would do is say, CM, all you guys that have mass, you're in this, that's the front of the car over there. You're in this ballpark. You guys, you're in this ballpark. And I don't want you to have to redesign multiple times, so I might be super conservative and there's sort of no overlap. These guys can be at their worst and you can be at your best and we're still okay.
Okay.
Just like you were saying.
When you say 55, 45, what are you talking about?
I guess front rear, so the amount of downforce we're generating on front tires compared to the rear.
And the front would be 55 and the rear is 45.
Yeah.
And then Curtis has a car that has 45 on the front and 55 on the rear.
Which is why we're going to have to, if we can't generate more downforce on the rear wing, we're gonna have to use it on the front.
Yeah, because
You don't want COP.
no. So if Curtis has a car that's 45 on the front, 55 on the rear, then you need to be somewhere about 42 on the front.
Yeah.
You need to be somewhat below, and this thing will, that particular number will be driver dependent. It will be day dependent. It will be track dependent. There's all sorts of dependencies on there that you can't take it into account, which is why you need to be able to adjust your front weight. But those two numbers, like right now you're fighting each other.
Yes, that is why I originally had that on the slides,
Yeah.
but I omitted it because I realized it didn't give you guys any information because it's purely just what we're at right now. It's not what we're targeting. It's
Sure.
not what we're going to aim for. Which is why I took it off. But yes, I do understand it needs to be behind the center of mass.
Gotcha.
Yeah, I mean, we know you understand that, but if you think about the system, this is fundamental stability to the car
Mhm.
and what kind of control it's gonna have. And so, and that's part of your struggle with, there's nobody presenting the systems view. Because at any point in time, you'd like to believe that, you know, the car is gonna be stable and okay. Or at least reasonably stable and not too driver dependent. So again, as a systems guy, I would have said, yeah, you don't pay that much attention to where the CM guys are gonna be. I guarantee you they'll be this far forward. You made sure your CP's this far back. Even under certain failure modes, if I have to take this part off because you can't get it to work, is the CP still gonna be where it needs to be? And so it becomes meaningful in a systems context.
And, you know, to just completely belabor this point. What you do with your front wing is having a big effect to the cooling, right? So at this point, you're better off to get more cooling than you are front downforce, right?
Yeah.
So maybe you could reduce that cascade a bit on the inner to get more cooling, because you can't use that anyway.
We're prepared
So-
to go entirely to a 2 element if we can't bring up downforce on the rear wing and we
Okay.
want to prioritize cooling.
All right,
then Taking out that 3rd element will fix it.
all right,
I
cool.
think cooling is probably
Yeah,
the most important thing on this car from an aero perspective. When we design race cars, the aero people are responsible for meeting cooling targets.
Yes,
And we care about that desperately when it comes to how you actually run a race car. And I think, you know, you don't want to derate your system, right? Because suddenly you get too hot. And that's something to really look at right now.
The actual like cooling metrics will come up in the cooling part.
Yep.
But I believe right now we're just like under the line, or just about the point where like we'll kind of be hovering around finishing endurance without throttling. Is that right?
It's pretty close, yeah.
Okay,
Not quite all the way there, but
yeah, it's like,
Give yourself some.
like 80% of the way.
yeah,
So if I tell you to don't bank on Aero succeeding, you're in trouble. Okay. Sort of tells you, back to, at this point, what I'm hearing, you're behind schedule, lots to do, lots of moving parts, focus on risk. I just heard of significant risk. It helps highlight what you need to focus on the most.
Yeah.
Don't wait till the last minute to make a change to go, okay, we got a backup plan, and then you made it so late that you have a hard time getting the key components in place. Manage the risk. You having fun? I mean, this is a cool design. I mean, this really is neat.
I love talking about this stuff. I love talking about the things that I do. So yeah, I'm actually having a lot of fun.
Good.
Oh. Anything else?
Hey guys, I got a couple questions if you can hear me.
Oh, yeah.
Okay, sweet.
God.
So, you mentioned some changes to the front wing mounting. I know there are certain rules that govern how strong your mounts have to be. Has the analysis been done on that you have that all settled? And is that an SES, or is that still pending your designs being finalized?
It's dependent on bolt shearing or at least the way we have it set up right now, the weak point is the bolt that connects it to the chassis. And that is within SES.
They improved it.
Yeah, something we might want to see also, just as well as everybody's had great comments and showing more numbers is better. So it sounds like the main justification for this aero package is from a cooling perspective. Do you also see meaningful performance gains from what you're getting, or is that purely kind of the reason for it?
It's definitely, this is the first time that we're prioritizing cooling as like a main goal, but there is still the main aero goal of improving overall car performance.
Understood. And also just to Roger, Steven, Vin, all those guys are still resources for you. Feel free to reach out. I'm sure they'd be happy to help. And a lot of the stuff that you haven't shown is analysis that has been done in the past. So if you kind of need a shortcut or somebody to give you a little boost to help out, speed things up to get this done, I'm sure they're awesome resources. So definitely don't sit on that. Don't feel scared to reach out. They're still around.
I gotta ask, I wasn't here for the exact start, but why Aero this year? Is it mostly just for cooling? Or is it gonna incur some penalty on acceleration or autocross, for example?
It will be about the same as last year. Our drag number hasn't changed. And I think last year it was like plus 0.2 seconds on acceleration. I don't remember exactly what the sim was, but it will be about the same.
I remember looking at that simulation and thinking, it was fun. I'm just thinking, I'm just wondering, like, every year we have there's the same question, why have Arrow on this call? Sorry, for a team that's never passed endurance, why have Arrow? When, there are teams like UC Santa Cruz, who was tearing it up last year in endurance, they didn't have Arrow on their car, they were able to do autocross, acceleration, all this stuff. Just having a good answer for that question is always important.
I think
You absolutely are right. You have to be able to justify it. When you're talking to the judges in Detroit, right, it can't be, well, last year we did this, so now we're doing that. That's the thing that the judges hate to hear, right? Last year never happened to the judges, right? So you have to come to them and you have to say, this is what the car does. If we do not have Arrow, if we're running just without Arrow at all, this is what the car does. And you can do this if you can get out running, right? And then you put the wings on, this is what the car does with the wings on. I happen to be lucky enough to have driven a car with and without wings on a tiny little parking lot. And it's faster than wings. I have no doubt in my mind it's faster than wings. But you can't just say that, right? You have to be able to quantify it. And yes, if you don't finish the endurance, now it really doesn't matter whether you have wings or not. Having an Arrow package like that is going to help you in all sorts of places, right? It's going to help you in the design. That's going to, there's a good chunk of points there. You only made 6 out of 15, right? So if you can change that to 11 out of 15, well, now you've made a step there. And I like the fact that you can have, you can lay in flat for your acceleration and things like that. That's great. But let's do something where we can quantify these numbers. So when you're presenting it to the judges, you go, yeah, especially if you get somebody that's frisky behind the wheel, they're going to go fast regardless. But that's not necessarily what this competition is about. It's about the engineering side, right? So you have to be able to give your engineering justifications in absolute terms across the board.
it all goes back to error validation. That's like the number one thing that we haven't done in years past that we need to get done this year, because everything we've said is hearsay. We don't have anything back in each of
Sure.
And so, yeah, right now arrow shouldn't be on the car. So, but if we can validate it, then
Directionally, I think it's where you have to go long-term. But appreciate that the work you're doing right now, you probably won't see the benefits of the work this year. You'll probably see it in about 3 years. So even if you do an aero package for the car and it doesn't really get where you need, and you pull it off and you run the car with no aero on it, having this work that you've already done and then document it. Document. Why did you make these things, right? It doesn't have to be a design brief that all of us are reading. It can be just bullet points that you're passing on to the next generation. And that goes for everyone involved. Everyone has to document what they're doing, because your alumni, they have this information that they have all the stuff that they've done, and they worked their ass off when they were here, right? But you don't know exactly what they did, so it's hard for you to be able to make that incremental gain. So it's kind of this 51st states thing, and you need to be able to make a progression, and the way that you can make the progression is through your documentation.
yeah. That is another thing, is outside of the actual development, we are focusing a lot more on teaching what it like teaching our freshmen that we have kind of what it is that we're doing, how to do CFD, and hopefully creating a stronger foundation.
Absolutely.
And also documenting all of our processes.
Yep.
All right, in the interest of time, I think we'll move on. We're gonna go to cooling next. So Payne is going to come up. And then after that, we'll get into electricals. Peyton has playing catch,
Yeah,
so.
sorry. Right, so you're asked about cooling earlier, here it is. So for cooling requirements for this competition, the rules dictate that we need to keep our battery packs under 60 degrees Celsius. For our motor and inverter, we also have our own self-constrained temperature requirements, so under 120 degrees Celsius for motor, 100 for inverter. This is a simulation from last year, I believe, where this was simulating 1/10 of the Michigan race, and it showed us that we get about a 5 degrees Celsius increase per lap without cooling. So the pack had to be, it would have to be throttled back to 60% peak power in order to make the race. So it is, yeah, thermally limited. Last year, Jason and I and a few of the members worked on the cooling system that they're trying to incorporate in the GR25. It incorporated 2 water cooling loops. One was for the battery packs, the lithium-ion battery packs, and it featured an ice chamber where we would have water that is completely chilled to 0 degrees Celsius, so that we could have more energy that we could store inside of our water. And then there was an electrical pump that would get the cycle going, and we had 5 battery packs where they were arranged in sort of like a series/parallel combination. So you had 2 branches, one with 2 in series, one with 3 in series, and they met back up. The other one was 2 motors and 2 MREX, sorry, A hub motors, 1 MREX motor, and then 3 inverters. We had a radiator for that system, and then we also had a reservoir. One of the arguments, I believe, for not using a radiator in the other loop was because the radiator or the air temperature is going to be much warmer than 0 degrees Celsius. So we were concerned that it might be working against us at the start. So the water would actually heat up faster because of the radiator until it exceeded that air temperature. The reason that wasn't the case for the other loop was because we were never planning on starting that at 0 degrees Celsius. We were always going to start that at room temp, so it wasn't really going to be beneficial. So last year it was just 2 water cooling loops. We wanted to at least validate whether air cooling was going to be viable or not, because if we can go without using water, we could use air. That would be significantly less mass on the car. So we went in through some ANSYS simulations. So this was aligning 56 batteries, I believe. 56 cells and 14 from the electrical data sheet for these batteries, we were expecting about 8 watts of heat generation per cell, and the ambient temperature being 77 degrees Fahrenheit. We simulated a fan that would be pumping 70 cubic feet per minute. And what we got for the 25-minute simulation is that it would last about 4.3 minutes going at full power. So that was on its own going to be a no-go. But it is something that we could potentially incorporate into our cooling system. It's just not going to be enough, which we suspected to be the case last year. But moving forward, the results show that.
Was that 4.3 minutes at like, you said full power? Or
Yeah, at maximum battery power.
Okay. Did you do a simulation with like nominal power, like not? Because I don't think we'll ever perform them straight.
Yeah, not for this one. When we did our simulations, it was in terms of just maximum power, because we want to see how close we could get to running at max power for the full time. But
What is max power? Is that like 30 kilowatts or like 80?
Per cell? Because for all the battery packs, I believe there's 2.2 kilowatts.
Did you say each cell was 8 watts?
Yeah.
So this is with the 8 watts.
Yes. Yes. Okay.
Okay.
Wait, sorry. What was the answer to Jason's question? Was it at
It was 8 watts per cell. So full power, yes.
80?
It's like 8, like about 30.
Right.
It's like reasonable.
So I guess are the future like simulations run at the same conditions? Like the water cooling simulations run at the same power?
Yes. So we kept those conditions the same so that we could compare how effective they were.
And then the other thing was, can you go back a slide? Sure. Do you try a condition where like the air was flowing from the side? Because like you have a hot spot like at the end.
Yeah, we hadn't tried that yet. I think the way that we just did this, it made it easier to get a symmetrical fan. Like we would have a hole in the box around the batteries. But we could try doing a fan from the side of it, especially because, yeah, like you said, it does seem to have a temperature gradient as we go across it. So, yeah, that isn't, I guess, something we tried yet.
I guess going back, when this is only a concern during your endurance, right?
Yes.
So are you at full power of the battery in endurance, or there's gonna be a duty cycle you're gonna go through?
Yeah.
So as you're looking at your duty cycle, is that the condition you wanna really cool at? Cause if you use this, if you're assuming full power output of the battery, you're just gonna oversize your cooling system at some point. So I guess that's are you gonna get there, or is it kind of like, we still gotta look at that?
I think we still gotta look at that, but.
Eight
I think-
watts of heat is already with duty cycle.
That's the duty cycle. Okay, so that's actually the duty cycle based on
A lapse.
lapse. Okay, so that is realistic. Okay,
That's not just full booty the entire way.
Yeah, sorry, no, not the entire way.
Okay.
that makes sense.
But the analysis you showed us, that was the 4.3 minutes. I thought you said that was full power continuous for 4.3 minutes.
This one?
Yeah,
No,
No, the one that goes to
no, the
300.
one that
The one
Greg
after that
said.
one.
Yeah, the one that goes to the moon.
4.3.
That
That's
one.
Yeah.
yeah. No, sorry, I think I misspoke there. Because it would have been the same conditions as this one. This was just the result of that.
You almost need to show us what the duty cycle is you're using for this model, for this simulation, to make sure that it matches what the whole team believes is realistic. So that the numbers mean something in reality, not just a simulation case that doesn't match how you're using the vehicle. Now, at this point, I'm sort of confused on how much of your simulation matches real endurance.
That'll come up later. I'll talk about it.
Anything else or?
So you've given us your limits as far as your temperatures. What are your nominals? What is your nominal battery temperature that you want to run at? What's the motor temperature that you want to run at? What's the inverter temperature that you want to run at?
For batteries, I did be between 40 and 45 degrees Celsius.
Like icicles hanging off of them.
Sorry?
Icicles hanging off of them if you could, something, keep it as cool as you possibly can. Is that what you would shoot for, or is there some operating temperature that you need to hit?
I mean, the priority would be just keeping it under that maximum temperature. I think from the range of 30 to 60 degrees Celsius, the performance of the batteries, I'm not entirely sure if it varies a ton.
Okay.
So I don't know if that's as much of an optimization parameter. Yeah.
I've seen, so, at a racetrack, we had a Tesla that was running with us that, was a kind of a track car type thing, right? Like they had done a ton of work to make this thing to work on the track. They had all sorts of special software on it, they were running the thing, God only knows how hot, like there were no safeties on it. And they could go like hell for 1 lap, right? And over the whole day, they put in 4 blazing laps, kind of a parlor trick. Because they don't have the cooling, and it's all cooling. It's not even, it's not charge, it's cooling. And so being able to cool this thing, and if you had an engine, then I would know, roughly speaking, what type of temperature is a nominal, right? If we were running icy, but I don't have a good grasp for what is the nominals that you're kind of shooting for. So I think those are things that you need to be able to present. Obviously, when you want to keep it under your maximums, right? Just to run the event, keep everything safe, all that good stuff.
You've got a cooling requirement slide you showed first, right?
All right.
You've got, I think that's their 60C for cell temp, motor temp under 120 and inverter temp. That's your ideal operating condition?
Well, the 60s are a requirement by the rules, so that's maximum.
Yeah, you go over that and you shut down.
Yes.
So in my
Yeah.
way of thinking, by the time you get to 55, you probably already overheated. you just haven't shut down yet. And you know, motor temp, if you're at 115C, you're probably already overheated, so to speak. You're just not in limp mode yet, or you're not burning the thing up, or you don't have to park it. So using those as some sort of targets, you're not giving yourself enough room. You have to come up with some sort of nominal, and I don't know anything about this one, so I'm just kind of throwing it out there.
We could safely go to the 60C. The cells are rated for 80. It's just the rules.
It is what it is, yeah. So if so it's not a safety thing, it's a rules thing, but you can't use that as some sort of target at 77 degrees F when you go to, it's a hot day at Michigan and you're running 90 degrees F, and now all of a sudden you're in trouble. Now there's things your drivers can do, and we can talk about that later, but you want to design around having the driver drum full chat the entire time. And then the drivers need to do something to cool the batteries off, then, or to cool the system off, then they can do that without losing any time pretty much. And then, you know, kind of limp home in that range. But when you're doing your design it for some sort of nominals that keep you in an operating range, which is where you really want to be. And give yourself some headroom top it.
And board. Right, so moving on from air cooling, let's go back to the liquid cooling that we were trying to implement last year, but the loop is a little different this time. Because we have a radiator in with this battery segments that we didn't have last year. Because we at least wanted to validate that having a radiator would like whether it would harm or help the system more. Yeah, so heat flows from the cells to the water via these cold plates. Can you see the mouse? Oh, sweet. Yeah, so there's these cold plate heat exchangers for the battery packs, and in the moment we have them in series. Oh, I'm sorry. We have them in series, mostly because of the way that this battery pack is organized. However, we could look into the option of doing them in parallel, because sort of for the same logic we had last year. It's based on the max temperature of the cells, not like what is the average temperature, right? So if we have our last segment in the series getting the hottest water, that could be a downside to it. So that's something that we're still playing around with a little bit, but for the sake of the simulations coming later, we just have them in series now. Right, and then like I said, we added a radiator. Nothing too crazy about the motor inverter loop compared to last year. We just have less motors and less inverters because we've dropped the hub motor aspect for this year. This is the design of the heat exchanger for the battery packs. So what we see is we have an inlet, and then it breaks off into four channels that go around to the other side and then curve back around, go to an outlet. The geometry of the, I guess, width and length of this entire plate is just based on the battery packs. The channels were based off of optimization simulations from last year. We kept that same design because the shape of the battery packs for this year compared to last year is more or less the same. This one is completely rectangular prism though. And so we just are rolling with that design. It also is more manufacturable than doing like more channels, or I guess like crazy winding. So this just made sense to continue the same design. The coolant's going to be water, and that's going to be prevented from leaking by, we would have like a gasket system, and then we would have a compression plate on the other side that's going to be bolted down. And then there's two on the ends here, 1, 2. These would be mounting holes. Yeah, sorry, the zoom showing up on my thing. But these would be mounting holes that we could use to fix it to the heat relator and the battery packs. And the batteries were going to sit on top of the mounting plates like in this fashion. So we would have it with held together with epoxy on the bottom. And they'd just be stacked in this kind of segment. So we could have the 4 rows of 14 cells. The channels are 4 millimeters deep and 5.75 millimeters wide. And the channels, or sorry, the walls are 2 millimeters thick. That might seem very thin and a concern for manufacturing, but last year when we did manufacture it, it seemed to hold up nicely. So we're just going to proceed with that same sort of concepts.
Do you have data from last year's design when you guys tested it?
How
How did it do?
Oh, well, so the car never actually ran, so we didn't have a chance to see what it would do in a race. But we did thermally test it on a test fixture where we had a heating element that was stacked on top of a single plate in isolation. And this was done so that we could extract some sort of heat transfer coefficient. And then when we have it for one plate, we could combine it with all the other plates and come up with a system like that. I believe we ran it at, I think there was heat generation of 375 watts. And what we saw was a heat transfer coefficient that was oddly enough not constant. And we think that there were heat losses to the system that we weren't accounting for, so that changed the heat that was actually going into the plate, which affected our heat transfer calculations. But the lowest value we saw was about 1,300 watts per meter squared Kelvin. Yeah.
Before going to too much of detailed design, like there are more system level sims that you can the cooling system to justify your configuration.
For this, not for this year. We were just basing it off of last year's.
I think it would be very critical to run those, even just basic hand calc. Like I've always been, a big skeptic of radiators in EVs because your coolant temps can only be like 50 C before they're hotter than the components. Like if your air temps at 30 C, how much is that radiator really cooling? From the hand calcs that we run last year, like you need like 10 radiators to like have sufficient cooling. So I guess I would challenge if you need a cooling system at all, or if you do, like how much heat rejection the radiators are actually dissipating to the ground. And that's like the first step we should do before like really going into details.
So you mentioned last year was like 1,300 watts per meter squared Kelvin, but how does that compare to sims?
It's the sims that we come up with a little bit later. They were a little lower. So it came out to about 1,100 watts per meter squared Kelvin. Sorry, you're talking about from simulations from last year. Yeah, sorry. Lower, significantly lower. I think at first we projected around 2,500 watts per meter squared Kelvin. Just going off of memory for that one, and we were much lower than that when we actually tested the plate.
So even with unaccounted heat loss, it was still worse.
Yes.
When you're trying to get the heat away from these batteries, you only have the conduction that's going from the battery surface to that plate. Is that the only way that you can get the energy out?
Yeah, pretty much. So it goes from essentially like the top of the batteries, the bottom, and then into the plate with conduction, and then it translates to the water. Yeah, because it's not very thermally conductive, or it doesn't transfer well to the sides where the wall is surrounding it.
Yep.
And it's not very effective from the top either, though I guess a little bit more effective than the walls are.
So it's going to be tough to get much of an energy flow rate just through the conduction. Is there any way when you can add some sort of, and obviously you can't pour water on the batteries, that'd probably be a bad idea. But is there any way where you can get some convection in there? Of something, air or whatever.
We could essentially combine the system of the air cooling from before and then have this water cooling as well. We also have an aspect to this where there's aluminum fins on these batteries that I guess I haven't really discussed that much yet. But they significantly improve the thermal, heat transfer from the top of batteries to the bottom.
Okay.
And a decent part of that is due to just the batteries themselves don't have like a massive thermal conductivity. I'll pull the values later, but it's about it's about 25 watts per meter Kelvin. But radial it's even worse. It's about 0.8 or 0.8.
Is
Something
there
like
any
that.
sort of gel or something that is non-conductive that,
You'd have to do the dielectric fluid.
yeah,
That's what most people do, but then you're submerging their whole battery pack and
Right.
don't think you're sealing the whole box.
That's a bad
a whole
idea.
other world of.
Okay,
That's fan rules.
okay,
Yeah.
so we would have to use, you have to use air.
Yes.
You have no other choice in there.
These cells are potted, so it's not shown. But I imagine the entire thing is filled with
Okay,
hot.
so the entire
Yeah,
thing
it's
is
a
potted
brick.
too, so it really doesn't want to transfer heat.
Yeah. Well, better than air or like stagnant air.
Yes.
Better than stagnant air, sure.
But not.
No,
insanely better.
That's better.
You can't do a double cooling plate, top and bottom.
Sorry.
Can't just put a cooling plate on top.
Her rules are on top.
The wires.
Yeah.
Electrical connection.
Is on top of it.
The electrical connections between the cell on the top.
So if you're dealing with, how can you adjust the geometry of the battery pack to further improve your cooling because it looks like to me, well, from the work that you did there, when you have the inner cells are running hotter than the outer cells, and the ones that are aft are running the hottest of all,
Yes.
those are the ones that are gonna shut you down, right?
Yep.
So is there a way to change the geometry of the battery pack so you can improve your conduction?
I mean,
More surface area.
yes, more surface area.
It's harder to package.
So the cell is like already, you get the cell, it's potted,
Yes.
right? There's no way that you can pot it with aluminum fins inside of it or anything.
Or,
I mean, is it, so it's just, it's a lump that you get, you can't change.
so we have the individual cells and then we stack them in.
And then you power them.
Yes.
So,
Along with the aluminum nitride fins. Or the ceramic fins.
I hate to be a Debbie Downer, but we'll get whatever thermal performance we're gonna get and we'll live with it. And assuming we get all the way to endurance, we'll maybe driving different than anybody expected, but that'd be pretty darn good if we actually were allowed to get all the way to endurance. What I haven't heard about was our experience with this water cooling system. Did we fully install it on the car? Did we have it there when we were doing some of our pulling the car around kind of things? Did we have any leaks? What was our experience with having this water near the batteries?
Yeah, so we never installed it on the car entirely assembled last year. But we did run a loop on a test fixture where we would pump water through it, so we got to at least test if it would
Yeah.
leak or not.
So why didn't we actually get it fully installed on the vehicle?
Vehicle wasn't ready at the time.
See, again, I hate to be a little too negative, but this is a student-run team. And we're putting water right around the batteries, the high voltage batteries. There's a safety factor there that's always bothered me.
Agreed.
Got to get to where we really validate the manufacturing and assembly and the processes we use can do this and do it safely, regardless of what performance we get out of it.
I actually think if you're gonna run this with a radiator, that it's not worth having.
More what?
It's not worth having water cooling at all. If you just have a radiator that may not dissipate any heat. That would be my challenge to your design.
My head was there, what you just said last year, but I got convinced that you needed to make this work. I was gonna start this conversation with assume the aero guys don't succeed, and so you're not getting any of that nice airflow. So there's a risk conundrum here that I'm not sure which way I'd recommend going.
Okay, let's go to Andrew first.
Sorry to pile on here, Peyton.
Okay.
I've always wondered this about the cooling system. What if you guys this is a very complex system. What if the aero performance is not what you think, or the behavior is not what you guys really think of a radiator? Is there some bounds that there is to, like, what variables can you tune once everything is made to, potentially cool down the batteries more? Is there more that could be done if they're underperforming like 10-20% of the cars made?
Well, for some of the simulations, we came up with scenarios where there is no radiator. We came up with a scenario where there is a radiator and there's one with the side pods. So even if it doesn't perform as well as we think it would with the side pods, we can still say it should do at least this well.
Do you have those simulations?
Yes, they're coming up later.
Okay.
Because I will say, at least when I talked to teams last year at Michigan, a lot of them told me specifically with air cooling that it is like worse than water cooling, but when I was told that when they turn on the car, they can just add more fans,
Yes.
which obviously is a little simplistic, but it's much simpler for us to add more fans that, have to remount the radiator, swap out the pump, change all your tubing for that. Good. Just something to wonder.
No, that's true. I mean, we could, like, the simulation where we want one fan, like we were talking about earlier, we could add more fans. There's no argument against that, other than you just be adding mass to the car, but there's a trade-off to it, right? And if we have enough fans, we maybe wouldn't need the water cooling as much.
The more
but
fans you
it-
run, more you gotta pull out the batteries.
But I'll talk about it in a second. But in terms of leaking, we ran it with we ran our pump at full power last year on the test fixture, and we didn't have any issues with leaking.
Yeah, no, I get that, but test fixtures and real world installations are two different things.
This is true.
That it's nice, it's sort of minimum mandatory, it doesn't convince me that fully installed with everything else going on.
Yeah.
It would have been nice to get it fully installed, see what issues you had during installation in that location, because a bench was easy.
Yes.
And you were pulling the car sometimes, so you could have gotten some other information out of it. So we didn't learn, from my point of view, that cooling will sort of be whatever it is. It's a good challenge, but the safety is the paramount factor, and we didn't learn about the safe operations of this system last year. That's disappointing. If you end up doing this year, make learning about its safe operation all the way from installation to some sort of dynamics, whether it's driving or just being pulled around. Make sure we learn that for future teams.
Agreed. It's good to document.
So I'm still trying to wrap my head around the cell makeup on this and the packaging. So you actually get the individual cells then, right? And you're packaging them up and you're potting them. So it seems like you can think about how you want to do that to try and pull more heat out of there. And it almost seems to me like you just really, you could have a cooling plate. They could set, everything mounts to a cooling plate, but really you need to be able to flow air through there and think about, the downstream air, where the hot air is, and I don't know. Bundling them into a giant brick like that, yeah, you're screwed.
Yeah. Just spacing them out a little bit, increasing the surface area.
And you need to be, these polymers, they're not going to conduct any heat. So a lot of the detectors I make, we do low temperature physics. I operate down, a few hundred millikelvin, 15 millikelvin, and it's all about thermal transfers. And it gets really, really hard when things get really, really cold. So it's something I'm kind of sensitive about too, is how do you pull heat out of a block like that? It's too tight. And you need you gotta get some OFHC copper in there to get that heat to the plate, and maybe bail on aluminum plates and go with OFHC. And but even so, I think you need to get air going through there too, or something, but you can't have all of that bundled up. I think they're just.
When you say get rid of the aluminum, are you talking about the fins, or are you talking about the?
Well, like your base plate here, your heat exchanger. Swapping it out to OFI. So in my world, aluminum's is a terrible, even before it goes superconducting, when it actually has zero, it's no good. It's just a terrible thermal conductor. And so it's probably better than stainless steel, but it's terrible. We use OFHC copper to do all of our thermal transfer when it really, really matters. And in my world, we're in a vacuum. It's a vacuum space. So the only thing you have is conduction, and we worry about the Kapitsa resistance and all this stuff. So it just scares me to have all those cells packed in tight, even with the water cooling, because you can only pull the heat out in one direction. So I think thinking about packaging and possibly, getting air to flow through there, you could still have you know, a thermal conduction coming down, but you can also have air going through there. That will probably help. I think you're gonna have to go this way. You can't go that way. But if you have control over the packaging, you know, then there's a hope, because otherwise these bricks, I don't know.
But I guess going back to your core, get a reliable car that runs, right? We're talking about optimizing performance, which may be a longer term discussion with this stuff. So, you know, it's like, I mean, I don't know, you got like 20 more slides, so we should let you continue, but.
Yeah, no worries.
I guess in the end, it'll be like, what's the overall performance gonna be? What can you get out of it? You know, I think there's questions about, is water cooling even the right approach, but I guess, you know.
Yeah, I think one of the arguments for water cooling is just because last year, like, we didn't get to fully test it on the car. We want to be able to document how well it would do, so just in the future, we can make decisions of, is this even worth it moving forward? In terms of replacing the aluminum, I think one of the main reasons for the aluminum, besides like, it's not the worst thermal conductivity, right? We're still looking like 200 watts per meter Kelvin, but not as good as copper, right? But I think the cost of manufacturability was a concern too. Is copper going to be more expensive?
Copper is gummy. Machinists aren't super happy with it, but it's not as easy as aluminum to machine.
Even if you just did it as a
It's not
top plate,
bad.
right?
Hmm?
Even if just the top plate was copper. Right?
Yeah,
It's touching the batteries.
Yeah, something like that. And then the other thing is, instead of having, you know, all 4 rows together, make more packs where you just have, you know, because those inner ones, they're gonna cook. You know, there's no path for, potting with epoxy is, if you're potting with an insulator with plastic, and so it doesn't help. You could use something like Sti-Cast with, you know, carbon in it or something like that, that runs up the thermal conductivity, but it's still terrible. So maybe you just have more packs that are only 2 thick, you know.
As opposed to just having less
Instead
packs
of
that are
4,
bigger.
that 4 width is, because you're insulating those inner ones, and it's just so hard to pull the heat out.
Yep. Yeah. And I just want to make sure it was clear, the aluminum nitride fins, they're not just on the exterior of the battery packs, like they're going to be next to every single battery. It's not. Just,
Yeah, I figured.
That's what I should clear.
Yeah.
Okay. Do we have any more questions, or should I move on? Yes, this is a schematic of how the battery packs are going to be aligned, so that's why they run series for now, but like I said before, we could entertain the idea of having parallel branches that meet up at nodes, just so that we are not having I guess a weak link in terms of our battery packs. But yeah, discuss that one as much yet, or made up our mind entirely. It would just come down to like a convenience, I feel like. Right, these are just some of the thermal properties for potting and aluminum nitride. Yeah, so this is the Sti-Cast potting compound, with pretty poor, like you were saying.
That's exactly what, okay.
Yeah. And then the
2850 FT black, yes.
Yes.
And you can put graphite in there, and that helps a little bit, but we don't rely on that. That is, because we can't do anything better, we use that, but we don't rely on it.
Okay. And then yeah, for the layer between the batteries and the actual plate, we want to just to reduce thermal resistance, try to keep it as minimal as possible. Which I think was going to be along the lines of a millimeter, because it has to be thick enough to resist the electric field from these batteries. But yeah. And then for aluminum nitride fins, much higher thermal conductivity, like we discussed before. The 1 millimeter was because that's about how much, with this schematic, it's how much room they have before it hits the next battery. They have to be 1 millimeter thick. These are some thermal properties, like I was saying before, the radial thermal conductivity is significantly lower than the axial. Mostly just due to the nature of these batteries are made. They're electrodes that are wrapped around each other. So the electrode is significantly harder compared to just going down the length of the battery. Right. So when we added the potting and aluminum nitride, I believe this simulation was just seeing what the thermal gradient would be like when we add the fins compared to just having no fins. It changes our what we call basically our effective thermal conductivity, where we just kind of bunched our heat transfer coefficient into terms of thermal conductivity along with battery thermal conductivity. We see a a little bit more than double improvement in thermal conductivity. And then compared to without fins, we have more of a parabolic gradient on the outside here. I don't know if you guys can see it that well, but this just has symmetric layers. This one on the outside seems to curve a little more. That's because it's pulling more I guess heat to the top of it, and then it's able to go down more as opposed to like, oh, it can only go down the middle of the batteries, if that makes sense. Yeah, and the way we simulated that was the top was held at 86 degrees Fahrenheit and the bottom was held at 122 degrees Fahrenheit. So yeah, that's how we came up with our simulation for that one. So for actually simulating on MATLAB, this is now we're getting to the point where we come up with plots where we can see like, how does it do with no radiator? How does it do with the radiator? And how does it do with the radiator side pods, right? So this was simulating sort of battery cooling loop. What we have here in terms of heat in and heat out is this is our Q battery. So this is the heat generation of the battery packs, all 5 of them combined. And then how much of it actually makes it to the water in this cooling loop. And then it goes into this radiator. And then we have how much of it is being extracted into the air based on radiator performance. Obviously without the radiator in it, we just neglect that radiator part. They're just saying that it's just going between this Q battery and this Q convection into the water. And we're taking in the parameters, the battery heat generation, we have our coolant flow rates and volume as parameters because we needed to know how much energy is our water going to be able to store too. Yeah, and the way we went about figuring out like how effective our heat exchangers were, like the battery coupled to the radiator, was just using the NTU method, number of transfer units. Last year we used log mean temperature difference as a method, and I think this year we were trying this method out because log mean temperature difference it requires you to have a form of like empirical data. You need to know your temperatures at certain points. This method we can use flow rates or like mass flow rates, and it's easier for us to work with while we don't have legitimate data from actual testing. So yeah, we just plotted the max temperature of the battery pack over time. So like what would be the weakest point of our battery pack? And we have this sort of figure here, which at first I was a little confused by because where that temperature is supposed to be a first order response. So I would have figured it would have just done a go up with a logarithmic curve and just curve off at some points. But I think this is factoring in that the resistance of the batteries increases at some point after we reach a certain temperature. So we're going to get more heat generation because of that, because of I squared R, right? That also just tends to happen at temperatures that were pretty far above what our max temperature would be, because so 60 degrees Celsius, just easy conversion, is 140 degrees Fahrenheit for this. So this is in imperial units. So we see with no radiator, and we're running at 1.63 gallons per minute, which is a value that was extracted from bench test. When we ran our cooling loop on a test fixture last year, that was about the flow rate that we were seeing with our pump, and we haven't changed any parameters in terms of flow rate right now. This is the value that we'd be seeing. It'd be lasting about 9.3-ish minutes. So sorry, go ahead.
What is segment max temp? How did you get that?
That was just done with hand calcs. So the way we did that one was we just bunched 5 segments as one together, which I don't necessarily know if that's the optimal way to do it. But it was just for the sake of simplifying calculations.
So it's like the average temp of your segment, really?
Yeah.
I mean, that's pretty concerning because like cells, if you go back to the aluminum nitride and system, you should go back to that. Like that cell gradient, this one. Also, why is it min at the top, max at the bottom?
Honestly, so Colin set up this simulation. I think it was supposed to be the other way around.
Sure, but like you can see now, even now that there's a 20 degrees Celsius temperature gradient. So,
yeah, well, that was because the temperatures were specifically set there. So what was varying was the heat flow.
Okay, well, in previous sims that I've run with like steady state, this temperature gradient was like 40 C.
Yeah,
right.
So I think this just needs to be polished up more.
Okay, but with your segment max temp, which is an average temp, it doesn't seem really realistic that you should use your average temp for your max temp, and you have a huge cell gradient.
Yeah,
You're going axially.
I think when it was in terms of max temp, it would have been just the temperature at the, like, if you had 5 segments that were turned into one, what's the temperature at the top of it? But yeah, that doesn't factor into how like the last segment is dealing with the hottest water. And then you have to go to the top of the segment too. So yeah, that would need to be polished as well.
Sure, you can continue.
Yeah, so, but based on that calculation, we were seeing 9.3 minutes. Because of what we were discussing, it should be a little less. But yeah, that was based on the flow rate that we had last year. We could entertain having a stronger pump or adding another pump to this system so that we can get a faster flow rate and have better heat extraction. But we haven't got that far yet. I think the main downside of that would just being that a pump might be a little bit more expensive than if we just talked about like getting another fan.
Pay attention to the actual connections, the connectors that you buy and stuff, and find stuff that has, you know, large openings, and just be mindful of, don't just go grab any old elbow or fitting or whatever, you know, make sure it's got a big throat on it. Keep your, so that the flow can, you know, make the life easier on the pump.
Yeah.
So, sorry, this is saying without a radiator, and you start at basically freezing water.
Yeah, so this is part of the aspect to it. Like last year, this loop is going to be starting at 0 degrees Celsius, and this is for just the loop with the battery packs right now.
Yeah, that's fine. I mean, so, okay, you did a kind of quick and dirty. You think you can double, got it. What about with the radiator?
We're gonna get into those simulations.
Okay, yeah, that's fine.
Okay. What else? Sweets. So now we have some simulations here where we added in the radiator. One was with like Forrest was discussing earlier, one without side pods and then one with side pods. The side pods would significantly improve our mass flow rate to these radiators. Obviously, we were saying before, we need to make sure that the gaps for like least resistance need to be minimized. So that it's not just flowing out away from the radiator, but that's a part for later. So we were seeing is based on this airspeed projected of 14.48 feet per second. It improves our time to about 11-ish minutes. So we've, with everything held the same as before, but we now have this radiator. We've extended it by almost 2 minutes without the side pods. But when we do add the side pods in, so we're getting 50%, about 50% increase in mass flow rate. I think it's 46%. Yeah, 46%. It now significantly changes it to about 17 points. So we've almost doubled our ability to run at this max duty cycle. And you can see kind of how the radiator does bias this water temperature here. Instead of rising up as much as the way the max segment temperature does, the air temperature should be at this point somewhere between 80 and 100 degrees Fahrenheit. So because now we have a radiator in it, it seems a little bit more biased to staying at that temperature. However, compared, I think, to the previous plot, it shoots up faster to air temperature than it would have without a radiator. So it does have that aspect of like the radiator is working against it at first, but then once it moves past that air temperature, it's now helping it, and it seems more worth it based on this. And then with this side pod aspect, it's even more extreme here. So it shoots up much faster to that air temperature, but then it's basically held constant for the majority of this simulation. It barely even, I don't even think it gets 100 degrees Fahrenheit simulation.
I want to preface this by saying I have a very naive perspective on this because I've never taken a thermodynamics class. I'm basically a stats math major. I'm a bit concerned just with the rate. Okay, the water is flowing into the segments and then it goes through each segments, right? Or each segment like continuously. Yeah. So in the last segment, the water is going to be a lot warmer.
Right? Yes, which is what I was discussing before.
Yeah, so you're limited by the single hottest cell temperature, which is at the very end of the water. How do you know, or like, can you guarantee that the radiator will make that much of a difference for that last cell?
I mean, based on this for the last cell, I'm not entirely sure, but this I would say it suggests that it does. Because I think what we got from last year's simulation data is that I think it was like there was a 2-degree temperature delta from each battery pack. So over the whole thing, it should heat up. There should be temperature gradient from the first battery pack to the last battery pack, and the water's 10 degrees Celsius warmer. So if we started it off at 0 degrees Celsius in the water or the ice reservoir, then at the end we should be seeing 10 degrees Celsius. So that's still less than the air temperature. And then if the base had started at air temperature and we now add another 10 degrees Celsius to that, that's about where this actually is on here. It might be overshooting it a little bit, but I would think yes, the radiator would, based on that argument, I would say the radiator would make a big difference.
So the real second max then will be 5 degrees Celsius above this.
Around it, 5 to 10, yeah. At least for the water temperature, but yeah, so it would reach that 140 a little sooner. So basically just offset this by 5 degrees Celsius. So yeah, probably looking at closer to now about 12 minutes, which is still a big improvement from the 9 minutes that we were seeing before with the other simulation. So
How did you calculate your heat transfer coefficient of your radiator?
So that was with the number of transfer units method, which essentially you're taking like you have a mass flow rates with our water or with our air, and we're seeing which one has the lower. It's like the derivative of the specific heat capacity, which takes. I don't know if I explained that one right. You take the mass flow rate and you multiply by the specific heat capacity, and whichever value is lower between either the water or the air, that's the value that we use. For I mean, I actually think there's a backup slide on this one.
So I think that's like the biggest discrepancy between this year's sims to
There you go.
our last year's sims.
So yeah, the heat transfer coefficient, it's derived with the mass flow rate of the water into this NTU method. That gets us a form of efficiency in terms of I guess it's squared. The heat transfer for the water. And so we get that to say this is how much is actually coming out of our radiator.
Yeah, you have some questions in the chat too.
Oh, yes, I do.
I think Daniel will kind of help manage it. I don't know if he's still. Can you see the question? Can you read it out?
Yeah, can you guys see it on there or no? I can't.
It's just doing pop-ups.
Yeah, that heat transfer coefficient seems ridiculously high.
Yeah. That is not good.
It's like what 4,000 watts per Kelvin meter squared. Like, how's that possible?
Well, I think that was done with the side pods in mind, like that flow rate, and the heat transfer coefficients is dependent upon your coolant flow rate.
I'm very skeptical of that number because your cold plate is like 1100.
Yeah, it's
Then that's directly with water flowing.
yeah. Agreed. So I think we'll have a better understanding of that when we actually do get to test this. Because kind of like we saw last year with the battery cooling plates, our simulated value was significantly higher than what our actual tested value was. But yeah, 4600 is very high. I agree.
Also, that heat transfer coefficient depends on your airspeed.
Yes.
Did you like normalize that to your expected average airspeed? Flow rate?
Yours is at 35 miles an hour. Is that what I saw in your previous graph?
The flow rate for this was 21.24 feet per second. I'm not sure what that converts to for miles per hour.
I think you have to look at.
Well, that's the one without the side pod. Where you for it, or is that for miles per hour?
21.24 feet per second.
Yes.
14.48.
Okay, sorry about that. My bad. Yeah, so I think we're gonna get a different value when we actually test this radiator. It's also possible. I mean, I can take a look more into the simulation to try to polish that one a little bit more. But that is a very high performing radiator in terms of what we saw last year for heat transfer coefficients.
And I'm assuming they're using a fan on top of that radiator. I think it'd also be valuable to look at how valuable a side pod would be if you had a fan. Assuming a fan is part of it.
Yeah, well, I think with side pod flow rates, we hadn't added a fan to it, but we should. Yeah.
Yeah, so at the start, you mentioned that you guys last year did like a sim with a 60% like derating for the max power. So I mean, at this point, like we just want a car that is driving, so like you can make some sacrifices, or like and not use the max.
Which is probably what we'd have to do.
Yeah,
Honestly,
it
to add
might be worth
I mean, the price.
software or something about like some derating strategy.
Yeah.
Yeah.
Because I mean, the priority of this is to get a vehicle that's actually running this time.
Yeah,
If we're able to race at full power the whole time, that'd be great, but
Yeah, like
if it significantly increases the complexity of this thing, then.
Yeah, like maybe even just do more sims with like lower power, but
Yeah.
see if we can finish the race.
That's true, yeah. Yeah, I think that is the next step to this process. I'm trying to read these questions too. Yeah, water will be ice cold competition day. Can your sims tell you how much heat you wick away relatively if you increase the amount of pump flow? Yeah, so if we increase the pump flow or decrease the pump flow, that would affect the heat that we draw away. I'm not. It just says iPhone answered or asked that question, but I'm just putting that out there. If you had cues, please chat them. Oh, questions. I got you. Okay, I think I'm gonna move on. Is that okay? All right. So we were on this slide, right?
Quick question. Sorry, I'm iPhone or Alan Iqbal. How, like, when it on race day, how will you make sure the water is ice cold or 0 degrees C? And would it be a problem if it was at room temp? Like, would you just not be able to cool your car enough, and it would, like, the last cell would just heat up and after like 2 minutes?
Well, it depends if we have the radiator or not. It would reduce how much energy we could actually store into the water. But the plan for cooling this, we have the water reservoirs have ports where we can adjust, like where could we drain it from the top, could we drain it from the bottom? So we would fill it up with water first, and then we have a bag of ice on the side where we add ice to the system. We have temperature sensors that are detecting the temperature of the water. We call it inline sensors. And we monitor that as we add ice, and we also drain some of the warmer water from the bottom of the reservoir. So it's like we're adding colder material and we're removing warmer material until we get at least as close as we can get. We tried it last year for our thermal test on a bench, and we were able to get down to about 2 degrees Celsius before we ran the test. So it would be close enough. But we'd have to do that relatively soon, or relatively like right before we actually do the endurance race, so that the system doesn't heat up over time, because it's not thermal, like the tubing and everything is not thermally insulated from the air around it and like the car that it's connected to.
The difference that it would make between 0C and whatever else is just strictly the heat capacity of the water up to basically room temperature.
Yes.
And then the rest after that, it doesn't play a part anymore. So it's just an energy sink, temporary energy sink, I guess you could say.
Exactly.
And you can put a little bit of energy in, and then, but it does give you a little extra oomph that doesn't require, air moving by and all the other things.
Yeah, and we visited a competition back in November last year called SoCal Shootouts, and we talked with San Jose's race group, and they did a similar method of what they called pre-chilling their components. They made all their components as cold as possible before the race because of this. It's just an energy argument, right?
You just have a big Yeti with full of ice, a pump, QDs on the side of the car.
Pretty much, because
keep it going.
Like this isn't a commercial vehicle. It doesn't have to run forever, or pretty much forever. It's only got to run for 25 minutes max, really, at this point. So if we increase the energy that it can store, I feel like that's a good enough argument for saying, we can go this thing for the race, right?
If weight wasn't a concern, you could put a giant copper block in there and make it cold, and put liquid nitrogen in there and do all sorts of crazy things like that if you really wanted to eat up heat capacity.
Yes, but But yeah, weight was a pretty big concern for us because last year we had by far the heaviest car in the competition. I mean, we significantly reduced weight, and I think we've discussed that already before, but yeah, anything that's not that mass, unless it really makes sense to do it, is nice.
Can I make one other little comment I'm thinking about? Interfaces kill heat transfer, heat energy transfer. So the fewer number of interfaces where you're moving energy from here to there, the better. And you had that comment about, which side would be aluminum, which side would be copper, all that sort. Make sure that the side with the fins is the side that's in contact with the battery, not the other way around, because then the energy's got to go all the way around the outside before it gets to the fins. So it doesn't really help that much.
Mm-hmm.
So just keep that in mind. Every interface is bad.
Yeah, it's a good idea. Speaking of this too, if we were doing like copper and aluminum sort of interfaces, this is a general question. Do you think thermal expansion would be a huge concern for us, or not really?
No, not really. Like we use Stiecast because it actually has a thermal expansion that's matched to copper.
Okay.
And that matters when we go through 300 Kelvin of change. But you probably want something in there, a little conductive paste or something, because otherwise you've got an air gap. You got all these surfaces at microscopic level are only touching at points.
Mm-hmm.
But then again, that thermal paste is not that great. And so you really want as little of it as possible. Put it on, wipe it all off, then sandwich them up so that, all you're doing is filling up air gaps, because metal to metal contact is going to be better than metal to loop to metal.
Yep.
But every interface is bad. So minimize the number of interfaces.
Sure.
Long skinny stuff also is terrible.
I go first.
You should, what if you just put actual ice inside the loop and then have a filter so it doesn't jam the pump? Because when ice melts into water, it absorbs a ton of energy.
Yep. I think that was actually something that we did last year, was we had like a mesh net in it. So like ice couldn't really escape the reservoir and damage the pump, because damaging the pump was a concern. We hadn't added it, like we hadn't made concept for a mesh net yet. But yeah, that would be something, because like you said, the process of going from
Phase
ice
change.
to water, phase change, right? That itself can store energy too. So that would be useful. Keep going.
Yeah.
Okay, sweet. Yeah, I believe we're all here. Oh, sorry. Yeah, so this was like how we were gonna verify our battery test loop. So we just have like an 80-20 aluminum fixture where we can store the things that would be on the car that are related to the cooling system. So we have our pump, we have our cold plate test segments, we have radiator, and we have reservoir. And we have parts of the system that can help us gauge what's our temperature going to be. So like the inline temp sensor, where we basically just stick a thermistor into the path of the water. We made it last year and it didn't leak, so we're not concerned about that. We have pressure gauges, so we can gauge some sort of head loss, because we also want to be able to model what our head loss would be, so that we know what our exact flow rate is going to be moving forward. We have a flow sensor there, so we just know what our flow rate is as well. So like we can gauge our flow rate, and we can gauge our head loss, and that will be helpful for figuring out what's our pumps capabilities, and if we want to add more pumps or something like that. There was also a concern last year. We projected that we were going to get a much higher flow rate than we actually did when we ran it, and I think a large part of that was due to inaccurate modeling of head losses, and we're still kind of ironing that one out, because if we can figure out why that is the case, then it'll be more helpful for.
And pay attention to your fittings, because they're not all the same.
I
You gotta
think that's where it
swage
came
lock
from.
and stuff like that, and actually really focus on getting high flow fittings.
Yeah, I think with the model that came up so far, I mean, I'd only really had a chance to model the losses from tubing, and we should still be seeing something closer to 5-ish gallons per minute, and what we got last year was about 1.6. So yeah, between fittings and I think the heat exchangers too. I mean, there's so many like 90-degree turns. You have to split into 4 channels and they meet back up. We're just thinking that adds something too.
Well, I think this is the most important thing you've shown us so far, because I think everybody has questions about your modeling assumptions and all that stuff. But this is now, like, I would say this is your number one priority: get something set up to validate the system. And if it's not going to work, you're going to have to scrap it and go for a convection system. given the timing you have
Yes.
right now, but this is, you know, super important to do quickly.
Yeah, we're gonna have that one done. Because the main thing I would need to do is I need to empirically test our plate from last year, where I try to minimize anything else as a part of the system. So I want it to just be a water reservoir. I want it to be the plate and a flow meter, and that's about, oh, and then the pressure gauge sensors too, because I need to know the head loss. So I can come up with some kind of relationship for what is the head loss as we increase our velocity or like our flow into this, right? And then I think once I have that, then I can do there's equations for fittings, but I'm imagining that it might vary based on how good the fitting, like how tight it is. So between those two things, I'm hoping to iron out a lot of the flow we did last year. Because yeah, that's gonna be a huge part of our system. This is sort of what our picture looks like. So this is our battery cooling plates here with the battery pack stacked on top of it. And then here's where the electrical connections are. So like this is why we wouldn't have a fan sitting on top of this. And then these are going to be some electrical components. Like there's a discharge switch, and this will be our system for, I guess, regulating what kind of power we're going to be drawing for this thing. Because in the near future, we're trying to actually test a test segments on campus with the cooling installed. Because we want this is less for cooling, and this is more so we're just trying to see how well a test segment's actually going to do. So we're electrically characterizing our test segments. And then this is kind of where we would stick a radiator here. We have a reservoir here. This is based on the model of the reservoir we had last year that could store 1 liter of water. You have flow meter over here, and then pressure gauges. Last year they were sitting on top of these beams. I'm imagining what this somewhere else. And this was our electrical pump over here. Yeah, so if you just wanted to visualize what our test picture looks like, this is essentially it. All right, I think that's all I have. Do we have any more questions?
So when we finally install this on the vehicle, assuming we head down this path and we like the results adequately, what kind of leak test are we going to do on this cooling system?
I mean, it start with at least running the pump at full power and just seeing it, or it shouldn't be an if, it will be able to withstand that. I think the main concern would be like when we're actually racing with the car, we might get bumps in the road where we just have a sudden spike, like impact. We might have a spike in the force that's going sitting on top of this battery full plate. I don't think we had really thought that one through entirely, but I think the plan would have just been if we can get the car running, throw it with the cooling system on and just see how that does. But in terms of testing like what's the max capabilities of this thing in terms of leaking, we were still kind of ironing that one out.
So again, I'm resisting any further performance discussions. To me, it's all about safety. What we usually do in pressurized systems like this is we figure out what's a good proof pressure. Can the pump generate a good proof pressure test to deal with the other things that are likely to happen when you really start getting into dynamics or not?
Okay, so if we didn't have a pump that would hit those points, would you suggest just getting another pump for testing that can
just to do some sort of a proof test? Yes.
Okay.
To do a proof test before you trust this thing with real batteries running.
I mean,
So what you would
the
do-
downside for even though right now is that would just be spending money on another pump, so we lose a little money because of that. Is there another method?
Yeah, so what you do with an IC engine is you have something you fit on the top of the radiator, right? And then you pump it up and
Yeah, it's not buying another one, it's borrowing one to just run the test.
oh, I mean, this, you can go to AutoZone and get this, right? So, you, in our operations is like maybe 30 PSI or something you put to it. So on this one, instead of 2 bar, I'd go 5 bar. Like put a ton of pressure to it and make damn sure that that's not going.
Exactly.
No water's going anywhere.
And the kind of numbers he's talking about is you got to have that conversation about what constitutes an adequate quality verification that as installed, this thing's not going to leak. And he said about a 2x. I think that's sort of the minimum for the uncertainty.
Well, it's gonna be 3 absolute.
Yeah.
So, you know, sooner or later, what's gonna happen is you're gonna fail the radiator because all the tubes are gonna balloon out, right? So in terms of the pressure, that's the first thing that's gonna go with the system. So you don't want to mess up the radiator that you have. So you talk to Mishimoto, you see what kind of pressure that the radiator will take, and then you test your system
To that.
to that.
Okay.
And make sure your normal operations then is well below that. So
Yeah.
instead of just the flow rate, all trying to meet performance requirements, I'm saying, take a look at all of these numbers relative to making sure there's no leaks so that this thing stays safe.
Yeah.
And if it means you gotta run at a lower pressure, lower flow rate, so be it.
Right.
And I don't think the pump itself is probably going to make enough pressure, but it's gonna be more of the temperature rise and things like that.
So my guess is you need something else. Sometimes people have to, gotta have a test port so that you've got a place to hook up your only to do a proof pressure test and then seal it up.
Well, I mean, it'd be temperature, or, you know, God forbid we get in a crash or something like that, it needs to be able to withstand that too. Yeah. The question-
Real quick, also, I'm not sure how feasible this might be, but if you have a nice, test bench with a full loop and the fittings and tubings you're planning on using in the car, see if you can find maybe a shaker to put it on or something like that. Just anything or any way, maybe it doesn't have to be that, but some way to expose it to dynamic vibrational forces as well, just to see how your fittings and tubings are all reacting when the loop is also full and running.
Yeah, I think, so there is a shaker on campus that we could use, I think, over in Professor Fields' office. We were trying to run that test last year, and he was very adamant that we just didn't need to run that test. So I guess we never got around to it, but.
Put it on the back of a flatbed truck and run it down the roof and feel like you can find.
Do that?
I mean.
Yeah, you
simple.
take the 80/20 thing, just put it in a truck and drive around. That's a great
Go
idea.
on some off-roads or
Yeah.
something?
Literally.
I think it's a great idea, but I would caution, it has to be the real, what I call flight configuration.
Yes.
Yeah, like
Can't
that
do it.
80/20 test bed thing.
Right.
It can't just be sitting in the car, it's gotta actually be set up.
It can't just be one module. It's gotta be the routing and everything, and the real connectors. It's gotta be high fidelity representation of what drives to make that test worthwhile. Otherwise, you get data and you don't know how to correlate it to the actual driving vehicle. So it's a great idea, but you've gotta build a lot more of a complete representation than what you're currently planning.
Yeah. But I think it'd make more sense though to do it with components that aren't actually like going on the car, but things that just simulate it, because I wouldn't want to damage anything if something were to go wrong.
Buy two of everything.
Buy two of everything.
Because to me, this uncertainty of whether or not we've got a design that is safe enough to hold together to really use is paramount, and we didn't get that out of last year. So I actually like the suggestion. I like the truck driving probably better than the vibration table because that gets too complicated with test fixturing. But that's very worthwhile because it gives you the learning you didn't get last year on just the basics. Forget all the how well it performs.
If you could, you would take the whole car and instead of, putting the tires on the car, you have some sort of fixtures that just holds it by the hubs. And that's what you mount to, literally a flatbed truck.
Just have a chassis.
Go to Home Depot and get a flatbed truck.
Okay.
It can be really simple stuff, but who else is doing that? No one. And if you can show the judges that you're doing essentially simple testing, but it's real world, it'll blow them out of the water.
You'll convince some of us that this is safe and we can. breathe
That too.
easier.
Well, you'll convince yourself it's safe. So when you get in it, you're not like, how
Hopefully
we
that
go.
doesn't leak, right? Yeah. Sorry, I had a question over there.
I don't know if this was already mentioned, but for the pressure proof testing, you could like fill it with water and then use like an air pump.
Yeah, that's what I was talking about with the red.
We did that last year with, we made a heat exchanger for the custom inverter last year. We stored it with water when we pumped it with a little bit of an air pump, right? Or was it just with the air pump?
It was both.
It was both.
Got like 5x safety factor.
It's just, we should probably move on, but you're gonna keep getting some of us going with, because I don't remember seeing the pressure inside the system on any of your charts. So we're so focused on the performance from a thermal point of view, but there's a whole nother manufacturing safety component, weakest link kind of view that we just didn't talk about, and you've got to be thinking about that. And that's part of what this test drives you to, is to see how good a job you've done on all those other things. You know, there may be some cantilever joint there that you've got that happens to have a connector right there, and that's the weakest link, and that's what pops open.
Okay, agreed. We have anything else, or do you move on for a second time?
Let's move on.
Yeah, pretty cool. All right. Electrical cycle direction. Ready?
Hi, I'm Ryan. I'm the electrical tech director. And I'm going to go over the competition recap from last year and some like high level goals and actions that we're taking. Okay, so last year we did not pass the battery inspection. That was a big issue on our sub team, or our side, I guess. So the main problem there was we just didn't have time to finish it. And as kind of part of that, we didn't do the inspection video, which would have helped us a lot in figuring out what, it would have given us a head start of what we could have like fixed before competition. And then the electrical issues, there were quite a few. So on the high voltage side, we didn't have our junction box finished. And we were trying to rush and do that at competition. That's like the box that distributes high voltage to like your inverters and has like some, like the energy meter and other components. So it's like in the picture down below. It didn't fit in the area it was supposed to in CAD. So there's some like kind of sketchy like bending going on there that try to get it to fit. And then additionally, the high voltage wiring was not completed. Part of that was we chose some connectors before we figured out how to crimp it. And then after everything was done, we found out that the crimping tool was like something like 10 grand a year to rent. So we tried making our own crimps and they didn't last as long as we needed. So that was quite a big issue. With that, we had some non-functional required sensors, namely our accelerator position sensor was not functioning correctly. Which led to some like last minute hot fixes, like the signal conditioner for those sensors, as well as our low voltage, I guess, power supply. Yeah. And all of that could have been solved with some integrated testing of our low voltage system, which we didn't fully do. We tested like some components with like our wire harness, but not everything, which exposed itself in Michigan. And then some of the components were not mounted, like the low voltage battery or fuse box and whatnot. Those were just left to the last minute and did not get on the car.
You know, this is a powerful chart in my opinion. I really like the focus the team's showing this year on just getting the basics. But think about what's on this chart. Nothing on this chart talks to performance. Everything on this chart talks to basic blocking and tackling, manufacturing, integration, test, schedule margins, procurement, all those kind of sort of boring things. Got to realize that, because we as engineers, if you'll let me join you for a minute, love to do the more sexy part of things, which is the performance, pushing the envelope, understanding the complex models, fasteners, schedules, that kind of stuff is boring. But to get a car that's going to run and get to endurance, you've got to do all that other stuff as well or better than you're doing all your performance predictions. Powerful chart. Even if every team wasn't contributing to this is a little bit disappointing. How far from passing inspection we were. And I think you're doing a lot this year to try to avoid that. But it requires a focus on these kinds of things in every team and every subsystem. I'll get off that soapbox.
Okay, so to address some of those shortcomings, here's some like goals and actions that we would like to take. So our goals would be to complete a mock inspection by the team. to kind of prepare us for passing the real inspection at competition, which would be the battery pack inspection and EV active, which is where we power on the high voltage system and run the wheels floating in the air. And some actions to do that we took would be like the creation of the systems team for mounting and integrating the electrical systems with the mechanical systems. Having targeting an aggressive timeline to leave us with more buffer. So we're planning on completing the high voltage battery pack with like a quarter to spare, so like 10 milliwatt weeks before competition. We're trying to submit the battery pack inspection video by its due date of 5/27. So we could, I guess that kind of goes hand in hand with the more aggressive timeline. So we need to get the battery pack done before then to submit the video. We'll like to do some kernel testing. So having everything, I guess having a setup where we could test each electronics box individually as well as just as an integrated system. And then more condensed mechanical packaging to make the mechanical integration easier. So in the top image here, we have like an example from another team's battery pack inspection video. So it's just like a simple walkthrough of here's how we address each rule and just like a walkthrough of the design as a whole. So it should be simple to do if the battery pack is done, which is a big if. And then down below we have like kind of how we condense the mechanical packaging, which Vin will talk about later. So like on the left is what we had last year, and on the right is how it's kind of moving to this year. Yes.
One comment, one question. The comment is I would call this the electrical systems team, because it's not a systems team. Right? That's not the team that's dealing with making sure the CP and the CM are in the right places, but it's a good suggestion. What's your targeted schedule today battery pack inspection video completion date?
I guess we haven't thought of that, but
you said
it's just by the due date.
But that's no margin.
Yeah.
So if you're really going to drive yourself to manage schedule margin, you got to put targeted dates that you're driving yourselves to. So you said your aggressive timeline to leave more buffer, but mentally you're allowing yourself to expect to complete that inspection video, which is sort of, I think, a pretty key sort of end thing. And you're targeting the exact same date, which means you have no schedule margin. You need to pin down a date and talk about how much schedule margin do we have. And at this point, you know, if you don't have a week, then you don't have any. So I'd aim for at least 2 weeks. And if you can get a month, great.
Yeah, I was thinking 5/1. Just looking at, if it's due 5/27.
Okay, so our targeted date to have the battery pack finished is before that. So like theoretically, once the battery pack is done, it's simple to make the video, but it's good to have like a concrete date.
Yeah, have a concrete, drive the team. I mean, the industry has a whole bunch of ways of how to show 2 different target dates. You've got an absolute drop dead date, but here's our internal target date. But your team won't be working to that internal target date if you don't actually have it. So make sure everybody, I mean, you'd hate to sit there and I got the battery. Oh, by the way, we need special video equipment. But you said we were doing it on 5/27. So work to a real date, have real schedule margins.
Yeah, and additionally with that schedule, like last year we had issues with like getting the battery modules wire bonded because so it was like we had our internal schedule that we never communicated to kind of these external companies that support us, and then they're like, oh, actually on this date for like this month we're going to be out of office because we're moving to a new office, and then that's how schedules get delayed. So
yeah, it's not just you,
Right.
like not hitting yours, right? It's the people that are supporting you.
Yeah, no, that's a good point. Yeah, if your date is 5/1, but there's some mechanical components that are supposed to be there for it, what if they're not working 5/1? Because they know the date's 5/27. Yeah. Using schedules to drive teams is really important, and having internal targets is the only way you actually have schedule margin.
So I have X is Odin. Yeah. What do you do? Okay, so I'm the HV electronics lead. There's another HV electronics lead, but he's too busy with his internship, so he's not. Oh, he's here, but he's not presenting. So last year, year 25, our battery pack was, it looks like that. It's bigger. The main problem with it is it's very difficult to manufacture. So first the aluminum nitride fins, they tilted and they were like pretty much impossible to align with the cells. So what we end up doing is, I think Jason figured it out a way, is you just put tape on top of the cells and dip the aluminum nitride fins in epoxy and put it in to the top instead of the bottom. That is very messy and it doesn't really guarantee a good thermal interface between the fins and the cells. Also, it's might be hard to see in this picture, but there is a acrylic cell alignment thing in there, and that is not rigid enough. Like once we put it in, we can't pull it out because when we try to pull it out, it just broke. And also, there are thermistors on these PCB bus bars, like there, that's a thermistor. The problem with that is to best measure the cell temperature, we decided to have like a through-hole wire thermistor go directly into the hole, like those are the two wires from the thermistors, and those are soldered by hand, and those are soldered after the segment has been assembled. So it is a quite dangerous job to like just to solder those right on top of batteries, because if you slip your solder iron by like maybe half an inch, it could short the battery. So ideally, we won't do that. And also, we had some problems of the PCB warping during reflow soldering. That is mainly due to there's this big, thick, nickel-plated copper bus bar on one end to carry more current, because there's this very thin section that's not wide enough to carry the battery current. The problem is the copper and fiberglass, they have different thermal expansion coefficients. So when this thing cooled down after we take it out of the reflow oven, the PCB was bent. And as a result of that, the PCB doesn't really sit flush on the cells. So when the wire bond machine pushes down, the PCB will flex, and that messed up the wire bonding. And more importantly, since we did the reflow soldering to get these bus bars in place, there's flux residue on these exposed like gold finish pads, which also made wire bond very difficult, and it took us a lot of time and work to clean them. Yeah, and lastly, that's not really a segment issue.
The wire bonding, that's the spot welding that.
Yeah, it's not spot, it's like a ultrasonic thing.
So it really is wire bonding, like
Yeah.
chip level wire bonding?
Yeah.
What do you wire bonding?
We bond the cells. We use aluminum wire. We bond the cells to the bus bar.
Ultrasonically, I'll be darned, okay?
Yeah.
You don't use a spot welder to do that?
Ultrasonic bonding is better because first we could.
Yeah, a eutectic bond is far better, but I was just surprised that you could get a eutectic bond that big. Okay.
We have a sponsor that does.
Yeah.
Okay. I just haven't seen one. That's fine.
And for the tracker battery container, which was called the accumulator before, there are some bolts that are pretty much unreachable. So it's hidden by that piece of aluminum, and you can see how it's unreachable. There's a bolt in the fuse that's like under this thing, and the wrench need to make like two 90-degree turns to reach that. And so how we end up installing is we took off this panel so it could fit like so it could fit the wrench in from this side. But then after this panel is bonded to the accumulator, this whole thing is permanent. So in case we blow the fuse, there's nothing we can do.
This is why mechanics hate us. Just a statement.
And also, some wire bend radiuses are underestimated. So did you see the two holes there? There's supposed to be a current sensor mounted to those. They're not there because the current sensor has a super thick, like 4-wire shielded cable. And we just can't get that thing to bend enough to go into the port that's on the circuit board. This year we found like a slightly more expensive but thinner cable, so that'll get fixed. Yeah, so I'll talk about the design first, and after that, I'll talk about the new manufacturing methods that will address these problems. So the battery pack is designed in mind so it could finish endurance without reducing power. Part of that is that's mostly limited by how many watt hours we have and by make sure the battery doesn't overheat. And as you see in the previous cooling presentation, the battery temperature is like pretty much dead on 60 C. So that is San Jose State University's data from last year. This is a autocross lap, which means they're driving the car as fast as they could. I chose to use their data because they have a similar car. They're tube frame. They have the MX228 motor. Their car is lighter than ours last year, but since this year we have a smaller battery pack, we believe the total weight will be similar. So basically what we got from this graph is in one lap, going as fast as we can, the RMS power is 28.6 kilowatts, which translates to the 8 watts of heat per cell I mentioned before. And since endurance has 22 laps, the multiplied results is we basically need a 6 kilowatt hour pack to finish endurance. Yeah, and since the rules let us do at most 80 kilowatts peak, we're gonna shoot for that number because then we could go as fast as we can.
Seems like they run region, or is that just data?
I think that's just noise, like because it's high voltage. It's so there are several choices that we have for the battery cell. The two major ones are for the sizing is 2170 and 18650, which means the cells are like 21 millimeters diameter and 700 and 70 millimeters tall. I don't know why there's a 0 on the end. It's just how the parameters are set up. Yeah. So Molicel and Eve, they're basically like the two best like high power cell manufacturers. So we mainly look at those. Yeah. So the P60Bs, they are the most expensive. They haven't been released yet. But they're the highest capacity dense cells available on the well, not yet on the market, but should be soon. That will be our top choice because they allow us to get to 6 kilowatt hours with minimum weight of 19.6 kilogram. That's just the cells. It does not include the segment walls, the potting. That's just the cells. However, the E50PLs, they are just 5 amp hours per cell, less energy dense. However, they are the most efficient cells. They have a DC resistance of 3.5 milliohms with 2 in parallel. So you can see if we use those, our cooling load will be significantly decreased. So that'll help to prevent our battery pack from overheating. However, we will be short on kilowatt hours, so we might need to increase our regen, which will increase heat generation. And also we might even still need to throttle the power with regen.
Before I'm done, Alex is gonna learn to just have coffee and donuts just for me out in the hallway, so I can not pay too much attention and not slow you down too much. What's TBC stand for?
Traction battery container.
Okay. So we're targeting a 313 next year, having this fully assembled.
Yeah.
Okay. So that's 4 months from now.
Yeah.
So why are you talking about might want to consider an option that isn't even available yet?
According to the company, that thing should be available in the middle of December.
And when can you get the E50s?
Right now.
So just go back to that chart that we started with that I thought was a powerful one. It says your number one problem is time.
Yeah.
So my suggestion would be make a decision. Don't wait. Because if you can beat 313, okay, I got it. At least it's on the schedule. I didn't know what TBC stood for. That's good. Pull it back. Get it started. Build the first one.
Okay.
As soon as possible. Because what's going to bite you is not this performance and the performance advantage you'd get from using the MOLA cells. It's going to be manufacturing. It's going to be trial and error. It's going to be the kind of issues that hit you last year.
Okay.
The only way to avoid those isn't to wonder if you can get a better performing cell a month later. And then that's them saying it'll be a month. I presume you're doing design work right now. And unless the design work you're doing is exactly the same for the two different cells, then you're distracting yourself with a cell option because it looks attractive.
These cells are standard sizes, so they will both fit nicely in our design.
Okay. And just, if I was you, I'd have cells already in hand. Given what you showed before, I would say, man, just putting this together is our number one disaster. I have a bunch of them already in the labs, ready to go experiment, trying to do the assemblies.
Okay.
Because what if you get them all and your new techniques that we haven't seen yet, but they're new techniques.
They're tested.
Okay.
Yeah, we don't like a small test signal. Just
good. Glad to hear that.
Okay.
There's two numbers on here that be really important to me. It's 0 and 0.
Those are because they're sponsored by Tesla, so we could get them for free.
All right. Well, in my head, there you go. There's your answer.
Except they don't show up until at least December, and that's if they make.
No, that's the other one. The 60 is the one. Because the
60
50 they can get right now. And if you have to carry an extra 10 kilo.
Oh, I thought it was the E.
The 50s, they can get for free. The 60 they gotta wait for. I would say stick with the 21700s, just so that you're not, so that you can keep designing, but, yeah. And then the other thing that I don't know if you have time to figure out, which ones have the highest thermal conductivity?
That, the data sheets don't tell us.
No, they don't tell you. You'd have to test it, and that's off the table,
But the heat per cell.
Yeah.
But the heat per cell is like really.
Yeah.
The heat per cell is the key based on the conversation we just had. 'Cause
Absolutely.
he's using 8, right? And you got a 4.62 that's free and pays, and your penalty is 20 pounds.
Yeah, I was just gonna ask, can you have an extra battery pack to make up for the loss in total capacity?
Elon's a billionaire, just order all of them.
In a perfect world, and I'm gonna completely, I'm sorry to mess you up. In a perfect world, I would say you build a pack with the 3Ps and a pack with the 2Ps, you run the 2P in autocross and you run the 3P in endurance.
It would be quite tricky to get two different size battery packs fit in the same car.
Or I think there
No,
are
I mean,
multiple
swap
teams that
them.
already do that.
Are they the same? I thought it was a.
No, this number is how many cells we have in parallel and series.
Oh, okay, all right,
Yeah,
Yeah, I didn't
Okay.
understand.
I thought that was a part number.
yeah, that's the part number.
Okay.
Yeah,
All
this is a cell configuration.
All right. All
Yeah.
right. So then I would carry the extra 10 kilo. Just to give you an idea.
Also drive like a bigger container and
Yeah,
actually gets.
if we switch to 3P, we need to basically restart the car.
Okay, well, that's an issue. I have, like, in long races, I've carried 2 batteries with a switch that the driver can, if we drop a battery. And yeah, you're carrying an extra, whatever, 15 kilo with you for a long time, but
So
you
you're,
finish the race.
you're committed to 2P140S, is what you're telling me.
Yeah.
Okay,
Okay.
so just
All
cross those out, because they're not even in consideration, right? So then you're really looking at P50, PL50B, and P60B.
For $1,200, yeah.
Got it.
I guess part of what we're saying is in our minds, the trade study isn't all the performance parameters you're putting. It's schedule, availability, weight. Yeah, and you do have weight there, but it's some other things. And the highest to me is being scheduled so you could go get this done.
You need enough capacity to finish the race and you want to do it as cool as possible because of all the follow on cooling. Yeah.
Problem is it's a little less energy dense and less energy overall.
Well, energy meets it at some point. Yeah, you're 5s, then you're just running at a lower performance rate to survive.
Yeah.
Do you know how fast each of these will get here?
Tesla sponsorship, I'm not really sure, Ryan, do you?
When did it arrive before? Or Jason, do you know exactly when the cells be shipped or?
I don't know.
Okay.
Oh, I know.
A bird in the hand. I take the bird in the hand, get whatever's gonna be here first.
Yeah.
Late January.
Mid-January?
January.
Late January for the cells?
See, I already don't,
Yeah.
I like your 313, I think.
Yeah.
But I'm already not liking it, so the parts are coming in,
Yeah.
2 months ahead.
Yeah.
Do you know what the fastest one could be, Owen?
That ships in 2 weeks. We order it now, we get it in like 2 or 3 weeks.
And how much performance do you theoretically lose?
Well, in terms of power, we're better. Well, we're still
You have the
limited by
same
rules.
capacity, but the
Yeah.
Eves can put it out faster.
Yeah.
It's total energy that's the negative on that one.
Yeah, they make less heat, so, but they have less energy, so.
Those come in 2 weeks. They come in 2 weeks, man. You gotta.
Yeah, get started.
Steve has never made an accumulator that is past tech. Make one that passes tech first, then worry about all this other stuff.
Gen 24 Techo pass, it's just charging.
Yeah, well, there's never been one that's passed charging.
Yeah. Okay. Moving on. So that's the reflective property segment. So the sidewalls are made of 1/4-inch fiberglass walls, same as 25. We choose them because they're rigid enough to satisfy the 40G acceleration requirement in SES. And on top, we have a FR4, which is also fiberglass cover to protect the circuits inside. And there are 2 openings on there that are for BMS signal connectors. The connectors aren't shown in there because they're counted in the wrong direction because I decided to flip the BMS upside down. But that'll be fixed. Yeah. And for the protected battery pack connectors, and we went back to the Amphenol Throck ones, which is what we used in 23 and 24. I did that because we wanted to avoid the the new ones, the HV 1200, that's impossible to crimp. Oh, and by the way, those are the 5.7 millimeter ones. They're smaller than the GR24 ones. And basically those are rated to 120 amps. So basically that's enough to withstand our battery current, and it saves size and weight. Yeah.
Who uses those connectors in industry? Is it like an aerospace thing? Is it?
It's a mostly low power EVs and some like electric skateboards and stuff. They use
Okay.
it.
So this isn't the thing that you have to get the super expensive crimp?
Yeah, that thing just has like a copper cylinder which allows a wire to go in.
have a crimper.
And we use a normal crimper for that.
Okay, there's no, I guess I'm thinking like, for the crimp that you were, it's $10,000 a year or whatever. If that is used in industry at some point, then they're gonna use it a certain number of crimps and then they're gonna time it out. So get one that they've timed out and it'll work just fine.
Yeah.
Is that HP crimp still gonna have to happen?
What crimps?
The one we tried to make last year, the HP 800.
Oh, I have one of those on the electronics tray, but we've bigger reused last year's wires for that.
Oh.
We have several crimp wires that we could just take off. Yeah.
So what's your battery current? You talked about this is adequate. Sounds a little small. What's the current? How much margin do you have?
Our peak battery current would be around 80 amps.
So you got a 1.5.
Yeah, like 5
safety. You okay with that?
Because that's the peak. That would peak for like at most maybe 3 or 4 seconds, and that's when the driver completely floors the throttle.
Okay.
The average would be less than 50.
Okay.
Yeah. And if you open the thing, there's the 2 BMS boards mounted upside down. That's because the cell balancing resistors are pointed upwards. That helps heat dissipation. Yeah. And for the wire buttoning, we have the 2 by 0.2 millimeter aluminum ribbon. And according to the datasheet, they have a fusing current of 86 amps at our length, which is 8 millimeters. That is high enough to withstand our peak battery current, and low enough so if something shorts, that wire bond breaks before the cell explodes.
Could you put some numbers to that, please? What's your expected current at this location?
So the weakest connection is from the bus bar to the cell's negative terminal. So there's one wire bond carrying half the total current.
You mentioned the fuses are at a number. I can't remember what number you said. 8 amps.
The wire bonds will fuse at from the current data sheet 86 amps.
86.
Yeah. And also by rolls, the main fuse has to be at most 1/3 the total current rating of the wire bonds in parallel. So.
Okay, so it's driven by tech spec requirements.
Yeah.
You're gonna fuse test that like we did last year?
Yeah, we will.
Just those numbers are notoriously flaky.
Yeah.
There's too much manufacturing variability, and so you get different performance out of different fuses.
Yeah, we will test them by running a high current through it and measuring how long time it takes. Well,
okay, good.
Why are you doing this instead of the single?
Because first we have a 2P pack, so there's no room for the stitch bonding. And then having a wire bond, a shorter wire bond means it's going to fuse at a higher current, so that helps passing tech basically. And also you could see we have two wire bonds on the positive terminal to reduce resistance.
Oh, okay. Yeah, I thought the two negative bonds were on the same side, but I understand. Is there the same bonds as us, same cross section?
Yeah.
Okay.
They're same cross section. And the BMS fuses are on the side. One end goes to the bus bar, another end, so the PCB goes to the connector into the board. And the thermistors, instead of having through-hole thermistors going deep into the cell, we just have surface mount ones that sits in this pocket between three cells. And then we'll put a drop of like thermal compound on top, so it thermally bonds the thermistor to the cells.
When is ESF due?
I think it's December 8th.
Yes, December 8th. Okay. What's the status on getting these approved? The design. Have you submitted yet? Or you haven't submitted yet?
I haven't submitted yet. We're probably gonna submit ESF without the wire bonding, the fuse test data, and then test it later. Because
okay, I'm more concerned about the thermistors if they'll approve that, but sure. So that's what they had issues with last year. But we didn't have potting.
Yeah.
Or thermocom.
Okay. And to connect the cells to the output terminals, we have this press fit PCB terminal that's rated to 160 amp. It's basically like a nickel plated copper piece that has these 16 pins that just gets pressed into the board. There's no soldering required. I use those because they're convenient, because soldering big copper blocks like that is very difficult. It just removes the heat instantly. And also soldering in the high current path is banned by FSA rules. And the bus bars are aluminum sheet metal. It could be copper. Copper's better, but aluminum is thick enough. It's good enough to carry the current we need.
So I have a question. So these basically the square pegs in the round holes that are through plated
Yeah.
on the board. How thick is the through plating and all that?
The board plating is 70 micrometers.
Is that, do you know that it's that thick also on the through hole?
It's half that thickness on the through hole. Like the whole size is designed to make it like press fit perfectly, basically. So there's like some resistance enough to have a tight contact and not too tight, so it bends the board.
You have access to like a Hioki probe or like a 4-point resistance tester to validate this joint?
And the data sheet says it could do 160.
Okay.
And it's the same connector on the fuse tester last year. We ran like 100 amps for 30 seconds. It did not at all.
Okay, it would be valuable to be able to validate all of your high voltage joints with like resistance measurement if you can.
Okay.
And then yeah, I was saying yesterday, aluminum voltage joints. Ideally, you want to nickel plate all the joints, but if you can't, should
it's surface prep.
Yeah, surface prep.
Okay. Yeah. And on the end of the segment, well, the cooling holes are not shown, but we have a small PCB here that has the DS18B20 temperature sensors mounted. Those are required by rules, so they could monitor the pack temperature with the e-meter. There are two of them because the rule says the sensors must be located on the hottest part of the pack. So depending on which one, depending on which direction the water flows, these two will be like one will be at the coldest location, the other one will be at the hottest. So yeah, it's more flexible for the cooling setup.
Do you have any access to the BMS thermistors? Do you have any access to the BMS thermometers that are that information?
Yeah, the thermistor, there are traces on the PCB.
I mean, like for the readout, or is
yeah.
that just purely for the BMS use?
The BMS measures it and then we could read it from the BMS. That's just their, those ones, there's their.
Yeah, so
We
you
don't
can
get
verify
necessarily
though
do
that you're actually getting the hottest part. I guess that was sort of why. Since you have a whole raft of sensors, you can just verify that you really are getting the hottest ones.
Yeah. And for the actual cells constructions, so there's the cold plate. The cold plate has slots for the fins to go through. The fins are 1 millimeter thick, the slots are 1.5, and I believe they're 4 millimeters deep, something like that. So the max tilt angle is limited. So, and that's very important for manufacturing steps because we have like a jig which makes the fins self-align when we push it down. And then between the cells, we have the cell spacers. There are 3D printed plastic that are just like glued onto the whole plate. They are 2 alignment pins below it. So those will make sure the cells, the spacing between the cells are what we designed to be, so that they don't like short. And yes, then there's the aluminum nitride fins that helps cooling. And there's also a aluminum nitride aisle that sits between the cell and the cold plate to make them electrically insulated and maintain a high thermal conductivity.
How deep are the tile grooves?
There are no tile grooves. They're just there.
Oh, it's on flat surface.
Yeah, it's a flat surface. It's for like just better manufacturability.
And you already made a prototype of with all these features?
Yeah. Yeah, so here's the prototype. The manufacturing step is first we will use some sort of glue, which in this case is JB Weld, to glue the cell spacers onto the cold plate. And then, okay, it's hard to see, but there is thermal compound below this, the ceramic tiles. We basically just use like the die-cast to glue the tiles to the cold plate. And after that, we assemble the walls, we put in the fins, and we drop this fin tool on top. So, and this thing has like a pyramid structure below it. So when the fin is tilted, and when the thing comes down, it's gonna just straighten up the fins. It works like. And then we could fill the whole thing with the correct amount of epoxy, put in the cells and put it in the PCBs, and then we're done.
So is there anything that thermally connects the fins to the case? Or they just drop into the slots and?
The whole thing is filled with the die-cast. So.
So you just have your aluminum nitride fins and are just floating?
Well, those slots are filled with the die-cast before the fins are put in, so that'll.
So you put die-cast in there before you put the fins in?
Yeah.
Okay. Because the die-cast isn't gonna flow unless you get it really hot. I mean, you get it hot, but then it cures too quick. So. But it doesn't flow.
Yeah, so those like fin slots, they will be filled with die-cast before the fins are put in. So when we put in the fins, it will like push out the die-cast, and then that
will help.
That will guarantee a good contact.
But this one is with JB Weld, not die-cast.
The JB Weld is just for the cell
Spacers.
spacers, not the fin. The fins
That
are
is die-cast. I guess the only thing is like when after you mix this die cast, it's like very liquidy for like
Yeah.
a couple of minutes. Then after like 30 minutes, it starts to get a little bit hard. So with like a full module, I guess I'd be concerned about how fast you can put all
Yeah.
the fins in.
The reason these fins, they're done row by row.
Okay.
So, well, there's some manufacturing problems with this because these fins are 0.5 millimeters thick instead of 1, so they tilt more, and they tilt too much, so the jig just doesn't work. So what we did is we basically put 1 rows of fin and make them straight by hand, and before they fall, we quickly just put the jig on there, and then we wait for like 2 hours for those 1 row to cure, and just do like row by row.
I mean, I like how you guys are trying to prototype this out, and I mean, this is the right way to do it.
Yeah.
Right, it's really well thought out.
Yeah. So that's the manufacturing process. There's no like reflow soldering needed, so the bus bars won't be contaminated. And also, since with the help of the cell spacers, the cells will be at a perfectly flat surface, and then the PCB will just sit right on the cells, so the cells will withstand the force when the wire bond machine pushes down. And that thing has no problems being bonded.
So where you're doing this assembly, what's the cleanliness requirements?
The cleanliness is we just wear gloves so the oil on the hand doesn't contaminate.
Yeah.
And then before the bonding happens, we just wipe the whole thing with IPA.
At the facility, they also have like a laser cleaning machine, and we've limit tested that to some capacity with like epoxy on the bonding surface, and it still like for the most part worked. So I think there's quite a lot of robustness in the bonding.
Yeah, I actually I wasn't targeting the bonding. My industry's very used to what we call FOD, foreign object debris. When I see a manufacturing, I've got a device here that needs to not have any random material of any sort end up there. Some solder ball, some spalling from a screw that got fastened and it falls in there and you don't see it. And so I like doing this kind of work in a clean room type environment. And you don't necessarily have to have a clean room to do it, but you can create a manufacturing space that is clean.
Yeah.
So that in
Laminar flow
addition
bench
to
or something
cleaning
like
for
that.
the films and all of that, you also are controlling all the debris that could be in there, including things falling from the ceiling and all that kind of stuff. Think about cleanliness so that there's not a surprise.
Okay.
I mean, when we do our high voltage battery assembly, we have clean rooms for laser welding side of it, where we control. This stuff, we just make sure your area is
Clean.
Yeah. Right, that's really, you don't need a full up.
Yeah, you don't need a clean room, but
You
it
just
needs to be
careful when you do it. Yeah.
consciously clean. Not
Have a guy
just
across
on
the
the
room with
bench.
an angle grinder.
Have you ordered the 1 millimeter fins?
No, but I got a quote. They're like $300 for the whole thing.
Okay. What's their lead time? Is it the same company, the Shenzhen company?
No, I just find something on Alibaba.
Pre-cut to your dimensions.
Yeah.
Okay.
Because somehow our dimensions, they just happen to be a industrial standard, and they just have the molds for it.
Okay.
So we're lucky, yeah.
So you're gonna test the 1 millimeter out prototype as well?
Probably not a whole prototype. I'll just see if it fits nicely.
Yeah, because the gap between the cells is gonna be tight.
I increased the gap to accommodate that.
Okay.
I increased it by 1 millimeter. So it's 23 instead of 22. And for the wiring inside the tractive battery, it's very similar to GR24. So the 5 segments, they're in series, they're connected with the orange high voltage wires. And to connect it to the control circuits, that's inside the E-tray, is mounted above the battery pack. There's like a hole here. And then the wire could just like go through the hole and be bolted onto a bus bar. Yeah. So, and for the output of the battery pack, we are using the bigger amphenol ones because they need to connect to the motor controller, which uses the same connector. Their minimum wire cross section is 25 millimeters squared, but those are 16. So we kind of have to use this unnecessarily big connector because they need to fit. And inside the E-tray, we have the battery control unit, which is the big circuit board. We have the isolation relays that sits between the battery pack and whatever's outside. So when the car is off, the battery is completely disconnected, both terminals. And then there's a 200 watt DC converter that powers the low voltage circuits from the tractive battery. And that round thing is the UV signal connector for controls. And on the left side, well, it's not really the left side. That side is towards the rear of the car. We have this big thing, which is the e-meter. It's a rules required component that makes sure we don't exceed the power limit of 80 kilowatts. That's the main fuse back there. It's much smaller than last year because it's just 50 amps rated. Last year is also 50 amps, but just found a smaller one. And to support these super long bus bars to stop them from flopping around and shorting, we have these 3D printed bus bar supports. And yeah, last we have this HVA 1200 to connect to the manual service disconnect. That's located right below the firewall because there's a rules requirement. That thing needs to be at least 350 millimeters from ground. And the tractive battery is like very, very flat. So if we don't extend that, it won't pass spec. Yeah.
Are any of the components in this view installed with threaded fasteners?
Pretty much everything. There are mounting holes for that. Those are threaded fasteners. Yeah,
Are they
basically
threaded
they're
through
all threaded.
holes? Are they threaded through holes?
There will be a fiberglass insulation on top of this. Actually, does it have to be? Probably not.
What I'm worried about is every once in a while you get some spalling off of threaded fastener, and then you've got a small piece of conductive metal that's bouncing around and floating inside your compartment.
Oh,
This is sheet metal.
yeah, it's sheet metal. It hasn't been converted to sheet metal yet, but shouldn't be too hard.
So we, in general, for a lot of things, we try to avoid threaded through holes. Just so that if there is any spalling, it can't fall out the bottom, or look for alternative mounting techniques. So just be sensitive back to things that generate quad.
I guess we could use nylon bolts.
Just have studs coming out.
Oh, yeah.
I don't think these holes are threaded.
Yeah, the holes aren't threaded. It's just the bolt is metal. Ideally,
It's not a threaded it's not a threaded through hole screw.
They have a nut on the bottom, right?
Yeah, there's a nut on the bottom.
So it is a threaded fastener with a nut on the bottom.
Yeah, those don't tend to spall like the
We had
screws.
we had some nuts go loose in a battery and short the whole thing out. So just make sure they're positively captured.
Yeah, they're lock nuts, so luckily they shouldn't get loose.
That's what Bosch told us. So just be careful.
Murphy's Law says it shorts exactly at the worst
You're
possible.
on a track
time.
that thing short of that. With Brad, so just be careful when you're building it.
Yeah, okay.
All this.
We have this fiberglass cover on top. Those will be covered after the wires are connected. So
Where's your inlet or cooling plate holes?
they're like down there. I
Okay.
don't think they're at it yet.
Okay.
Because that's not the most up to date model. The general size is correct, but the mounting holes aren't. It's not most up to date because I don't know how to use SolidWorks, so I made this in Fusion.
Okay, just as long as you're aware.
I guess I would just be concerned about like mounting, like for your pre-charge resist, or essentially all of your high voltage components that are directly screwed into the sheet metal.
Yeah.
Like they're pretty close to the metal. As it, like, for example, the BCU fuse holder, like
Yeah.
those tabs are kind of flexible. If someone accidentally presses on it and then doesn't notice, and you put a
The connector that plugs onto that thing is insulated. So once the connector is plugged in, you could just push it down and then it's still fine.
I think
it's
you need
insulated.
to make sure that you keep a very large clearance between your high voltage stuff and any grounded
Stood off a little bit.
stuff.
Okay.
Yeah, you do. Yeah, you can stand it up.
Yeah.
And same with like your battery B plus B minus pass throughs, like those lugs.
Those,
Are they very close to the sheet metal?
Yeah.
Yeah, right. Bottom.
I guess I could put like a plastic ring around this.
Yeah, like a floor.
Yeah.
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 Why not just have a fiberglass panel on the entire bottom of it?
Because that'll raise the total height. And
Won't that interfere with anything? Say, for example, you could have fiberglass on everything besides, say, the airs. That's it. So the airs are the same height. And then everything else is relatively flat, so.
sure, that'll work. Okay.
MSD bus bars, are they gonna have a plastic insulator between
MSD bus bars?
where the connector is?
Yeah, I'll put like a T-shaped thing. There's two holes on top that just goes in there, so they can't squish.
Okay. I guess just the outlet ports, the bottom SLP, the bottom slipper connector.
Yeah, that one.
The nut seems maybe a bit hard to access.
The
bus bar.
Oh yeah,
Are they stacked for a reason, like vertically?
they're stacked, so the wires going into the motor controller on that side could just be like straight.
Okay.
And there would be like two 90-degree plugs that just does that.
Same with the discharge resistor that's mounted on the vertical wall. That seems also maybe challenging to mount, especially if bus bars are there, to unmount.
I think the mounting sequence is we mount the discharge resistors first,
Yeah.
and then we could mount the bottom connector, because we could just like screwdriver and bolt like that, and then we mount these two, and then we mount the bus bars and yeah.
Okay. I think it would be also worth putting in CAD all of your low current wires. Just to get the routing.
Yeah,
figured
sure.
out, and how to secure those wires so they're bouncing around.
Okay. Sure. Yeah, and that's it for the battery pack. For the custom inverter,
Well, so just for a thought.
Yeah.
And this is maybe more of an Alex kind of question, but do you have any significant open design decisions for this whole TBC? Doesn't seem like it.
but what do you mean by open design decision?
Things you're showing us a design, there's a few tweaks we're talking about it. In general, is it all design?
I think for the most part, at least electrically, I think it's mostly designed. I think Owen can you have anything else to say to that? I think it's mostly designed for the most part. For the tractor battery container itself, Thomas will be going over that, the physical mounting of that and all that. Thomas will be going over that in the next section.
Fits.
Yes, yeah.
Because where I wanted to go is, this is looking really good approach, hands-on. You've got a schedule of 3/17 to have the TBC finished. Have you guys ever held what you would consider to be a schedule integration meeting?
Not intensively.
So the reason I would suggest it is everybody brings all their detailed schedules. You make sure everybody lines up, but you also talk about, well, what could you do? If you went with the batteries that you could get in 2 weeks, what's the earliest date you could have a TBC built? Because if you could have a TBC built in January, or by the end of January, I'll bet you there's 3 other teams in this room that would say, bring it over. I can run a cooling test like I've never been able to do before. I can do a fit test mounting series of tests that I've never been able to do before. There's probably somebody else in the room that would say, you've got it? Ooh, we can use it. Almost to where they're like, you're going, well, do I get to test it? Maybe I need to build 2.
Okay.
That kind of schedule, and not just looking at what they told you is the drop dead to make it all fit, but where you ask yourself, how fast would you build a TBC?
Assuming Hess Mechatronics has room for us to use a wire bond machine, the whole assembly process should take about 3 days for the segments. And then maybe another 3 days to assemble those and put them into the battery pack. So the whole process ideally would take a week.
So my throwing out dates are not crazy.
Yeah.
Is what I'm hearing. And so this comes back to how you're managing the program to deal with your biggest risk, seems to be time and surprises. And these guys seem to be doing a phenomenal job bringing it all together. When they do a full pack, they might get some surprises. Hopefully not. Hopefully you thought of everything. If you've got the opportunity to pull that schedule in 2 months and start to do some integration and testing that you've never had a chance to do, I'd seriously consider it.
Okay.
You bet.
There's like one thing I could think about that makes the manufacturing difficult is you can probably see the test segment is short, and that jig could fit in a 3D printer, so I could print it, but the actual segment is 2 times longer and it doesn't fit. So yeah, we need to figure that out.
Yeah. Okay, that's not bad though. I mean, you're really on top of this. You're taking last year's challenges, make use of it. It's a key component with lots of impacts on a lot of other people. So there's gonna be motor guys that are gonna wanna get it. I mean, like I said, if you had it and said it's available, everybody in this room would be taking it from you and you wouldn't get a chance to test it yourself because they'd be doing all these other integrated tests with it. Drivetrain guys would say, hey, I want it. You can't have it back. I mean, I'm serious. It could open up some opportunities to integrate early and get some real data that could be real eye-opening. Not to mention how the judges might like it, just for yourselves.
Sounds good. Thank you for the suggestion.
Thank you. Good. And yeah, we're even though we are using one motor and we have a DTI, we're still trying to make it crescent inverter. The reason for that is first on the cost report, the inverter is cost by watts. And since the DTI has more than double the current we need, that thing costs like $10,000 extra on the cost report. So having a inverter that's spec to the motor will reduce cost support numbers and help improve our cost score by a lot. Also, since the DTI H500 is a pretty old product, it's not very efficient because it uses IGBT transistors. They're slow. So according to my calculations, using what we get from our sponsor, SemiQ, they make silicon carbide transistors. We could improve the average efficiency by almost 3%. And that reduces the heat generation by 30%. So yeah, it's quite a big improvement. And also, since the switching frequency is improved, the ripple current that goes to the motor will reduce, so the motor will run more efficiently. And then it's also a benefit from a higher speed transistors is those blue things, they're the decoupling capacitors on the high voltage. And for the DTI motor controller, since it's slower and there's more rubber current, those things are like that big. And with all that space, first the weight is reduced, and also I'm available to add this voltage clamp circuit, which basically solves the problem when the driver is braking and the car is regenerating power, and then the shutdown circuit trips. So that regen power will have nowhere to go except to just accumulate inside the capacitors, and then the voltage is going to go up and eventually blow up those capacitors. So that circuit will dissipate the power into heat. And then at the same time, it will notify the motor controller that something is very wrong, and it will turn off the transistors to stop that. So it's a very good safety feature. It's not been designed yet, but there's space for it. For the general structure, it's mechanically compatible with the current DTI motor controller. It's the same size, same mounting holes. Weight is about 1 kilogram less. Yeah. And inside we have the control board, which has the microcontroller that runs the control logic. And then it communicates through digital signal through these 3 separate gate driver boards. They basically just makes the signal larger to drive these huge transistor modules. Yeah. And this thing is water cooled. It could be air cooled if you want to, but that'll increase the weight because we need a bigger heatsink for that. Yeah. Yeah, and it uses the same connectors for both high voltage and low voltage to the DTI, so it's a drop-in replacement. Oh, and one thing to mention is that power board down there, it's a PCB and there's 240 amps running through it, so the copper thickness on that is 8 ounce per square foot, and that's 8 times thicker than a normal PCB. So that board is it's gonna be quite expensive, but.
What's the source of the cooling?
Water cooled.
No, but I mean, what's you building it, you buying it?
We're building our own cooling.
We're gonna see some of that design here?
I don't think that's been designed yet. I mean, it's just 500 watts in this big surface area, so it's not that hard.
Not tough. It's just things that are not tough that leak when they leak is a problem.
Yeah, I guess as a backup, if it has to go air cooled. Do you have a contingency for that?
If it has to go air cooled, it'll just be taller and has a fan.
Okay.
And heavier, but it'll still work. Because the DTI, it also has an air cooled version that's less powerful, but it's still enough for us. It does like 300 amps instead of 500, but yeah.
Is there a lead time that you're working with here on the getting this GR inverter? Is it?
The lead time?
Yeah.
Well, the design is close to complete. I could finish this in a month, I guess.
Okay. But is there any of the suppliers that you're gonna be relying on, they have a long lead time that you're gonna have to deal with?
Most of the parts are already readily available. The lead
Okay.
time on the PCBs is 1 to 2 weeks.
Okay. Even with the custom high copper.
Yeah, without the thick copper is 1 week.
Okay. Yeah. So you're the whole, you still need to design it and finish it, tape out.
Yeah.
And then go get it built.
Yeah.
Does anyone work on the enclosure for this?
Thomas. I mean, it'll be a sheet metal thing that wraps around.
Yeah, that's what we said last year.
But now we have like triple the time.
Yeah, so it should be.
Yeah.
It's not working.
Yeah. Yeah, and the motor controller will mount on the left side of the PVC. It fits pretty nicely with the E-tray. And by the way, the motor is like down there, so the lengths of the high noise switching wires will be minimized. For the battery management system, GR25, we have several problems, including high failure rate. It's not really failure, just soldering problems, because half of the board that we assembled just didn't work on the first try. We have to resolder a bunch of stuff. I think the cause is mostly we used to mount it on the side of the segment, so it has to be like long and thin. And to make it fit, we have to put small components both on the top and bottom, and to connect them, there's a via that goes from the top pad to the bottom pad. So when the manufacturers put this into the reflow, the solder just flows through the via. So there's not enough solder for the top components, and that cause problems. And also, another reason is the GR25 thermistor locations aren't really optimized. So there are 28 thermistors per board, and that's why we need so many components. And yeah, there are 4 discrete 8-channel analog to digital converters reading those 28 thermistors. Yeah, and also the temperature readouts are quite slow. That's because those ADCs are controlled by a 8-bit microcontroller running at 1 megahertz. It's slow because we need to keep the power consumption low, so the BMS chip doesn't heat up too much. And to fix those problems, we moved the BMS board to the top of the segment where there's more room, so we could have a shorter but wider board. So all those components, all those thermistors, they fit nicely here instead of having being without needing to be on the bottom. And also we are replacing the 8-bit microcontroller with a 32-bit one at 16 megahertz. It's made at a better process. They draw the same amount of power, but that thing is like 64 times faster. So the thermistor readouts shouldn't take as long. It used to take like 20 milliseconds. Now it's gonna take less. And also, since our pack is smaller, it's 2P instead of 3P, we could reduce the thermistor to 14. So you can see this board, this half is the BMS circuit, and those half are the battery temperature monitor. That's the microcontroller.
You know, in the interest of sounding like a broken record on purpose, this chart again highlights that we probably as a team don't spend enough time focusing on manufacturability and what can go wrong. I'm surprised that we must have missed last year that we had a design that had vias trying to mount something on both sides. I mean, really? We should have fought that and said, no. You're gonna put that in a reflow, it ain't gonna work. Should have known that, should have caught it, but we tend to focus on the performance and not enough on these details of how to build something.
Yeah.
I'm just gonna put a hard stop at 1 for lunch because our lunch is here. I don't want to get too cold. So you just Owen knows and everyone else knows.
Okay. What's the plan?
Yeah, 7 minutes.
Oh, okay.
So when do you think you can prototype and validate this, the function of this?
The BMS board is already made.
Okay.
The problem is, the side of the test segment is not cut out. So basically the base, the cold plate is like bigger. So that doesn't fit. So I had to extend it with wires, but it will be tested soon.
So okay, back to the inverter thing. Is the fallback still to use the DTI?
Yeah.
And it fits in that same
Yeah.
space.
And the reason I have those 2 bus bars extending into nowhere is making it the same length as the DDI.
And how would you deal, as a fallback, how do you deal with the voltage clamping?
You just run less speed. So the voltage rise is like slower, and then the software has enough time to detect that. Because my solution is hardware. It's like Microsoft. And I think that's my last slide. No, it's not my last slide. So for the battery controller unit, that's the thing that has all the circuits related to high voltage to pass rules and also make the car safe. Last year we had some problems. The biggest one is the BSPD circuit. That's the thing that measures battery current, sends it to the ECU, and compare that with the driver's brake command. And if the driver is braking super hard and also there's current flowing to the motor at the same time, it shuts the car down. The failure reason is that circuit cannot detect a short to power failure on the current sensor. And that is addressed by adding a Zener diode. So it could detect whether there's current going through the Zener diode. And if there, and by measuring that current, it could determine whether it's shorted to power supply. And then, yeah, the relay driver on the GR25 board exploded. That's because I did not have a freewheeling diode, thinking the relay has an integrated driver, so it just should behave like a resistor, but it doesn't. So I just added that back and it worked. Oh, and also the integrated driver inside the relay has very large capacitance. So I had to add more gate capacitance to the MOSFET that drives it. So it switches slower so that the peak power doesn't blow up the MOSFET.
How did we learn about the GR25 problems?
Well, I just turned it on and then the MOSFET just exploded.
So the first time we powered on.
Yeah.
Got it.
Harsh blows. We've all been there, buddy.
Got it.
And then since we merged the E-tray in not the E-tray, we merged the junction box into the E-tray. We need to move the circuits in there as well. So the accumulator control unit, not the battery control unit, is extended. So it now also has the discharge relay here integrated, and also some circuits that's behind this thing, like there, that controls the ready to move light. And lastly, the high voltage DCC converter. The GR25 one, it kind of worked, but I only got 100 watts out of it. And that's because the transformer is like asymmetric. And because to get the power density I need, I decided to go for a planar transformer. And that thing is, since it's so thin, it's extremely difficult to get both coils have the same coupling ratio, and that made more current run through one half of the two half-wave rectifiers. So if I run the full power through it, that one half will blow up. It did. And I just throttled power to make it work. And also, the synchronous rectifier controller is not very accurate, and that's solved by using a better, more expensive chip that has 1 millivolt accuracy instead of 7. And also, last year, the feedback loop is implemented with software, so it's slow. And also, it's a high voltage circuit where there's a big half bridge which requires gate drive. So the switching node surface area is like quite large. That generates a lot of EMI. So it has to use very slow low pass filters to get the signal I want. And that makes this feedback loop slow. And that is solved by using that better topology, called push-pull resonant. What it does is basically, instead of having a half bridge, it just moves both transistors to the bottom side. So they reference to ground. It reduces noise. Yeah, and also I developed a Sigma Delta controller for it. And you can see the Sigma Delta controller is goated. First, at max power, we're basically when the low voltage battery voltage is lower than the set voltage, the circuit the circuit behaves like a current source, like it charges linearly. And then once it reaches the set max GOV battery voltage, this Sigma Delta controller basically reacts to load transient super quickly. And you can see here I have like a load jump from 0.4 amps to 4 amps, and there's no overshoots or undershoots. So it's like super stable. Yeah.
Is that simulation or?
Yeah, this is simulation.
All right, I think we'll call
Yeah,
it for lunch.
that's
Sorry,
right.
Owen, but
This is my last slide anyway.
Oh, perfect, look at that. All right, thank you, everyone. Yes, can go eat lunch outside. We have Costco pizza today, so yeah, and then team leads, you can go after.
Oh, okay. Yeah, that's what I have to say about that.
Okay.
So you use half hour. You're not industry professional.
Well, just like. Wait, what do you mean? What do you mean that regions?
We should just make this self-users.
No, but,
Yeah, really.
So when you get the core.
The board is mostly the same, so I could just test the whole board with like the second top fixes on there. Yeah. I already tested the BSCD and the relay driver part. It's mostly just code. That's
So it's just like shocking. So when is it all integrated?
We'll do that right after the battery.
So we get you to do the battery, you want to do that?
Yeah.
I mean, you look like you're in a great position to really help the team nail some things through. And live with surprises. I mean, because part of the GR25, it must have happened. Build a new one, make it to a design tweak. So this year, there's so many. Don't trust that it's all going to work. Build it already.
I think it was put it on a chair. Me and Steven stand up here. Yeah, I think that was. That was not the aerodynamic fault. That was. So, and I put it. The same thing this year. Yeah, I'll say. That'd be fun. Yeah. It's like, put it on the front of the path and see what we have. Yes, yeah. You found it. Starting out with the stuff. So then, and then, yeah. But it's like, it's. So then he's also going to design code for 5 years. During this making competition. So it's my slot size from without any. And then not like
He's very open. Extended his stay here for another day, for tomorrow. So you get back to me, Curtis, and that's tomorrow. So I think you want to talk to you guys today. Yeah, he was guy, well, he's, you know, behind horses, was another person. Yeah, that's the thing.
Guy talking about like. Settle.
There's a very small one. Yeah, you can run it out for 5 miles per hour. Same last year, same code.
We use slow. So, like those air guys, it's actually. Like our rapid transition, right? So the flow is torturous going through. I was asking what the Start out, I don't think it's worth it. No, that's maybe 16. What's up the business? GR26 CDR. And it's capacity increase. But yeah, it's a digital. He's very good at talking. Yeah, like when you were showing the cutaway up to 30 days. We're approved at least. No, 26. It's a lot of.
I just like that it's the first time.
What are you guys trying to pile in there?
Go fast. Like you were. Okay. You can tell me that's not. Yeah. Oh,
They're supposed to like recognize.
Unfortunately, our all of it. Like, I don't see if you guys still do.
time it always went fast since we got the, That's why.
I cut it out.
We drive by. I'm sure. Our team to go to. Oh, Caltech.
They're really good.
Chris Corbett, I don't know.
They don't want money fine.
Really?
Yeah.
Where are you gonna run into him?
Yeah, they're team is brand new.
I don't know what you look like.
I don't think they run far.
Yeah, you should tell them, let us do some people needs are trying to do a calculation how bad.
Oh, we were drilling. Coals and coals. So like 6 a.m. I remember like zip tying the shut on the drill. That's how you get 4 hours. That's like 3 hours. That's like, yeah, just do correlation. For you, let's do a correlation that said that's all. Your diffuser length is such a horrible they make people count 60,000. You can have different types of parts. And it counts for each part for 60,000 parts. They were like, like not 60,000 pieces of stuff, like 60,000.
It's like a wheelbase.
Like there's 60,000 different shapes of probably going to be like each one next time. No, it's like in the inventory section. So like they're like
How would you be able to do us? But what you can do is you can run the system behind it, like, and then you can actually at least like CFD correlation. It's just like you got wait, that won't work. Like just speed it up and like smash it against one another. We don't expect. Slides from wait to get cooked about like
Oh, it's great.
Sadly, I cannot out loud. I'm gonna be gone by the time Jake's presenting.
Jake, are you real?
Wait, that's not real, bro. You're gonna have to talk about TCM stuff. What?
What the fuck do you mean? You're the one who made this.
You're the one who wrote the software
For what?
for TCM.
For the CAN controller? That's all I wrote.
Yeah, and that's the thing BK said he was gonna question me about.
Yeah.
Okay, I'm just gonna tell him to call you. Wait, him asking about software that he wrote is so diabolical.
Yeah, you're supposed to know it, Jake.
Yeah, I'll ask you about it.
Jake, as the new data lead, you're supposed to know it.
Ask Jake about it.
You're the Giga Chat. Have you seen the meme? If I can spell. Giga Chat. We are reading over. Giga Chat headphones. I did not buy them because of this. This is my second pair. The first pair blew up. Yes. I really like taking out the glass things. It's all my one.
My slides are out, so you can just see what's there.
My cups are glass jars. I'm not broke.
Well, you missed it. And it showed up as iPhone, and Alan was like, "Hey, iPhone." Oh, I'm
Like the only thing that I cannot have an explanation for is, I don't know. No.
Wait,
No.
that could be like a.
Ryan knows exactly. That design is not finalized. It was literally made yesterday, 2 days ago. Still. So that I I asked Ava, she said they're somewhere in the hat.
So.
That's why I want integration by parts. You know how it says woo? What was I saying? Maybe we should. Maybe this year. I don't remember integration by parts.
Thomas stuff.
I just feel like, oh, we always know you're talking about
I'm surprised. Bro, it was at the car. Alright, it was like. And it was like. Wait, it was fun.
We're not like tabs with phone.
You're not supposed to lie.
What's like phone? Mine's black orange.
No, he doesn't. He could dip the fly.
That's just mounted on the back of, attic. Where the fuck did you get gearbox from the attic? Because you have the welded plate, which was mounting to it.
No.
Well, I think what he's saying is just like, you acknowledge my thoughts.
Alright, guys, go back inside. I think we're getting ready.
Just have like a sec.
Ava, I told.
Especially if you lost.
It is for 2 hours. Long story short, Jeff scammed us out of.
Yeah, that's a long story. Scammed us out of everything.
Did you ever pay him? Yeah. Wait, like Nick, other Nick and me paid him, bro.
Yeah, I think that's true.
And because the attic is not really
Oh, yeah, no.
Oh, wait, no. No, it's fine. Yeah, okay.
Alright, so just now.
Pizza.
Oh, what? Yeah.
All right, we're gonna get started. Thomas is gonna present on high voltage systems integration. Now, Thomas is, he was planning to do his master's this year, but he got a job over the summer, so now he's working in the industry. But considering that he designed most of these components here, he's still gonna present on that, so.
Does that violate the rule that we can't have a professional engineer design?
No.
Yeah, bro, definitely not illegal.
So I'll go over a little bit of last year's accumulator container design. Last year it was called the accumulator, but this year it's been renamed to the tractive battery. So you'll see a little bit of both. But last year we had 2 layers of the battery modules. So the overall height was very tall. It was constructed with aluminum bent sheets. That's outsourced and laser cut. And then they're all bonded together. So there's like flanges that are on joints where you can put a bond in between. So it's quite a lengthy process for bonding. And we'll get into a little bit of that more later. And we're using this load-based mounting scheme. So in the rules, you can do mounting for the battery in the chassis 2 different ways. There's load-based and corner-based. So load-based allows you to put the mounts anywhere you want, but there's a certain requirement of like the number of mounts based on the mass of the battery. And then there's like a proof load. For corner-based, you're restricted in geometry. So your mounts have to be like one at every geometric corner of where your modules are. But the test load is a little bit less. So in theory, if you can hit that, it's much better. You can save a lot of mass because you're designing for much lower loads. In general, the loads that you're designing for the container are kind of outlined for you in the rules in SES. So you won't see a lot of FEA, I will say. It's more just like hitting rules and structural equivalency and calcs. So this is a picture, some pictures from our bonding process last year. So it was quite, it's like 12 hours straight, I think. And we were all like getting out of class and stuff, and we started at like 6 or 7 p.m. So it's kind of unfortunate, but it took a long time to surface prep everything, clean all the surfaces, like sand them down to give them a little grit, mix the epoxy. This epoxy, we have a pot life of around an hour, sometimes a little bit longer, sometimes a little bit shorter. And one of the times we mixed it, I don't exactly know what happened, but it started curing like very quickly, and it's very hot. So that was a little spooky, but it mostly all aligned fine. We're getting like within a couple millimeters on like each cell within the container. It's just a very lengthy process. I still have some epoxy on my clothes from this. Yeah, so that's one thing we wanted to change. This slide is actually taken from a slide that we made last year, reflecting on our accumulator. So this slide is, I just copy and pasted it. It's from like spring quarter last year. So these are some things that we wanted to change last year, moving forward. So accumulator mounting scheme, that's like referring to load-based and corner-based mounting. And we also had some issues with clearances inside. So you can see there's like some bolt heads sticking out. These are mainly alignment bolts, but we never actually put them in the like CAD assembly. So that we didn't like make clearances for them properly. And when we were sliding the modules in, we had a lot of issues with them like bumping on little bits of stuff. So that was, yeah, that was not a very smooth process. We also wanted to explore more on the bonding specifically because during the bonding process, well, it was very rushed. So we were doing it end of spring quarter, right before comp. And we did not have a lot of time for material or like mechanical testing on it. We had made a few test coupons. We were like trying to break them. And we could not break them in shear, but one time Tim hit it with a hammer very lightly and it just broke instantly. So then we were all very skeptical of bonding. So we were like, okay, maybe we can do this next year, but we need to have better control of your surface prep and like being able to measure whether or not it's actually viable. Because according to the structural equivalency, like the competition documentation, you could do bonding, but those are all like static calculations. There's no impact or dynamic evaluation of that. So that was kind of a concern. That was particularly a concern if we ran the car last year, but we didn't. But yeah. Yeah, I guess I went over those first two issues. The third one, in the past, many years ago, we've tried welding this. That's what most teams do. But we've had a lot of problems with control on like the walls bending in and stuff when the welds get hot and warp. So we've been trying to avoid that. That's kind of why we went to bonding last year. So we didn't have any thermal issues. And I think we are trying to do more welding this year, but so yeah, I guess welding is on the table for this year, but we have had lots of issues with it in the past. So yeah, the solution to most of last year's problems are trying to move to a fastened construction with rivets and also being a little bit more careful about the modeling, making sure there's clearances for everything. These are some good things that we did in the past that we'd like to preserve. So the aluminum sheet metal that was outsourced, they all came out very well. Actually, last year, this base plate, which was flat, 6061, was unbent, but it was warped when we got it. Like the middle was like a 1/4 inch out of the flatness plane. So that was a little bit worrying, but all of the bent 5052 parts were very good. Yeah. So this is a little picture top-down view of our 26 container. These are the very small mounts. So we have 8 of them around the corner. Primary function of the tractive battery container is to just hold the battery within the chassis. So that includes the mounting schemes, making sure you satisfy the rules and competition documentation. And also we want to protect the batteries from water ingress from the outside, and also potentially if there's a cooling leak on the inside, how to either egress the water or like otherwise protect the batteries. And then yeah, service and manufacturing, those are some of the problems we want to fix from last year. Mass is another consideration. because our container was so bulky and large last year, but not a top priority. Yeah, here are just some pictures of how the sheet metal is broken into pieces and assembled. We're about half the height of last year. I think center of mass of this and also the electronics tray and the inverter assembly is about 5 inches, or like 7 inches from the ground, 5 inches from the bottom of the accumulator here. I think last year we're about twice that. Yeah, one thing in the rules is that you can use rivets, but not open-ended ones. But McMaster has closed-ended top rivets, which we're planning to use. So this is a brief comparison of rivets over threaded fasteners. Just to say that rivets are a little bit smaller and a little bit stronger for equivalent performance. I will say that we have not used rivets a lot in the past for structure, so maybe a little bit of testing is needed there. But in principle, they will be better.
Can the same joints be swapped out for threaded fasteners if the rivets don't?
Well, yes, if we design for rivets, so they're all 1/4 inch, like clearance holes. And the rivets or the fasteners will be a little bit stronger for per each rivet. So if we design for the fasteners, we'll space them out more. But if we design for the rivets, they'll be closer. They can be swapped. I think the clearances are probably okay, but it will be tighter.
I was gonna ask clearance.
Oh, just a quick thing, like tear out and pull out are also part of the SES documentation that controls like the size of your flanges. That 120% is kind of our factor of safety on the strength of the joints. So basically, the sheet is saying just make sure whatever you use to join, it needs to be the same strength as a weld. That covers 50% of all the bonded lengths around your container. So we're meeting that. There is something to be said for a higher factor of safety than like 1.2. But to me, in general, like meeting the rules, as long as you meet them, it's like fine. I don't see that much benefit from going over what the requirement gives you.
Yeah, as long as there's not like a safety disaster kind of issue that it wants you to do higher.
Yeah.
What happens if one of these fails? Do we just
like a rivet would fall out or something?
Yeah.
That's a good point. So there is a minimum spacing between the rivets, and I think on most of the vertical joints, we have 1 extra rivet to meet that spacing. So there's 3 instead of 2. For the longer joints, I'm not sure, but that would be a good thing to think about. So
I don't know what numbers are typical in this industry, but in mine, 1.4 would have been about as low as we went. We would go to 1.15, but only if we were able to proof load test it with a realistic load. So you're getting close to where it better not be very critical.
But this load is assuming like 30 Gs or whatever of accumulative mass.
This is not loaded. There is no test load for the joints.
That's just like
It's just for weld equivalency.
you're saying you're 1.2x over the strength of a weld.
Yeah, of the weld.
Okay, so we don't really know what the factor of safety is relative to any real world loads.
Yeah.
In the box. Depending on how it's mounted and dynamic motions could be pretty low. You know, it begs the question, so do you trust the rules they gave you? Or are you gonna go and make sure you've got some sense for what your real loads look like, so you know what your own factor of safety is?
I usually trust the rules, but they do typically for Teslas, for other parts of the rules, they use 20 Gs vertical and 40 Gs lateral of the mass of the modules inside. So we could do a little analysis with those numbers, but I think those are kind of.
Well, if they were that conservative in how they developed this criteria, but you should know that. You should know for sure, not just trusting. Okay, but yeah, that's pretty conservative then.
So for our corner-based, or for the load-based, traditional load-based mounting, the baseline for test loads is always 15 kilonewtons, no matter what. So it's like in shear or tension. But with corner mounting, it's like one quarter of the mass of the battery at 20 or 40 Gs or something, which comes out to 5.3 kilonewtons. So we can design for a lower load. That's also based on the rules. And then we have our fasteners, or we have the mounts located. You can have two mounts on the same chassis tube. And then each mount needs to be within 50 millimeters of the nearest segment. So that kind of governs like how far away you can put a mount from a corner. Yeah.
Has there been SES feedback?
Yeah. So I think a couple of things were the fasteners should be not on the threads. They're concerned about that for, I think, the mounts and something else. I think that one is a partially threaded one that it's only the shoulder is like here and the threads are there. And I didn't want to get a longer one because it was like sticking out. I also didn't want to use traditional shoulder bolts because they're expensive. Like precision diameter. But yeah. And I think some of the mounts we got feedback that they're a little bit long, so the bending is high, but it's not a reject. It's like a check, and then the feedback is it would be wise to strengthen them. That's it.
So are you going to?
Yeah.
Yeah, I mean, I didn't realize we were changing the mounting techniques, and that's okay. I get nervous when I'm trusting the black box of the SAE guys, only because communication's hard. So if they fully understood your design, and whatever they dumped it into to take a look at it, as long as it had the kind of conservatism that you think it did, okay. But that sort of never replaces having your own analysis. So at least a hand calc on all of these and a factor of safety that you're comfortable with against what you believe are the worst case loads.
Good.
These mounts only have a single bolt that locates it to the container.
Yeah.
How do you guys feel about welding those mounts?
They're steel.
Yeah. Wait, what? Oh, wait, welding those to the accumulator?
No, to the chassis.
The chassis ones are steel. They're steel to steel.
No, I mean like.
There's like a locating hole. So like on this side of the mount, there's like a little hole, and then we can get a laser cut hole from VR3. You can like weld in a little pin.
You think it'd be good to like bond and bolt like the bracket?
Yeah, so actually the original plan was to bond it and one of the bond requirements on SES had like TPL in the wrong units. It was like in area instead of in length. I couldn't figure it out, so this is kind of for the sake of SES to put the bolt in there. So this has bolt equivalency, but we can do both.
Personally, I'd rather see both. Sooner or later, bonds age, get brittle, and they just fail. So I'm not surprised when I hear you're like, yeah, it's great, and then boom, you tap on it and it falls apart.
I have one quick rivet question. If you go with that, have you spec'd out a rivet in particular that you're looking at using?
There's it's the beefiest 1/4" rivet on McMaster, which
Okay. I'd maybe do a little more digging. We popped a couple hundred in that trailer build a few years back, and there is a meaningful gap in quality between rivets, mostly between the Home Depot ones and the ones we got from SB Fastener even. So I think they do have standards for this, and there is a whole rabbit hole you can go down to for different types of rivets, which might be worth looking into.
okay. Yeah, we'll do that.
Are you guys gonna do some testing on the strength of the rivets prior to putting them in? I feel like
Yeah, we
there's a
can.
good chance they could vibrate out or. Cause the biggest load case here is mostly vibration. Right?
Um,
It's also pretty
Okay.
easy
easy. What do you mean?
to buy rivets and then rivet together some plates and shake them.
What I actually thought you were gonna ask them about was just the entire test program, starting.
Oh, yeah, well,
Because this is sort of a new mounting technique, which means there's new modes of movement that you gotta worry about. And I just don't wanna trust some handbook from SAE that says, hey, this should be okay for this corner mounting. So I'd really like for us to understand. And if we're not gonna model it a great deal, then what's our test program look like? And I'd be okay with that too. That test program needs to include not just static loads, but something that's representative that informs you on any sort of quasi-static accelerations.
Okay, I haven't thought about testing at all. I guess vibrations we could do the truck bed thing, but for the mouse, I'm not sure.
To get the right mass.
You can put it on Kirk's tension thing. Like those, you'll be able to test the shearing, those bolts or how those perform in tension. The mounts are also pretty simple, so it shouldn't be that hard to get them.
Yeah. Yeah.
And I'm thinking about it, give some thought to the test, because the more I think about it, I'm like, yeah, but unless you've got the full up chassis, now you don't have the right boundary conditions that are representative of the real world, so you end up simulating that, and so I'm not sure how much value the integrated testing is gonna have, because you're not gonna get the same dynamic responses across the boundaries without having the whole chassis. And next thing you know, man, we need the chassis and we installed it, and that's pretty late in sequence of things. I just want to feel like doing something new. Don't want it to be a surprise. Don't want anything backing out. Don't want anything popping off. Don't want anything bending irrevocably along the way. So good, robust factors of safety and all of that should be fine.
Okay, this is a little extra note. So something we did change this year was a lot more spacing on the sides of the modules. That's also just to help with like inserting or like assembling. So it started as clearance for your fingers, but then when I was putting the rivets in, like they also stick out to that space. So I think it'll be a little bit smaller than intended, but it's mostly clear around there. Yeah.
Have you looked at GR24 CAM?
No.
I left like multiple inches of space there, and it was so very tight. Because the fasteners are very hard to fasten. Modules fasteners. You have to get a tool in there, you know, you have to like locate. Like to get the fastener out,
Oh.
you can't get the fastener out without using like a chopsticks or something. So I just look at that.
Just considering fastening into the segments from the bottom outside of the accumulator. If you like tap the cold plate, then you like safety wire them on the bottom.
Yeah.
I think these are designed with tabs on the inside, so you have to screw them.
You know, another random thought going through my head is, of all the load cases that the chassis guys are looking at and all the nodes that they're looking at, maybe ask them to make sure they look specifically close at the nodes where you're going to be mounting. Because again, it's new. I mean, we got the suspension, we're used to all of that. This we're not quite used to. So make sure that the stiffness in the area that this component cares about gets as much attention as we've given all the other components.
Yeah.
Are those like end plate things separate individual pieces that's what the rivets are for?
Yeah. Like the blue ones.
Yeah.
Yeah. Those are individual ones.
Do you think that's enough width tolerance for the modules to slide into?
This way.
Yeah.
It's about a 1/4 inch. I think that's what we had last year. Last year we had a 1/4 inch on all sides.
I think GR24, I mean, as well, it had like more than 1/2 inch each side. It's still okay. So this is different.
Yeah. Maybe when these were originally designed, we were a little bit more space constrained, but after yesterday's firewall presentation, I didn't know we had 3 inches of space up there.
Also, the finger gap, is that with the 8 high voltage gloves? You're in full PPE.
Yeah.
You have to both be able to install this in and take it out.
Yeah. That's a good point.
So all your fasteners that in the queue also needs to be, you have to consider the PPE that you're wearing. It's working.
It's 5.25 inch.
Okay. So let's bring me to my favorite part. Leak drainage system. This is not very fleshed out, but this is a kind of a concept. So the idea was if there's any internal cooling leak, maybe like one of the hoses popped a line or something, there'd be like water spraying around inside. The water would like gather in a puddle at the bottom, and there's kind of like there's like a little space at the bottom where there's nothing there, so because the modules are stood off from the floor. Now we could put little holes. Well, we could leave unfilled holes in the corners so that when you're driving around and the accumulator is accelerating, the puddles will be like pushed into the corners for drainage. But yeah, there's a few. I mean, yeah, so the holes, obviously, they're not good for rain test. So we probably need to work in something with like those shielded meshes or vents. So you don't get water into them, but yeah.
Are you not worried about stuff getting in, like dust?
Dust, I don't think so. I mean, I think there's gonna be dust in it anyways. But like all the modules are shielded on their own. Yeah.
Instead of, if you're worried about rain test for, and you have the holes like this, why not seal this up and have little holes on the bottom? Because you said that the segments aren't on the ground, right? So would it work if you just have little holes poked on the bottom instead?
Yeah. Yeah, I guess the only advantage of the corner ones is that when the thing is accelerating, like water gets pushed towards the corners on its own. But yeah, I think the bottom is probably a little bit safer for rain tests because they have like a ring that like sprays. Yeah.
Do you know the dimensions of that little corner area?
I think it's about a 1/4 inch. But yeah, I guess with this one, it can be filled in with like epoxy or it can be welded over. If we decide we don't like it, but yeah.
I feel like it's just very easy for, I mean, you don't have any bonding catted, and I don't really blame you for that. It seems very difficult to have something like that in, but it seems like it could very accidentally easily get filled up on its own accord by like extra bonding on the side or just stuff. But I just wanted to know if it, like, how big the area was, just to see if it's something to be concerned about.
Okay. So I don't know if that is big enough. I think we should size them for your flow rate and your cooling system. Like, I think you can do some calcs. Holes on the bottom.
I'm just sort of struggling to wrap my head around how I think about this. Is there a requirement for an internal leak drainage system?
I don't think so.
Because as somebody pointed out, dust, I mean, if there's a hole there, how do you feel about having a whole bunch of spiders that are living up inside your cavity and other things growing in there? And then I look at the rivets and the whole approach and how well is it gonna do in the rain test?
Oh, there is we will like silicon caulk over the
all
rest
the
of it.
rivets.
Yeah.
No, you create an ingress point that doesn't have some sort of flow control. I don't know. I worry about leaks a lot, as you could tell, but we've got a leak. Am I happy that we've added a hole into our electronics cavity? I don't really like having a hole into the electronics cavity.
Or maybe another thing is if you want to go this route, could you put some kind of like one way valve or something right before the leak so that stuff can't go inside?
Yeah.
Okay.
Yeah, I don't know how efficient that will be, but I think you gotta do something like that. Just because you don't wanna see a whole bunch of moisture, dew migration inside, and then who knows what's growing inside your cavity.
Or another thing too is, do you need to have an egress point? At like what point is having a leak in the system so detrimental? Like, could you not just check if there was a leak and then try and at least clamp the water flow to try and mitigate it? And then if you have a leak, isn't that a sign that you should probably stop?
Well, yeah, it's just the drain while you're driving.
There will be
Along the
sensors.
lines of what he's saying, what went through my head before is you put a water bucket in there, because if we got water inside any of our electronics, we probably should just shut down. Cause there shouldn't be water in there.
Well, yeah, that is, yeah.
So if you want to try to get rid of the water, just shut things down if we suddenly detect a leak. So do a leak detection.
There is,
I think we have
leak
designs for that.
detection in the battery control. Yeah.
Has one.
Yes, yes.
Mounted on the floor of this.
Yeah. It would be like a PCB with exposed wires that surrounds the hose.
Okay.
And
So-
then when it detects the leak, it's gonna turn off the pump, and the car will keep running until it detects a short.
Okay. Well, this keeps coming back to whether or not you really need this leak drainage system. It sounds debatable.
We need your last slide, right? Yeah. Any other questions for Thomas?
Well, where's your vent?
It's like, here.
Okay. Like that's. I think if you have holes, it's like not as big of a concern, but like when batteries go into thermal runaway, the amount of gas they create is like astonishingly large. Pressure builds up really quickly. Like that's how things explode. Yeah. But not think of the vent as like an afterthought. It's like these cells can generate a lot of heat.
Is there a requirement for the vent size? Or
There's requirements for a vent, but I don't think there's a vent size.
Use a burst disc.
Yeah, you need a burst disc.
Yeah, so I would just look
You'd have a
into,
bunch of burst discs, and then that way you don't have the opening until you actually need it.
you know,
Thank you, Thomas. Any other questions for Thomas or? All right, not that I think we have the local edition next.
Hello, I'm Vin, and so we'll be just going over the general low voltage architecture. We'll go in depth into electronic packaging and wire harnessing. We won't go over sensors, that was a mistake. And we'll also go into just like manufacturing stuff. So as a review for GR25, in terms of integration, we found that during competition, there are numerous components that were quite difficult to mount and also account for. So during competition, we actually some of these enclosures did not end up getting mounted. Although we could have done it, it would have been a very fast hotfix. We would have preferred if we had actually good mounting plans and also So, and our other thing was the telecommunications module had a custom 3D printed enclosure. And it was manufactured very poorly. It quite shattered during assembly. So ingress was very much possible. And then pretty much all of the sensors were not mounted, and in the camera as well. In terms of wire harness, this was given as a feedback by the design judges. There was a lack of shielding around critical signal wires, specifically for the twisted CAN pairs. There was exposed wiring that was just exposed from even like around corners that where sheathing were meeting. There was a general complexity in power and grounding. And there was a lack of CAD integration, so there were numerous issues with MechTech with the wire harness interfering with the cockpit templates during and such. And then in terms of components, we did have some mishaps, but we won't go over them because we feel that these components have been resolved, and that most of these issues have come from just a very rushed timeline as we were all building these components like a few days before competition. So we don't consider this as a major point of concern. Is there any questions? Okay. So in terms of what we want to do to improve on those issues is that for the general low voltage electrical system, we want to have a proactive integration within some CAD assembly, preferably the master assembly. We also want to try to simplify the general architecture by locating and consolidating components together so we could simplify the wire harness. We want to simplify the wire harness so we could also improve manufacturing times. I forgot to mention that the wire harness took quite a very long time to manufacture because of numerous connectors. We also just want to improve shielding and also provide clear documentation to also enable precise manufacturing process. And then for data acquisition, I won't be covering it. It'll be later, but we also want to provide clear mounting schemes into sensors. Okay. So for GR25, this was the general overall architecture of the electrical system. The way I counted the separated components was these components are things that we need to mount individually. So I counted 22. So there are components like the fuse box and the DC-DC converter. They were both separated. The battery was also separated. Yeah, like does anyone have questions about this diagram? Yeah, it's kind of very comprehensive. Anyway, and then for GR26, I'll go over why certain components have been consolidated together, but the main changes is we created two master enclosures called the penthouse and the attic, in which the penthouse combines the ECU and the telemetry compute module, and also just general changes in power electronics to improve the general routing of power. And then the attic contains the main GLV battery, the fan and pump controllers, the rear right panel, and the DC-DC converter. And this change decreases the amount of components to 13. So we have decreased the amount of components that we would theoretically need to mount. Okay, so this is the general CAD overview of our low voltage system. So the penthouse is mounted here, above the cockpit, and the attic is placed here in the rear right, where the rear right panel is. I'll again go over why these locations were placed. We also have the main wiring harness mapped out. There's two of them. The reason why there's two instead of one master harness is because we have a firewall bulkhead connector. So it separates the wire harness as a front section and a rear section. And then extraneous components are not modeled because they're not done. Okay, so the main issue that arose with consolidating components together was in GR25 and GR24 we used Deutsch DTM DTM enclosures. They were just standard off-the-shelf parts that we would use to house our PCBs come together. They were rated to IP67, and they had a max pin count of 24 pins. So these were great because they just worked. They prevented any ingress. But for our main design goals, we want to unify more components together. So for GR26, we are trying to do 3D printed enclosures. Our target IP is IP65, based on the rule book that says, oh, the attractive battery components should be IP65 rated. But in the main point of concern for ingress that I have set was just a rain test, which was just a water spray that sprays from above and covers it, sprays for 2 minutes, and then the water spray stops, and then the vehicle's observed for 2 minutes and then see if everything's fine. So the general benefit is that by consolidating and using custom enclosures, we would decrease the connector count, the main connectors, and then we would have a more simplified harness topology at the cost of the general concern for how we're going to be manufacturing these custom enclosures and how well ingress protected they would be. Yeah.
For the previous enclosures, how did they seal for the rain test? I remember them just being plastic boxes.
They have rubber grommets or gasketing around the outside, and also the DTM connectors also have just built-in rubber grommets inside.
Didn't we cut off the bottom of them and then tape on some extra ones? I remember Sean working on that.
That was in 2024. That was like a shot.
But the standard boxes are rated for IP67.
So if you guys wanted to make an enclosure, you have to include that rubber grommet?
Yes. Yeah.
You guys have plans to rain test the custom enclosures?
Yes. Ideally, well, there's also other factors that would be pretty important, such as like vibration and thermal characteristics, but I personally don't know how to do that. But for rain test, we're just planning on just spraying it with water and just recreating the rain test, spray it for 2 minutes and see if there's any ingress, and then see if it works. Yeah.
Well, so that kind of contradicts with your target IP of IP65. So do you want to just stick to the IP65 standard and do whatever dust and water resistance that applies?
Yeah, so yeah, it would the dust, well, it would be ideal to be at IP65, but dust ingress isn't, it is somewhat of a concern, but it's not. I think IP55 would be a better standard to hold both these designs to.
But you would test for that.
Yes. Okay. So for the placement of the attic, we're just integrating the attic into the right rear panel. The location of the right rear panel is rules regulated, in which the master switches have to be on the right-hand side of the vehicle, has to be in proximity to the main hoop, and then shoulder height of the driver, and has to be easily operated. So this was a planned location. The reason why we wanted to integrate right into the right rear panel is because this right rear panel is welded into the chassis, so it would give us a good point to set our main grounding point. Also, it would also simplify the shutdown circuit in terms of the wire harness, because we can just integrate all the wiring inside of the enclosure instead of having to terminate into separate DTM connectors. And then we also wanted to, we put in some fan pump controllers inside because the cooling system is in the rear. And then battery mount is placed at the bottom. I'll show in a better picture, but this is the GLV battery, which is a DeWalt 5 amp hour battery. And then, yeah, there's measuring points here, and then a CAN debug port. And yeah, this, you have questions. This is only just for the location and the component choices that is going inside. Yeah.
Last year, they said that the rear wing was like overhanging the right rear panel. Is that an issue this year?
So yeah, I tried to, during the design process, I tried to place the panel here because that's where most teams do it. But I was told by other people that I should just put it here and just, yeah.
The rear wing is also in a different location, so it blocks it, we believe, a bit less than that in the previous years. So, yeah.
So is the E-stop part of this? Or no, it's just mounted to the same panel?
But there's
MSD.
That's the MSD.
Oh, sorry, I meant the MSD. Is that part of this?
Not attic. It's not part of the attic.
It's on the same panel.
But it's on the same panel.
Does that have its own enclosure?
I didn't model it, but yes, it should have its own insulated enclosure.
Okay. Did you have? So if we do go to MechTech and the rear panel is in fact being blocked by the rear wing, is there any remedy or is it over?
You take out the rear wing.
Yeah. So if you pass tech without rear wing, then
You can't run the rear wing, of course, but we don't believe it'd be a big concern. It's not against the rules per se.
yeah, and I know it's up to the inspectors.
Yeah.
But I mean, their word is final.
Yeah, that's true.
Is there a separate section on rear panel or is this? Yeah, okay.
Is the can like, what, is there a controller there or is it just like?
It's just a wire harness.
Just like wire harness point?
Yeah. It's just a direct tap into the, yeah. I didn't model it, but there's supposed to be a little cap on the DTM port.
And all the.
And all the banana plugs too. Oh, and I didn't model I was going to model the TSMP cover as rules recommended. Okay.
Okay, so next comes the penthouse. The plan is to have it in the nose cone, more in the front of the car. It'll contain ECU, our telemetry compute module, HDMI cable going to our dashboard, a Z2I cable that goes to the camera that's facing front, as well as antennas that are going to be sticking out from the side of the car in the arrow. Plan was above cockpit so that any sort of cables we have are generally shorter, coming from the rear car and front of the car. And the arrow top lid will act as the cover and should make it waterproof for the rain test. And then all the router antennas are going to be routed to the side of the arrow package. Yes.
How are you doing the HDMI connection?
There's going to be a plug on the front panel right here. There's space left over for it that I need to put in. So it's most likely going to be around here, and I'm going to move DC up. Any other questions? Yes.
Is it at the same level as the chest tube or is it below?
It is lower. I need to put in trick tabs here and they're going to be mounted with bolts that allow us to drop it down a little bit and still not interfere with the plates down here for the rules pedal box constraint.
It's not like an issue with the driver's knees and stuff.
It shouldn't be, assuming this plate just extends forward. It does not interfere even at the lowest part up here.
So the arrow is the lid box.
I plan on making an extra lid, but ideally arrow is the lid since this part of the chassis needs to be enclosed and also the top needs to be enclosed and rain test.
Yeah, I'm just like the suspension is like pretty open.
I believe by rules it has to be closed by arrow. I think Forrest was talking about that earlier, right? Yeah, so that will be closed off. Yes.
Is waterproofing gonna be a problem for the two cables?
What do you mean? The cables going out from here to dash?
Yeah.
And the camera? Yeah. I do not think so. I need to check on that and I need to look at where the camera is being mounted because that's still a question. Yeah, just.
Is nose cone covered by?
Yes.
Is that gonna mess with the antenna?
Antennas are gonna be on the outside. So there's gonna be SMA cables going to it that ideally should be quick detach. I'm still looking at quick detach RF cables. Any other questions? Next slide.
Okay. So as a general overview for the right rear or the attic, contains all the master switches and measuring points. Has a separated tractor system measuring point enclosure with a separate connector on the other side that you cannot see. It is 4 pins, so 2 pins will be for shutdown, or the 2 pins will be for the actual TSMP, and then the other 2 pins are for interlocks. The manual service disconnect, it's shown better on this side, but it's separated from the actual main enclosure of the attic. And then the chassis ground point will be attached directly into the right rear panel, which will be the source of all wiring shield drains. It'll also be the source of all low voltage ground. The DeWalt 20-volt battery there's a mount that we have from last year that we're gonna reuse. It has its own fusing part, and it'll be 30 amp fused. Inside will have a e-fuse box and a DC-DC converter, and it'll also have fan pump controllers that are 20-volt input. And then just as a exploded view, we're trying to do a 3D printed shell as the main shell for the attic. We plan on using ABS through FDM printing. Ideally, we want to use high wall loop count, but we'll just have to experiment more on the effectiveness of that. Gasketing, it's not supposed to be neoprene rubber. It's actually supposed to be silicone, but we're trying to laser cut a 16th inch thick silicone rubber silicone gasket. We'll also use additional epoxy seal on the steel side because we're not going to be detaching the box from the steel panel at all. So we'll just do an actual seal. We're going to either use a polycarbonate or a fiberglass lid, something with high stiffness. And then for panel switches, we want to do some gasketing. So specifically the O-rings on the banana plugs. The DTM connectors already have gasketing, and then for the master switches, well, I haven't figured that one out. And then there's a TPU like umbrella for the GLV battery. Yeah.
For your the MSD, no, it's not model. How are you planning to seal that, and also the wires that go into?
I don't know.
Is that your responsibility, like part of your system, or someone else's?
I think it's part of mine. I think
that seems like maybe even more critical.
It is, yeah. Okay. Yes.
So that breaker panel guy is going to be welded to the chassis,
Mhm.
and then the box is going to be permanently affixed to the panel.
Mhm.
When you work on it, are you climbing inside of the bar?
Right. Serviceability will not be very great.
Also, how will installation work?
Sorry?
Like just installing the thing at the end?
Is it like installing the components together? Or?
Yeah, because you have the box, but the master switches come through the front side and all the measuring points.
Well, it won't be impossible. But
Yeah, it won't be impossible.
It's just going to be tricky. But the thing is with this component itself, it shouldn't ideally be needing that much servicing, because it's just a standalone product, and like the only thing that needs to be like touched is just the battery, but the battery is external and you can just swap it out. And then inside, like the only things that you would need to service inside is like a potential enclosure, like a potential PCB failure. But at that point, you would need to go in depth even more.
Do you make the entire box with the panel and then weld the panel on with the box? Or
No, you can't do that.
Or so it has to be the panel first.
Panel first.
To the chassis, and then you have to attach all the box stuff on the frame.
Yeah.
Could you just bolt this to the chassis?
We could, yeah.
Super easy.
With trick tabs. Whatever, it's fine.
Wait, because if you're gonna leak test it as well, just spray water on it. I'm assuming you're not gonna do that in here, like on the chassis. You would take this as a subsystem.
Yes.
Because the only time when it's done is when it's actually on the car. Because the panel will be heavy.
Yes.
You wanna do your rain test though after you've welded it on in case it's not flat anymore. Because you've got an O-ring seal right there, so it's gotta be flat.
I think trick tabs would be a better solution than welding. So that servicing would be better. Yeah.
You guys taking this return material, spraying water on it? I know last year we had this question of could we make, for example, the cooling sleeve out of free-frame material and the water just like went through the
Yeah.
material, because it's pretty porous.
Goes through the seams where the walls
Yeah.
start. That was also but that was pressure like filled with water. So I think it's splash proof, but it won't be like. It was still not fully waterproof. But you could coat it with epoxy.
We could also cut it wall thickness such that it goes hollow in between, at least.
I tried 100% infill, it still leaks through.
I was thinking not 100%, so that there's a reservoir to just capture it.
I'm just saying, those three prints, like, it has rained at Michigan when we were there. We also have like rain tests. Actually, it rains here too.
Yeah, I understand, it's a.
And you're like putting a lot of effort into waterproof, you have 2 gaskets on there. Just gotta make sure the material is not.
Of course, yes.
Wait, also, one of your screws is inside the gasket, so it could just leak through the screw.
Oh, yeah, right.
Yeah.
Wait, no.
Yeah, it is.
No, it's outside.
No, in fact,
No,
you
the
got
gasket
2.
is
I see
inside.
2 that are inside the gasket.
Right. Design mistake.
I'm sort of having a hard time following some of the conversation, but what drove you to wanting this to be a welded plate, everything trying to get assembled on?
I had a conversation with, I don't know, someone, and I did actually want to do trick tabs, but someone told me not to do trick tabs, and then someone told me it'd be better if it was welded, but I should have thought this with a little more intuition, so.
I mean, it's not a bad idea to just, like, we've used the right rear panel before. It's also on the left side there. It's fine. Like, we've used it.
No, it's
just
called the right rear panel because it's on the right-hand side of the vehicle.
The driver's on the, whatever. Yes.
I mean, if it's planned for and you've thought about the rain test and other things, if there was some sort of an easy access thing, but it feels more like it's a surprise and it just doesn't seem to fit the rest of the design.
Yeah, and also everything inside that box looks like it would be hard to service. Like, it looks like you would have to go on like the other side of the car and like lean in to get your hand in there, just to like.
So you want to be able to take it, if you ever have to work on it, you want to be able to
Yeah.
take it out.
Yeah.
So,
It's not that big of an issue because it's not structural, but maybe try and put some more thought into like, this is something that every time the car runs, you're gonna have to check. Well, maybe not every time it runs, but you put it together, you service it. You know, because you guys are gonna be the ones doing it. Also, do a little more testing on the lead stuff.
Is a general question, is the LV system like very sensitive or is it robust to like? If the entire chassis is actually grounded, you have a poor connections. Is that like?
It's not a major concern because it's the voltage difference is not huge. So if there was ingress, the components would not blow up. So
I'm wondering, I don't know if people do this, but do you want like a ground wire like in your harness that you bolt to multiple parts of your chassis?
no, it would be better to just put it into one point of the vehicle, ideally.
No signal no signal grounds?
Oh, the signal grounds go into one central point.
Right, but you don't drag a signal ground around with you?
No, we do.
We do. Yeah, like I'm thinking about like the IMD, like doesn't that have to reference like accumulator ground?
Yes.
So you want that ground to be like the same as this ground?
Yeah.
There's a lot of joints in that path.
Yes.
Okay.
yeah, your words are good. I always like to see a grounding diagram, where it's almost sort of like your cable diagram, except it's just purely the grounding, where your single point ground is for systems.
Yeah. All right.
Okay, so for the overview of the penthouse, again, we have our ECU, which is a revised version from GR25. We are TCM or telemetry compute module, and which is a Jetson or Nano with a new heatsink that makes it a little lower profile. We have our router, and on top of the router, we should have a SAM, but I believe that's not getting put on this year. Then we have our DC-DC eFuse module over here that converts our 20 down to 12 for residents and ECU, as well as the router, and provides eFuses on top of that. For the container, I am using an old X brace and then an FR4 panel mount on top of it with some locating pegs. And that, yeah, and then the walls are just 5mm 3D printed walls that are mounted onto the FR4. And then from there, the overall box dimensions are 15 by 10 by approximately 3 inches. So it's the entire box. Any questions about it? Yeah.
Is that like full and the bottom left? Is that for like a fan?
This guy?
Yeah.
That's for the harness.
Oh,
So it's essentially wire harness is plugged in here. I left some space here to route cables upwards, and then all of this space is up for routing 2 different modules, because I was kind of focusing on making the inside routing as easy as possible. So essentially, like ECU in this case is lifted, so I can access these ports down here. All ports of router face this way, and ECU ports face out into space.
How many pins on that connector?
Which these guys?
No,
Or this guy?
the big one.
How many pins are in the?
It's around 37.
Yeah.
You looked at bend radius and how you're gonna get that whole bundle through there?
I believe we're not using all of them. It's,
Well, the connector is 47 pin, but we're using around 36 or 37 of them.
so is it bend radius for the full harness or like individual wires that you're asking? I do not know that, but I know individual should be relatively fine. I can also extend this if there are any problems. I should probably model the cables going in there too.
Looks pretty tight. I mean, we don't have all the dimensions
Yeah,
on here,
yeah.
but it looks like some of them are gonna get crimped.
Yeah.
Yeah, the half that connector is gonna stick into the space. It's not like it terminates.
Yeah, I need to put it in there, but I don't think it's actually half. The connector, most of it is on the outside. They get mounted from the inside. So you have, it's a screw in from the inside. So you have about, I'd say, a centimeter sticking out. So you have about 3 centimeters going for.
So then you're gonna put the connector in and then you're gonna solder all the connections to the back of that?
It's connector, and then there's gonna be, it's gonna split into harnesses. So none of these are soldered, they're all connectors. So it's essentially, there's like a sub harness inside of it. That makes sense.
I'd like to see the connector, because like if you'd have a mil spec connector, you'd have to put all the connectors into the body, and if it was gonna come from behind the bulkhead, then you gotta come in from behind, and now you don't have enough space for the wires and the back of it, the whole connector to come through. If you were gonna crimp up, do the crimps and then stick it into the mil spec type of thing, you could probably do that one at a time, but you're looking around the corner and that's kind of tight. So, yeah, I would say make sure that you've got enough room that you're not trying to solder a connector inside the box with that many pins. I mean, like 8 pins is hard enough to do.
They're not soldered, you push them into the connector itself.
Okay, so now you've got to be able to make sure you find the right hole.
Yeah.
I've worked a lot with big connectors and
makes
I
sense.
don't do that anymore.
Yeah.
So just make sure you've thought the whole assembly thing through, because you've got to put it together too.
Yeah, that's kind of the reason I left a little bit of space here, because I didn't want everything crammed. I was kind of pushing on more space. But
the space up where the green box is looks okay. It's really the space down by the connector.
Yeah, so
Making that turn.
yeah, so it's this turn right here.
Yeah,
Okay.
that turn right there. All
Yeah, I
of them, you're gonna do a full test, you put them in, you gotta do a full test, I mean, there's just no room.
Yeah, you'd be better off to come and do from the front side, do the mount that way.
Front side might be a little harder because the connector itself is larger than the box. So I can't really front mounted. And then we also have the.
No, what I meant was it comes in from the outside instead that, it's got a flange on it that goes onto the front of your bulkhead rather than the flange going onto the back of your bulkhead. Most of these have choices on, how it is you're gonna mount it up.
Okay.
So when are you gonna have your TBC and your attic first versions built?
I have them in CAD. Ideally, it's gonna be middle of next quarter, so around January 20th, around that area. Currently in design, I still have to split up the entire box so that it can be printed in pieces as well as design the bottom FR floor plate. So
That's sort of about as late as I would want to see it.
Yeah,
Right.
yeah.
I mean, I'm impressed where you are on cabling this year compared to last. You're bringing back bad memories from last year, looking at cabling going, we just haven't paid attention to it. So kudos for paying attention to it. Looking at finished wire harness, 2.7 with welded chassis. You're banking on those boxes being right the first time.
Yeah.
With your January 20th kind of time frame. So anything that looks risky like this connector, you got to get on it quick in case you have to do another iteration.
Okay. I think the other thing about the way that I'm modeling it is the walls are going to be 3D printed, so this piece can move down, if that makes sense. So that allows me to make it a little bit more modular.
If you really go look at it and think about it, have it in your hand, and you're looking at how you're going to do it, you're going to want to do that pretty quickly.
Yeah, got it.
It's waterproofing. So you have fans, so it's not waterproof,
Yeah.
but it's like close to the decoupled hole.
Yeah.
Water could get in and like drip down and then like towards the fans.
Fans
Exactly the question I was gonna bring up, this, how are you gonna have, when you do this, the bucket for the decoupling and then the lid for the top and all these, if there's like gaps and spaces, that is not a good,
Yeah.
you're gonna have to seal this box up. Or you'll have to put a hat on this thing.
Yeah, no matter what, I can't make it waterproof because I do have to do the Jetson, so there are fans that line right here. So no matter what.
Where's forward and where's aft?
This is forward, this back. So essentially this entire part can be sealed, but I need to.
So that back end is the part then that would really concern me. And I think even if it's just a hat, right, it doesn't have to be sealed. Just a hat that comes over so that he doesn't have to make sure that water isn't splashing up and over and then getting sucked in or whatever.
Yeah.
Worst case scenario though is packing tape. That's what we've done to seal up holes in the past.
Flex seal.
Whatever you can do to get.
Big wide roll of flex seal.
Yeah.
Yes.
I'm not sure if I understood correctly. So the part like from the Jetson forward is not gonna be covered by anything?
I still plan to have a cover over it, just like some, I don't know, acrylic getting put on top of it, just so the stuff doesn't like fall in, say we have the nose cone off.
It's like the nose cone usually has like dust and stuff.
Yeah, there's gonna be a cover, but it's not gonna be waterproof or as water resistant, something that's the right rear. Yes.
How's your airflow working? So you have like fans on one side, what's like inlet?
This is inlet, ideally outlet around here, probably where I have the external ports. I need to figure that one out. Yeah, that's I need to figure out with Arrow how waterproofing is gonna look like. Outlet, worst case, I could just have bottom of box right here. That just allows exhaust to go down rather than to the side, if that makes sense. So just have a.
You can have a thing where, you go out one hole, you have to kind of go up and over and around and
Yeah.
that way water can't really
Yeah.
come back, but air can get out.
Yeah, that's possible. Any other questions? For the ECU, so our last year's ECU was 2 layers and used DTM connectors that were soldered on. This year, we're moving to 4-layer, which allows us to have basically better ground planes rather than have a winding ground through everything. as well as JST and Molex connectors to allow us to basically have a smaller harness inside and still connect everything in the penthouse itself. Any questions on this?
Alright, wait, one question.
Yeah.
Were you mixing both the JXT and Molex, or is there a reason why you didn't just stick to just I?
Well, okay, so JST and Molex are pretty much the exact same thing, except JST is the clone version of these Molex connectors we're using. So the connectors are technically interchangeable, but it's just easier to buy JSTs in these like non-standard pin configurations. And if you want something with larger pin capacity, you want to go Molex because they almost guarantee you have that pin capacity, and that's why we're going Molex for our 90-degree that go under our board. This is a slightly older version that didn't really have the correct space requirements from me, so that has been updated in Penthouse, and that's the more recent version. So if you can go up a slide. Yeah, right here we have the two main connectors. I still need to talk about maybe moving this one over to this side, then getting these to be 90 degrees rather than vertical. And that would be the only concern that I have with them. Any other questions?
Is the ECU bigger?
ECU is, it does have more space, but I believe it's still 10 by 10. Well, it's technically smaller.
Like what's on there that, what the extra space?
Remember the hat board for the 4 to 20 signal
Yeah.
converters? That got put on the top. I didn't get the proper STL, or sorry, the step file exported from Altium. But that is taking up a pretty big chunk either here or here.
Oh, so we no longer have the second board?
Yeah,
just
that
all
doesn't
one?
exist anymore.
Okay.
So it's all on same board. Yes.
The CAN bus interface for the Jetson.
Yeah.
Uh,
That is modeled right here, so it has a space claim currently. But so essentially Jetson normally ends around here, but the hat overlaps with the pins that go right here. So I have that catted in as part of the Jetson.
those are the 40 pin things.
Yeah, it's already catted as part of it so that it pushes the router over. I think it's normally 85 by like 95 millimeters, but I have it catted up to 110. And those align with the measurements I have currently. Any other questions?
All right, so in terms of wire harness changes, we're adding a new connector type called using the HTTP 20 series. They're circular connectors that have a high pin count. Things that we're using in this is 5 pin and 47 pin. With this change, we decreased the amount of connections in the wire harness from 52 to 22. Not just because of the connector changes, but and then the harnesses will have 2 main harnesses, like I mentioned before. And then in terms of the design software, we're switching to Rapid Harness and SolidWorks. We're using SolidWorks for SolidWorks electrical routing to map and cap the harness, and then Rapid Harness is for the actual pin documentation and connection documentation and length management. And yeah, any questions?
Are you gonna try to fab in place around the early chassis, or are you building in some margin to deal with uncertainty in physical layouts? How are you dealing with not knowing exactly what things might be?
Like in terms of the chassis, components changing locations,
or just being off by half an inch,
right?
And you didn't allow for half an inch.
So last year, when GR26 wire harness was manufactured, all lengths of the cables were measured in CAD, but in manufacturing we put a 10% oversize on each length to account for the slight inaccuracies.
You did 10%. Is that adequate in all cases?
I believe so, yes. Yes, it was. And in terms of manufacturing, I think we'll keep with the same 10% margin as well. 10% of per size.
Well, it looks like the chassis is coming along in parallel, with you, so good opportunities to do some string measurements at a minimum on the chassis after some of these things get welded on, to where you can double check that you're not 2 inches off, because then your 10% won't be enough.
Of course, yes. Yeah.
The team never done recam heat shrink in wire harness manufacturing before, so
We
you
have
know
not.
how much added complexity to the manufacturing process that would add to it.
So we may try to do DR25, but I think because of I think it would be best if we kept with the original design. But the only reason why I want to consider using DR25 is because it does provide a better sheeting solution than the TechFlex. But
How many samples do you have?
nothing.
When are you gonna get some samples?
We plan to order some at the end of design freeze, which is in 2 weeks.
So I would say you don't really need to wait.
Right.
Unless management just refuses to let you buy it. Because you need to understand the technology. In my opinion, you know, I used to have some really high trained techs and they had no problem. Work loved it, worked fine. So you may love it and find that it's easy, but if you've never done it before,
it may be
I could be wrong, but go get some. Go try it. Go get a few up next week. Or whenever you get to it between classes.
I think TE connectivity has some samples that you can have to recam.
Yeah, but I'm banned. Yeah, we'll order some.
I might have some like on them.
How many people wire breaks inside of the heat shrink? Will you be able to replace it without taking fresh full heat shrink?
If a wire breaks, then it's really bad. Well, the hot fix solution to a wire snapping is to strip the outer sheathing and then do a manual reconnect. But with DR25, it's supposed to be a more permanent solution than TechFlex is. So
It is, but I
Can
don't
you
think
drag
it's that
some
hard
extra
to do
wires?
rework either. So get some and practice with it.
any other questions?
Is there like, how do you test this after video? Like, aside from just connecting it to all the components, is there a way to make sure connections are good?
Well, there's continuity checking, just a multimeter. There's also just testing it with all of the components connected together. But continuity checking would be the primary.
Can I make a
test.
suggestion on that? One of the things that is not just, you know, beeping things out, but actually measure the resistances.
Right, yes.
Because it saved a lot of heartache on things like closing up cryostats and then having to open them all back up again.
Any other questions? So for connectors, we chose the HB20s because the contacts that they use, we already have a lot of them in inventory. So, and then in terms of contact sizes, they come in 16 and 20. 16 allows for higher gauge wiring, so that's going to be our main powering wires. Any questions? And then for shielded wiring, we're switching from pre-twisted wiring they had color options, and we use this for GR25, but for GR26 we plan on using a shielded twisted wire pair in 22 gauge. They're slightly more expensive, but and then for shield drain is again going to be connected to the main grounding point. Any comments, questions, concerns? So this is the overall CAD of the wire harness. It's kind of hard to tell where exactly everything goes. So this is whatever. So there's the main connectors are just a bulkhead. The E-tray connector, the attic, and the penthouse are using the HTP20 connectors. And then everything else uses standard DTM 3-pin or 4-pin connectors. What's not modeled is the sub harnessing, such as for the sensors for the ride height sensors at the bottom. Also the cooling cabling is also not modeled in here. And then the documentation, we're using rapid harness, comes with an integrated cut list, BOM wiring table and whatnot. For manufacturing, we want to try to create a 1-to-1 scale of the schematic to facilitate in the manufacturing. The diagrams on the right are quite not finished. The connections are made, but the lengths and also the layout and organization of the documents are quite messy and should be improved. So, but I'm only showing this to.
Yeah, the only thing you gotta watch for on those wire boards is to make sure you capture the required 3D turns. Right, there's a tendency to think of it as a 2D problem. It's not.
Of course, yes. Any questions?
Are there wires that are not differential and not shielded in voltage signal?
No.
Okay.
Just 4 to 20.
Like the other signal wiring is just 4 to 20 milliamp. It's current signals. There's no analog voltage signals at all. And if there is, we want to just the signal condition them before we put it through the wire.
Are there digital voltage signals? Except canvas?
There shouldn't be, because we don't have SAM sensors anymore. So the only things that are going are going to be 4 to 22 penthouse. All the digital signals are going to be for like time of flight that are going to be part of the sub harness sensors. And those should be on board level and then get transferred to CAN.
This shouldn't be too long.
That they're going to be on board. Okay. So it's microcontroller plus sensor on board. And yeah, they just get it so we convert it to CAN.
The camera?
Camera, I believe, uses a shield like Type-C cable.
It's also quite short. It's just right above the penthouse. Yeah.
And it's again away from anything high voltage, because you have high voltage in the back, so everything signalized in the front is more safe than things in the back. Anything else?
And that's it.
I see the camera being used as a stopper, so yeah. No, I was just saying the cameras should stop anyway.
Yeah, not critical component, so Jackson.
Okay, hello, I'm Jackson. I'll be presenting on the sensor systems integration. I would like to address, the systems team as a whole at the end, but I'll go through what I have on the slide first. So for the agenda, I'll go through my design goals as well as a recap from what happened last year. Electronics already covered a little bit of it, so we don't need to go through it next. And then sensors list, and then the enclosures and mountings of the sensors. So housing, similar to the rest of the electronic components, we need to meet the IP65 specifications, which is dust protection and water splash. So for the rain test, obviously the sensors are going to be exposed on various parts of the car. So the rain test will be quite critical to many of those sensors. For some of the sensors, we do need to maintain integrity at high temperatures, specifically some of the thermal modules, looking at brakes or tire temp. So specifically for those ones, the structures need to maintain integrity to those high temperatures. And this no deformation under 16 G load, I took that from the suspension data. I know there was some concerns over it was a 8G load from outboard bump. And so I just doubled that for factor of safety. I will go through with them to decide what kind of load we will expect, whether that 8G is within reason. Mounting wise, I'd like to keep our sensors plus or minus 2 degrees under vibrational loads. Some of them do have a pretty narrow FOV, and so being able to keep that window within what we're looking at is quite important. Standardized fasteners, I'll go into that a little bit later. I plan to use M4, which I think is what we used last year. And then team, get stuff started early. I know we've mentioned this a lot. So avoid scope increases, and I'd like to test all of our sensors, the enclosures themselves, and then with the board inside, make sure that everything works as intended, both electrically and mechanically, by the rolling chassis deadline. So for the GR25 recap, this on the slide here is a inertial sensor housing that we used last year. As electronics mentioned, a lot of the sensors did not get mounted, so mounting wise, we're not entirely sure how this was done. But enclosures wise, you can see this is quite a bit longer than it is wide, and the screws are on the corners there, labeled in green. And we did try to use gaskets last year, but water was able to get into that top kind of clear plastic there. And that's just because the plastic wasn't rigid enough with the force of the gaskets underneath. And so we need to rethink how we're going to fasten the top and how that interfaces with the rest of the sensor. Mounting, as I said, not everything made it on the car. Some things we did mount were generally effective, but obviously with a lot of the stuff not being put on there, a lot of things need to be tested for this year. What we can see here, we have a welding tab and zip tie holes, as well as the circular portion to mount onto the chassis. So that welding tab, and I'll go into this a little bit later, we have heat set inserts that melt a small portion of the 3D print, and that allows for threaded fasteners into the 3D print, and it's a lot more solid than what you would get with just putting a bolt into the 3D print itself. And then that weld tab, I will get into issues with jigging onto the chassis to make sure it's located properly. And then the zip tie holes on the other side will make sure that vibration isn't quite as much of an issue. As for other components, there was an issue that I personally worked on with the main ECU box in the front. Things in CAD kept moving around, so mounts had to be redesigned and redesigned and redesigned. So sticking to those timelines and being able to say, okay, we know this is finalized, and then from there working on space claims and such will be very important going forward for sensor. Questions on what I presented so far?
I just wonder, big picture, does the campus have design software that you guys can do any kind of 3D VR, where I can walk around your chassis with everything installed and actually look at where I think I'm gonna put sensors?
There is a few labs. I think there's some in the library you can also use potentially for that.
But is it anything that's set up where just like that, you could port everything you've got into one of the labs and go walk around and let the sensor guys really look at it?
I am not clearly aware of any. Does anyone know? Or no?
Okay.
There might be one. We're just not.
So if you don't know about it, that it's not commonplace, which means it's not gonna be trivial, like
Yeah.
10 years, it'll be standard.
What were you suggesting for the AR VR kind of idea?
Well, one of your issues is you're sort of the last to come to the party, right?
Yeah.
And there's nothing you can do about that because you just gotta live with everything else. But if you were able to put on some VR goggles, have the latest CAD version of the entire vehicle, you've even got harness guys that have integrated all of it, where you can walk around and look at where things might go. So that you really get a sense for where you've got an option to put things. I think it would make your job a whole lot easier than trying to do it, looking at a CAD model and then wondering where people are moving and wondering what kind of glue it might be. It's just much easier to see interferences, things like that. A lot of people are using it these days.
Thank you.
But it's expensive.
You said library, correct?
Potentially.
And so I'll go through the sensors we have, or this is fairly finalized. I think all of the sensors here, I've got 2 slides. So we'll start with suspension. Suspension travel, we plan to use a linear potentiometer as well as a magnetic encoder. So that will be used for suspension validation and tuning on the decoupled suspension module. And so we'll use 2 LINPOS total, 4 magnetic encoders total. So split between front and rear decoupled suspension. And then thermal wise, we have the tire temp heat map one. That'll be an infrared camera to look at suspension tuning, wheel load, and then tire wear. And as I said, this one is one of the ones with a pretty narrow field of view. Needs to be mounted pretty rigidly in view of each tire to be able to get the data we need. Brake temp also similar, and as I mentioned earlier, the high heat enclosures. These will get pretty hot, so we'll need to test whether our enclosures can withstand the temperatures we expect. But this is again for braking performance and efficiency, and then thermal modeling of the brakes. This will be inside the wheel assembly facing the brake caliper. Brake fluid will be inline pressure sensor. This will be similar to how we have cooling, which we mentioned earlier. This will be for pedal feedback and then brake system plausibility. It's needed by rules. And then this, of course, will be in the brake circuit. Vehicle heading and acceleration will have a differential GPS in the center of the chassis. So that'll help, of course, with lap and speed analysis, and then the general driving performance of the car. And as I said, in the center of the chassis. Ride behavior we plan to have 8 time of flight sensors. 8 does seem like a lot, but we want to have a little bit of redundancy, and especially since none of these sensors have been on the car before, we want to get as much data as possible and then trim down from that high amount if we are able to clean up the data in time and know what we're working with. Next set, we have steering inputs. This is a rotary potentiometer that comes with our steering rack. And so that'll help us analyze between the outputs we get from the car and then what the driver inputs steering wise. Accelerator input, I think we mentioned the accelerator pedal position sensor earlier. So analyze the pedal inputs and detect changes between what the driver inputs and what throttle we get out. Coolant temp, coolant pressure, both will be in line. I think the cooling presentation mentioned this earlier, and that'll help with monitoring cooling performance and fluid losses as well. Wheel speed will be a Hall effect sensor. I've been working with suspension on this to get it mounted. I know some of that will be changing based on geometry considerations, but that'll help us analyze traction, stability, and then braking performance as well. And that will again go in the upright. And finally, we have our camera. Not that we'll be going into autonomous yet, but we hope to get some stereo data from this camera that it'll be mounted to the front of the decoupled plate.
I have a question. So for steering input, do you want maybe put one up high and one down low so that you can see how much of this how much slop there is in the steering, and then whether or not you're getting other things going on? It's harkening back to the the U-joint discussion and all of that. So
So
it
you're
might
saying-
actually be good to have one up at the wheel.
Okay.
And then one down at the rack and pinion, so that you can see what's the driver doing, what's actually making it to the car, you know? And maybe you could say what the car feedback might be an interesting. You'll see the driver doing this and the car just sort of go with something else, you know?
Yeah, I think that's a good point. The steering input one we currently have comes with the steering rack that we bought. So adding another one would be more custom.
So that one's down, lives on the rack.
Correct, yeah, that's down.
So yeah, this would just be some sort of, well, it would be an encoder with a sensor just behind the steering wheel.
Yeah.
You could also use like a gyroscope, just if you want to test its time to see at least if the steering board. Should be pretty easy to know.
I think that's a good point.
I think it'd be useful to highlight which ones are rules required.
Yeah.
When you say decoupled plate, do you mean like the actual, like part the decoupled mounts on, or the chassis bar in front of it?
It's the plate that the decoupled itself is on. So
Because that's not gonna be covered. That part's gonna be exposed to the air, and the nose cone is gonna come underneath it.
Correct.
So they will, I thought that the working plan was to have it in the nose cone and then have like a clear like slit that we put something over so that it can see out. Is it able to be exposed to the elements?
The camera itself?
Yeah.
Yes, I'm pretty sure. Oh, electronics left. But I'm pretty sure the camera is built to be outdoors. The only concern with that would be connections between the camera itself and the penthouse.
Okay.
Are all of these digital? You said the steering input sensor came with the steering rack?
Yes.
So all of these are digital?
I think electronics would be the ones to ask about this, but as far as I know, yes, digital.
I think at least for design competition, it would be nice. I know that most of our sensors will be digital, but if we do have an analog sensor, it would be nice to just say, hey, design judge, we have this analog sensor, we did this kind of signal processing, this filtering on the hardware level to kind of get those points. Because in terms of data acquisition, there's not all that many boxes we can check. And we want to make sure that we can say we checked all of them.
Right. So go through and evaluate which is digital versus analog.
Yeah, I can talk with you about this later. It's just, I'm a bit confused that I was told the steering input was an analog sensor, and that's kind of contradictory. If it comes with the steering rack, it would seem to do most of the work for you.
It's an analog potentiometer that's mounted on the rack. It like has a mount designed into the rack. That's why we.
Okay.
And it was just like a thing that came when we purchased it. It is just like a normal potentiometer with an analog output, but Vin was talking about putting a signal condition on it to make it 4 to 20 current million. And to your point of like filtering and whatnot, well, I guess Vin and Audrey are gone right now, but if I remember correctly, there are like filters and whatnot on the ECU itself, which would be measuring. But talk to them.
Moving on, going to the enclosure side, electronics covered a lot of this with their mounts, or sorry, their enclosures. So a lot of this will be similar. So as they mentioned before, more wall loops, more infill, and then what I personally would like to do is test all of these to make sure, okay, we think these 3D prints will work. Let's actually make sure they do. As part of, I don't know if all of you are familiar with IRCA, but as part of my IRCA project, we'll be doing static rig to test all of these. And so February, I'd like to create that. March, as I said, the deadline earlier for rolling tests. I'd like to test all of these sensors before that, and that includes the pictures. Waterproofing,
We mentioned gaskets already. I will go into on the next slide, conformal coat and then potting compound, how we might use those for sensors.
What are you testing on your static rig?
I think that's gonna be in conjunction with hardware in the loop, so that'll be electronic testing. But before that, I'd like to test like the enclosures themselves for waterproof, for heat, for. So epoxy versus conformal coat, examples of both. Examples of both below. So the potting compound or epoxy is much thicker than conformal coat is, but does offer more protection. I know Curtis was worried about the weight. It should not be too much. Most of these enclosures are pretty small. Another issue with potting compound is that it will be very difficult to repair once the potting compound is added. So that might be a kind of last step in waterproofing the sensors. Conformal coat is applied to the PCB itself. So it's a thin film with a spray application and has less protection, but does protect against moisture, dust, and corrosion. Very lightweight, transparent, and you can repair the electronics after applying it. So not to say that one has to be either or, but we can use both if we want to, along with gaskets if we feel they are a good option. Some examples of electronic mountings for other teams, lots of 3D prints, lots of zip ties. There even is some tape and Velcro, which I'm personally not the biggest fan of, but especially for components that don't need to be super rigidly mounted, some of these clamps and zip ties are an option that are cheap, they're lightweight, and fairly easy to take on and off. So as I said, for rigid mounting, or enclosures wise, 3D printed when we can, and for mounts as well, in conjunction with, I mentioned before, our heat set inserts. You can see in the top right here. So what that is, it's a little metal insert that you take a soldering iron and you will press that into your 3D printed enclosure. It creates a little, or it melts the part a little bit and then allows for a threaded connection. So like a threaded bolt into your enclosure, and that allows it to mount much more rigidly than otherwise. Zip ties tape, I already mentioned, lightweight, easy mounting, but of course less secure. So that might be something for cables or wires rather than all of the enclosures themselves. I would prefer mostly bolted and threaded. And then at the bottom there, I'd like to focus on simplicity. You see, this here is an example of fluid line mounting. Left side is very over designed. Right side might be actually a little under designed, but we'd like to keep it easy, not, as I said, let scope creep happen. Questions here? Do we want to talk about systems team stuff or leave that to separate conversations after?
You guys prefer? Do you want to hear about systems from the systems team structure, or do you want to move on?
Well, we should probably stick to your agenda.
Okay,
I mean, it's one of my.
We can talk about that personally after.
Yeah, and I'm willing to come back if you guys want to have some conversation
Okay,
on it.
sounds good. We'll do that. Daniel.
Hello, I'm Daniel, the formation lead. Yeah, let's get started. So we're gonna walk through our purpose, a bit of what happens in the past, our organization, and then how we're gonna try and do some more formal validation this year. Here's some photos. There's a wiring harness from last year on that table right there. So our purpose is to basically program the boards that aren't under high voltages domain and aren't under data teams domain. And this comes down to the ECUs, the SAM, which I just learned is not going to be on the board on the car, and the CCU. And our goal is to really just have it be something that's there. It works invisibly, doesn't have critical failure. Any critical data gets throughput. We're always prioritizing the driver. And then ideally, we're going to make automation efficiency and really build a solid base for future cars. Yeah. So in the past, we had 3 files with 2,600 lines across them in TNC. The year prior, we had, or the year in the middle between those, we had the STM32s using the HAL and LL libraries. And so this year we are using the STM32s again, which allows us to actually start building up an idea instead of rewriting our code base from scratch. That being said, we are going to rewrite it from scratch. But this time we're going to do our best to follow version control and other industry best practices. There's an example that you can tell that the dash panel, for example, somehow ended up with 0 contributors and 0 issues, and that's just blatantly inaccurate, but it just highlights the need for improvements. And finally, last year, here was our state machine. Here, the biggest change you'll see is that errors were handled as a separate state. This led to confusion with TS discharge off, discharge in a high voltage system, and an error, for example, and required to keep state outside of the state machine. As well as unnecessary complications in the drive active state itself, considering regen never made it. As well as it has a lot of states that aren't super critical to have, such as reflash tin. So in that spirit, here's the revised state machine diagram. It needs to be a lot simpler, operating more as states and less as potential transitions. So in these states, the car is stable, and any input could set it to a different state, but it won't change its state as a function of itself. So we'd start up with GLV off, general grounded low voltage off. You'd turn on the switch, that would activate everything, the ECU itself would boot up. If the TS active button is pressed, then you'd get a pre-charge. When the pre-charge process completes, then you're waiting for the ready to drive signal before you're able to turn on the car's high voltage. At that point, you're able to drive using the throttle. And after that, you can safely discharge the car, or if an error happens, you'll also discharge the car. And this will only put you back into a low voltage state once you are confirmed in low voltage. This is opposed to last year where you could be in something that looks like a low voltage state, but you could still have high voltage in the car, and this just goes to prioritize driver safety. Yeah, and so our drive active was also simplified. It's now just a single state. It's going to have non-critical errors handled inside of it, as it should. It's just a state. Yeah. Are there any questions on the state machine? I know it's a bit.
I really like it. I have to wonder behind the scenes what all was going on that led you to realize this was a better kind of approach, but that's an outside conversation, I guess.
Why did you remove transitions?
We kept transitions. The one that I'm specifically calling out is this drive standby, because at that point the car is turned on and it's ready with all but the actual torque request. And then the other one is this idea of having an error state as opposed to an error transition. So we actually added that in where error is a transition that happens, because any state could have a critical error or a critical need to discharge rapidly. And so on this version instead, if something goes wrong, it's kind of obscured by down here. Errors are handled on the edge.
Why do you have GOV off there? Like your code is not running with GOV off.
Yeah, that's part of the idea of just what we're doing. If the GOV is off, then nothing's happening, but I figured it was worth documenting what's physically going on in the car as well. The code on the car will never be in a GLV off state because the ECU is unpowered.
Yeah, I was just gonna ask, do you guys have a way of handling like non-critical errors? Like let's say, I don't know, maybe you'll come to it, like, do you have like failure modes in mind for like the sensor array and if that fails?
So for sensor arrays, if they're critical, such as the pedals, something like that, those we're going to consider as critical errors. Depending on where we are, those will lead down to either discharge and then back to GLV on, or just back to GLV, or yeah, straight through.
So like, do you have like a hierarchy of like problems? Like there's like shut off the car, and then there's okay, you can still keep driving, but we might have like the degraded like stuff.
No, we don't actually have that. I just have a list of these are the things that can happen. I haven't orientated that into a this means that we should do this, this means that we should do that, besides just reading the rules. That's a good point though, thank you.
Yeah, it would be nice to review that complete list of errors, but it sounded like I assumed that you've got some you're managing inside the state. Because you can afford to stay in that state.
Yeah.
And then you've got some you can't, and those are the critical that fall outside, but you ought to know every one of those, which ones you're considering into which bucket.
Exactly. And so the other change we're making, instead of having 3 different repositories, instead of having a single giant files, is we're building out a very industry standard monorepo. Currently that has about 1.7 million lines of code, or about 80 kilobytes or 78 kilobit bytes. And essentially this allows us to do what you'd see in industry, where your main branch is going to be proven, it's going to be tested, it's going to be verified, it's going to have gone through a whole peer reviews. And then other branches are going to have other things. They can be testing, they can be trying new things. Additionally, with our monorepo, the way we're setting it up is that the platform is fundamentally isolated from what a given board could do. This will help extend for future years. This does come with an overhead though, as most of our libraries are being implemented. But the way it's currently set up is that we are going to implement a bunch of things, but if we don't need them, or we're running out of time, we can drop them, go back to the easy way, which is just tons and tons of lines of code. But that's easier because it's generated. And that'll keep us within a nice margin. And then the monorepo will also run unit tests and do some other automation work for us.
Was there a N after each name?
Sorry?
Was there a N after each name?
Just to symbolize that this could be living docs 0, 1, 2, 3, 4, 5 or something. It supports multiple instead of just one living doc, one board. I was trying to find a way to represent multiple without overclouding it. So a big part of this is we're going to try and use more of the LL abstractions provided by STM32 as opposed to more of the HAL ones. This just allows for significantly increased speed. I don't have numbers on that speed because every function is different, but from rough testing it is significantly faster. We're also not doing a real-time operating system, instead handling things on an interrupt cyclical balance. We're going to implement smart serial logging. So if you're plugged in to the car and you flash the boards in a certain manner, you'll be able to get live debug output. And alternatively, if you flash the boards in a different manner, that overhead will be completely removed. And then the way we're packaging everything up all together is just as tiny libraries that are then all compiled together into the firmware that goes onto a board. Yes.
Yeah, I have a question about like not using RTOS. So I assume like it'll be like a single loop, and then you have like ISRs or whatever you plan to do. So like each thing the components are communicating with will probably expect like a certain frequency of communication, like say for request is like 100 hertz. Do you have a way of testing that and verifying that?
We do not. In previous last year, without being able to verify any code, it seemed that our loop was quite tight enough that we were able to sufficiently stay within that. Yes.
What is your planned interrupt priority?
CAN as one of our top, and then other things below that.
Continuing on with the question, are you sure you want to have CAN on the top, or do you want to have something like a hardware fault as your?
Well, I mean, the hardware fault is required by the STM32 chip to be, I think, -1 per or -2.
Not like the STM32 chip hardware fault, like a signal fault or something like the shutdown.
Okay, so we'd have the shutdown, and then we'd have critical failures that we'd find, then we'd have less critical operations like CAN, since CAN controls ACU and stuff.
CAN
Then
should be
we'd
the
have
least.
less pinging and stuff.
Should be the lowest priority.
CAN would be lowest?
Yeah. If something's code decides to just crash and keep spamming the bus, you need to make sure you don't get just stuck.
Yeah, that whole, whenever you've got it and you're ready, you probably should review with a lot of the team exactly what your priorities are, in addition to which errors fall into the critical and which errors are going to be managed internally. Because they will have an understanding of the ramifications and possibilities of that error far beyond what Do that.
So our goal here is to really try and follow industry best practices. We're gonna have different runs happen, we're gonna have validation. And we'll also have it upload files that you can then flash on your own in case firmware happens to be sleeping or something. It'll also do cross builds, cross platform and all that kind of stuff. Just to help catch bugs that happen earlier with different compile versions. This goes hand in hand with automated testing. We're going to be set up a CI/CD pipeline. We're going to try and do linear history with comments. We're going to have asynchronous code reviews, peer reviews, and really just trying to smooth out working on things while still making it possible to follow these best practices, like protecting them. And then our last organizational point is the controller area network. Our ARCA project this year is to make living documentation as our configuration. A big problem we had last year was someone would change the CAN documentation, but then other people wouldn't be notified. And so you'd be building off the wrong thing, you'd be setting the wrong data. And that's really hard to catch. So the goal is to not do that at all. So it's going to be straight, your one source of truth, get compiled down into code. And then if the source of truth changes in some manner that isn't compatible, then your code will break. And that, or your code will fail to compile, and that'll mean that things aren't what they seem. This will help prioritize just ease of configuration and testing. And then finally, standardly, we're building out APIs. We're building up these things for future years to try and make life easier down the road. This firmly takes a second seat to getting a functional ECU, a functional CCU. But it's a nice thing that happens in addition to this. That means that next year, we're not rewriting our code base from scratch. We're not even writing half of it from scratch. Any questions? And so in terms of validation, one of our big designs is instead of having a bunch of global state kept in a variety of different ways, we're going to try and dependency inject. So any function that gets called, we'll try and get as many or all of its variables from the calling function. This means that things percolate downwards, and that a function can act more as a mathematical function it's going to have side effects, but ideally less side effects. And this is in software. You can't really abstract the side effects of hardware changes, such as GPIO. But it restricts things to a much more limited scope. Yeah. And so because of this, we're able to isolate different components, and we're actually able to do different forms of testing. So the smallest of these is hardware out of the loop, where we're going to use the code that we've made and validate it does what we expect. And this will use the minimum amount of actual production code as corresponding to the test code, but it'll mean that critical pathways such as our bit manipulation library and stuff like that will do exactly what we expect. The other form is human on the loop, which is basically before we do anything, we're going to run through it. I'm going to sit down with paper and pencil. We're going to catch undefined incorrect behavior. We're going to validate against the rules. And this is going to really be helpful for logical errors where you test and your code are corresponding, but they're wrong. And then finally, honorable mention to the electronics IRCA, the HITL testing. That is going to help validate that our abstractions and everything below our top level is going to be accurate, specifically GPIO as well as CAN and other items. And altogether, this helps form our idea of correctness, where we can say that our code is as correct as we can envision it, and that will make debugging down the road. You know, if you look at your paper, we have approximately a 2-week timeline for debugging, and that's incredibly tight. I think last quarter it took us 6 weeks, 4 weeks of debugging. But the goal is to isolate as much code as we can to prove that it's correct in advance of that debugging time to then make that process easier, help keep us on track. Any questions?
So between personal safety and then machine safety, does any of that rely on communications and computation? Like, you know, if you had, you know, safety interlock system sort of a thing, does any of that rely on computation and communication, or is that all, especially looking at the safety interlock system sort of a thing, or is that all just purely hardware
So things like the shutdown circuit are purely hardware and firmware is explicitly not allowed to touch them. But things like controlling whether or not the motor is running, firmware has a large say in that. I think firmware has the only say in whether the MRAX is actually spinning or not. Well, in addition to the ACU being ready. So there is critical components that we are interacting with. But defense in depth, I believe there's safeguards on everything that we do and everything that happens. Can I answer your question?
Yeah, I think so.
Any others?
I saw you mentioned unit testing. Is your main form of like integration testing that hardware in the loop stuff?
No, our integration testing mainly is going to be human on loop. That's going to be us sitting down, manually jumping to a state and verifying that it does what we expect. Hiddle IRCA is not directly involving us, and so I'm not going to plan to test correctness on it. It's going to be a check that what we've done is so far right.
Also, do you have like any like redundancy or resilience in regards to like missing canned messages if something goes wrong on the bus?
If the CAN bus goes wrong?
Yeah.
I mean, as mentioned, we'll have to prioritize our interrupts. There's a ping mechanism. If certain components are no longer online, we're going to treat those as either non-critical or critical errors. Yeah. Yes.
So earlier today, we were talking about cooling and like finishing endurance. Have you thought about maybe implementing like a derating system for the motor for like max power during endurance, or maybe just talking to battery team and
Yeah. My hope is that once we have some data on what we can expect, that we'd be able to implement some form of torque curve that keeps us below linear, but says if the temperature is rising, then we need to reduce our maximum output. But that is reliant on getting data. Beyond that, we can try and implement a linear curve or something, but it's going to be a shot in the dark that might not be helpful compared to what Ryan or something could do with correct data displayed to in real time. No questions?
Are you planning on like adding or organizing your unit testing compared to last year?
So the main, compared to last year, is quite simple. We had 0 testing last year. Literally none. This led to weeks and weeks and weeks of debugging. But the main idea is that things that are implementing with platform drivers inside the looper are going to have to be tested using hardware in the loop or clean on the loop, because we'll have to actually look and see if an LED turns on or something. But beyond that, like a bit manipulation library, we're going to store the testing data and the testing setup right next to it in that same folder area. So we have our headers, our source, our tests, our CMake for that. Does that answer your question?
Yeah, but I think also I was just thinking about like what types of tests are you gonna do? Like, are you gonna do like latency tests? Are you doing like error tests?
So unfortunately, hardware out of the loop means that it's running on a computer that's controlled by us. So it's a nice laptop instead of that. Calling that specific one we did was a circular buffer implementation. We had a test to verify that we're not leaking memory. What happens if we try and add too many things to the circular buffer? What happens if we try and smash the circular buffer? Things like that to see what happens in one of the possible failure modes of a given tool that we make up. Same with our bit manipulation library, saying, okay, here's some random arbitrary thing. What's this bit, and verify it's correct.
Yeah, but do you guys have like a checklist or like some sort of way to organize each type of test you're doing? Or do you just kind of do it based on like we can do this test?
So each thing's organized as a single library.
Oh.
The standing not official rule is that every function should ideally be tested, or to have some test that enters it. So if you have a push function, ideally some test covers that. That'll come up during the PR process. Hey, I noticed you haven't tested this branch of code that does appear critical. But there is no formal 100% code coverage or any requirement like that due to the complexity of working on firmware instead of a software level. Any questions?
I'm just curious, like what's the manpower? How many people do you have working? Because like building your own library for like every function seems like pretty large task.
For the most part, that's been done for the criticals. The manipulation, circuit buffer and stuff. We have approximately 30 members. Of those, I'd say we have a manpower of about 10. In terms of that is the goal.
That's pretty good.
That's actually a really good number.
So my estimation is that we'll get, data team's gonna need to borrow a person. We're gonna need 3 to 4 people working on ECU, 3 to 4 people working on CCU. If SAM boards crop up, they'll each need a person or two. And besides that, the rest of the people will help out swapping in and out to form a single person hour worth of work. And also these libraries have been implemented in adjacency to these. As a back-end lower priority thing. Because of how STM32 works, if something doesn't come through, we can use CubeMX to generate that. And that's currently our failure mode is we're trying to get a nice CAN abstraction going with the circular buffer. But if at the end of the day, the timeline doesn't hold, then we're gonna say, nope, we're gonna use the tools at our disposal, get something that works, get something that will be working enough to meet the endurance and all those other goals. And then next year come and try and make it better. Anything
Just letting you know, you need to account for situations where the canvas just dies. Because as far as I know, the STM32's CAN controller just pauses itself when it receives like an incorrect sequence. You need to do something to restart it.
Incorrect sequence as in?
As in like maybe a bit is flipped due to noise.
I don't, that comes as a CRC interrupt, or a CRC flag, and there's a CRC registry callback that we have to engage for that specific error case. And then presuming that hopefully, if someone's taking the notes, then I'll remember that, we'll make sure we have that in there and we'll drop that misaligned packet.
Thank you, Daniel.
Why is there? Never mind.
You can't get it.
Agenda. So, given my audience, and this is the last presentation, and I'm presuming a lot of people are tired, and I'm going to give a very generalized historical infrastructure. Again, our system has been developed over the course of about 3 years, so there's some good context that needs to be done. I'm going to speak in a relatively general sense, so if I mention something or I breeze over something that you're more interested in, you can ask me about it. But again, for the sake of CDR, and that this has been developed for quite some time, I'm going to try and move through quickly. Okay, so to begin, just so everyone can kind of understand what's going on. So when we say microservice architecture, it's just the way we built our application is so it essentially functions as a bunch of interrelated but independently functioning applications. So it's really easy to add one function later on or change one function down the line without destroying the whole thing in general. The TCM is basically the compute module that's on the car. So this is where our code will be running when the car is on. And then Mapache is kind of it's just a suite of services. It's basically essentially everything that we've been working on for the past couple of years. But for the sake of this presentation, just think of it as we're inputting data and then we're outputting the scaled and deserialized values. And then for cloud, I guess, is just all the compute that's happening in the cloud. So there's a computer in the cloud, specifically some AWS EC2 instance, and that's where all this computing is happening. Okay, so the main infrastructure for GR24 was you get CAN data on the car, the TCM sends it to the cloud, and then Mapache deserializes and scales all the values in the cloud. So essentially you're getting data, and as soon as you get it, you're just sending it to the cloud, and then we do whatever we do with that data. And we did our first test run, or I guess we got our first data at SoCal, so huge milestone for us. A lot of really fun stuff, and there were a lot of problems. And because this is the only kind of benchmark we have for real-time data acquisition, this is a lot of what 25 and what now 26 is going to be based off of, right? But again, so the first thing is kind of just a peeve of mine. We have the uncalibrated IMU data. So we were supposed to have a, what was it called again? The BCM? Something was supposed to exist and it did not. And so for most of our critical telemetry, the one that most of our engineers care about, aside from the electrical people, but even still them, was all captured from a phone that was loosely duct taped to the floor of a car. And this phone was not calibrated beforehand nor afterhand, so there's no way to discern the ground truth from those measurements. There's no way to tell what data is real or what data is not real. And so a lot of or I guess anything you get from an IMU, so GPS position, acceleration, kind of velocity, that one's a different story. Like all that data is really bad. So that wasn't fun. LTE only, again, like I mentioned, we have the data from the car, we're sending it to the cloud, and then all the processing and the deserializing and the storing is happening on the cloud. And so if it messes up in that process, then you lose the data, which happened for a couple of our runs. Timing discrepancies, we also didn't have in place a good system to like session stamp our laps when they started, when they stopped. You can see in this bottom diagram, so that's our phone recorded GPS data. That is for our lap time, but you can see it doesn't go all the way around. There's kind of no truth. There's no between laps. The position could be different, who knows? That was kind of bad. Sample rates for a lot of our sensors was really scuffed. So anyone who's worked with the data will probably know it was kind of not the best. And there's also, that data right there is pretty much the best we have. If I were to describe what our other GPS data looks like, it's like you gave a crayon to a kindergartner and they tried to sketch you something. And if you were, it would be zoomed out and it would be moving within miles in the lateral and longitudinal direction. And that doesn't really make much sense. So that happened as well. Node-based sending, I'm not gonna go too much in because it doesn't matter because we've already fixed this, whatever. And then time synchronization issues. So we had actually good data from the GPS, although that was also very finicky because I don't know why one of the runs outputs this with really nice data, and then the other one also just looks like a toddler took a crayon. Maybe that's just a GPS thing. But the problem is the synchronization between these two was completely impossible. Not only that, the GPS or the timestamp for that GPS data from the GoPro, it was like 2 years too early, 6 months too late. So there was no sync, there was no real way to sync it unless you were to match the data timestamp. So that's just, or like the actual data, the payload of the data. So that's something else I wanted to consider, which I haven't answered yet, but just problem preaching. Okay. Let's see, signals. So this is one of the things I kind of want feedback on. I think I'll just go into it. So the way we get the data is essentially we're sending the data as individual signal packets. So you'd send it as this, you'd send this one data and then it would be stored. So all those 4 signals would be associated with one timestamp. And as you can see in this bottom, they kind of show up as this, where they have a value, a signal ID, when they were received, created at, all that fun stuff. And all those would be locally related with a timestamp. But then if you were to compare it to these, they would not be associated, right? So again, motor RPM, throttle, if I were to compare those, the timestamps would match. If I were to compare these 3, their timestamps would be slightly different. They might have different sample rates, who knows? And so the way we kind of solve this was to just query each signal individually and then join them together on the closest matching timestamp. And so if you have different sample rates, you're doing some interpolation. If you have different, like if you're originating from different timestamps, you're kind of, and you don't interpolate, you're kind of assuming value is something at a time and it's not. And so even at the microsecond level, that is something you might want to consider if you're slightly shifting values. That's what we're currently doing. There are ways to, this is just a screenshot from the way this ed does it. If we want to put more thought into how we actually sync our data, considering it does come from different sample rates. The initial idea behind this was just to get as much data as possible and just to have the data. But I have been asked on 2 interviews now why we didn't have a better way to organize the data. So that is kind of my basis for questions, if anyone has any.
I need to back up a little bit. Did you guys build the hardware for this data system? Where is the system itself coming from? How are you?
How do you mean?
So you can get an off-the-shelf data system, right?
Yeah.
So I'm assuming you're not doing that.
Yeah. So we're essentially running.
Do you have a time server on the system somewhere? Because it sounds like what you're seeing is each one of these units is timestamping the stuff for you before it goes to QTT.
Yeah.
And they've all got their own time thing going. So I'm trying to think of it off the top of my head right now. I did a bunch of stuff where I was integrating signals and it was going through the MQTT thing. And I have to remember now, but you need a time server in there that they can all talk to get the time. And then, now we were doing it over Ethernet. So, you know, we could have UDP packets coming out with current times for all the things to sync up on. But, and I don't know if you can do that on CAN. I imagine you can, but I think that that might be part of it, or you're just gonna have to, MQTT is gonna have to timestamp it when it receives it. And it's not a terribly big system, so it probably isn't that big of a deal for it to just impose its own timestamp when it gets the data. But you do, it sounds like you also wanna have an onboard cache somewhere just in case you lose your uplink.
Yeah, so I'll talk about that in a second. But again, the main thing that I wanted to focus on was specifically this slide. So time syncing is something we kind of took for data. Again, it's all sent from the TCM, so it has a unified timestamp then. But that's kind of assuming that's the transportation over the CAN bus is instantaneous and that you're not losing.
Well, and also the latency in the actual instrument itself. So it very well could be that these things are late. I mean, if they're minutes late or years late, that's definitely not it. But they, you know, individual sensors may also have a high latency. And so maybe it could very well be that those sensors did take their data at that time and it just took them 2 days to get the data out, you know, but yeah, it sounds like, I mean, there are, we had this big giant thing that serves up the timestamps for trailer full of systems. So that's obviously too big for this. But I'm sure that there's something smaller, you know, and whether it lives on the CAN, I don't know. I imagine it can. I mean, it's two-way communications possible. Do your instruments, can they receive information or are they only throwing it up there like UDP?
I think they're only throwing it out as of now. There are, actually, I won't get into that. But yeah.
So, you
know. I think what Jake is meaning specifically when he's talking about the time synchronization is if we have like 2 sensors with different sample rates, being able to, like when you're actually querying it and doing analysis, being able to like see those 2 in context where they have a misaligned timestamp.
Right, but ideally each instrument would be on board with the clock, right? The instrument itself is providing the timestamp with the measurement. Then it needs to know what time it is when it took the measurement. And so
the point would be so the hope would be, again, don't want to say hope, but that each individual sensor has some sync timestamp and that it is measuring whatever it's trying to measure at a sync timestamp with respect to everything else, right? Instead of just getting it as soon as it gets it and then we mesh or we sync everything on the TCM or in the cloud, essentially.
Right, you gotta be able, each sensor needs to be able to find out what time it is.
Yeah.
So you need a time server somewhere, and they need to be able to get that information from the time server.
To answer your question, which was asked a couple minutes ago, this is, again, there are systems to get this out of the box. The original reason this exists is because our sponsor was Single Store. And so we were receiving a huge grant of money to implement this server to just get data and send it to the cloud, which is why it was such a blunt approach at first. We've now kind of developed it into something that is essentially an out-of-a-box system, if not better. A lot of the things you lose with those, again, is the real-time analysis, which is something that we try to keep up. Typically, you'd have to pick and choose what data you want to send in real time, or you might want to just keep all the data on board and then pulled off after. After this, which I will go into, again, this is this is 24 infrastructure essentially. It says 25 just because this is a problem I wanted to tackle specifically for this year. But
are they still giving you money?
No, so we are transitioning out of Single Store, but now that we have the infrastructure, we're going to keep it. If that makes sense.
So do you know why these sensors times are out of sync?
Or they're just operating on each. So they technically should be operating on the same UDP's timestamp, but it's not going to be exactly identical between devices. It's not something
you're not foot per nanosecond. You're not that far apart and your timing is not that critical. These things should all be able to see the same time signal, right? Now, the latency on board of a sensor, it could be half a second before it actually burps out its own data. And you're just gonna have to put that together later and sync those up. But you gotta know whether it's latency or it's just ignoring the clock. It's not listening to the external clock that's supposedly synchronizing everybody.
Like, is your problem just that the sensors are sampling at different rates?
Or not particularly. We just want to, or I want to make sure that our timestamps are accurate, and I want to make sure that doing this way of just interpolating them on the closest timestamp, as is kind of, or an as-of join in SQL is just joining tables where you don't have an exact column to join them to. So you join them to the closest. So in terms of timestamps, if you want to join columns and they don't have identical timestamps, you instead join them on the closest possible timestamps, but then you kind of lose stuff. So should you interpolate beforehand? Should you have a more structured way of sampling sensors, right? Instead of just having them sample at their max sample rates, do we need that much data? Should we have a more organized approach? Would we benefit from that? That was kind of what I was trying to gain from this.
Yeah. Those are exactly the same sort of problem I was dealing with. I had some of my instruments were working at half a hertz, some were working at 10 hertz. Stuff that could run faster, I didn't need it any faster than 10 hertz. And then, yeah, it was all sorts of different times. And for my purposes, I would then, bin things up into half-second intervals, or I might, depending on what I was looking at, I might bin it up into a 5-minute interval. So, but, at that point, I knew that all of my timestamps were correct with my data. And it was in a SQL database, and I would just query it however I wanted to.
Okay. I'm going to move on to infrastructure for GR25. So this is for the TCM. So there's a monitor service, which is essentially just a health service of the TCM. It essentially checks connectivity and then computer statistics and then sends them back and forth. The CAN service basically just listens to the CAN bus and then sends the CAN messages to the MQTT service, at which point sends the binary data to the cloud to be deserialized. And also with 25, we had a new system to deal with the data dropouts, which was Epic Shelter, where we essentially just stored the data locally as well to make sure that we weren't losing everything. And then it would be perpetually compared to the data that we had in the cloud to make sure that everything was correct. And then there was also Mapache 25, which we have the ingest service, which receives the data being sent by the MQTT topic. It deserializes and scales it. That's what the GR25, GR24 service is. Again, these services are different for different years of cars because the CAN data is different, the sensors are different. So it's nice to just have or be able to add another service, and then you can pick and choose which ones it needs to use. Vehicle and query service, again, I'm not going to end up going too much in depth onto what we do for our dashboarding and that kind of stuff, but essentially these are the gateways, the APIs where our data was exposed, and they make querying the data a lot easier. Same with the vehicle service, which does the same thing, except for more metadata related to each run. And then we have live telemetry, which was streamed just to a webhook, and that was only for live data. After it's streamed to the live data, you have historic data, you can just query that from some API. I guess I had made some animations for the slide, but yeah, that's all for that. I don't expect there to be too many questions. Okay, infrastructure. So I've kind of brushed over the database parts. So again, we use single store because they were giving us money to use them. They are really good for HTAP, so hybrid transactional and analytical processing. And we are partially, to my understanding, going to use them for a majority of our other services, but it's just not needed. And it's also not necessarily the fastest in terms of querying our actual large 80 million rows of signal data. And so for that, we're moving to ClickHouse. So it's column store. It's purely OLAP, so online analytical processing. And it's faster because it's more simple. It doesn't do as much. And it's also really nice because it has these things called materialized views. And so there are general materialized views in SQL. ClickHouse does something a little differently, where essentially it has a materialized view and then, is anyone familiar with the materialized view, or should I just gloss over this? Okay, well, a view essentially is a data or a table in SQL where it's basically a variable for a query, right? So if you have some really complicated query, like syncing a bunch of unsynced timestamps that you don't want to call anytime, you'd store it in a view, and then you just call it. It's basically a shorthand for a query, right? But the way it's set up is it has some really nice properties that allow you to query from the view itself and treat it like a table. So that does really nice stuff. ClickHouse has materialized views, which treats these views as appendable objects, essentially. So every time it sees new data ingested, it automatically adds that to the view if it's associated to the view. And this is really important because we have widgets and dashboards like our ACU widgets, which is simultaneously streaming 144 cells at the same time of temperature data. And this isn't you don't want to query that every single half second, multiple times. And so the materialized views are nice because the data, as soon as the data gets ingested, the view gets open, and then you're just querying from the view. You don't have to re-sort through all the data hundreds and hundreds of times. So that's another nice part. They also have async server-side inserting. So this kind of goes back to column store databases are a bit trickier to insert into. They're not as efficient. They're more efficient for querying from. That's why they're AP analytical processing. But ClickHouse does support async server-side inserting, which means that insert time isn't going to be too bad. So for historical queries, there's not too much of a loss there. Okay, so from Apache, the differences this year is we're essentially adding a couple more services. So we're adding the model service, which is essentially going to be a organizational center or implementation of Python or MATLAB models that already exist, which would allow us, one, to have a central place of discretized models, but two, be able to use them to make it makes analysis a lot easier. It also allows us to run onboard models, which I'll get into in a second. But this is something this was, I guess, the next step in my mind. There's a notification service, which is more of just like a quality of life thing. I'm not going to get too much into that. There's query service. We are changing our database, so we have to kind of refactor and migrate the query service bit, which is currently happening now. And then we have dashboard widgets. There are more sensors, stuff like that. Widgets were a nice thing because you don't want to have to rerun a notebook or rerun Python code every single time you ask a single question, right? if you have your engineers coming and asking you the same question after every lap, you don't want to have to redo the code every time. So widgets were a nice way to be flexible enough where if someone asks you a new question that you weren't maybe ready for, you can incorporate them easy enough, but also like rigorous or rigid enough to, you know, sustain multiple uses. And then TCM is where a majority of our changes are going. So we're now adding Mapache as one of the services inside TCM, right? This just means instead of MQTT just also sending to a database, or it's a bit more convoluted than that, but we're just sending to Mapache and then Mapache will host to a local database. One, this is nice because now we get the model service on the car. Again, the model service was just added to Mapache. Now it's running on the car, which means it can power some onboard modeling that we will be doing this year. But also it makes the epic shelter step a bit easier because if we're scaling and deserializing on the car as well, it has to do less work to validate that all the data was properly sent to the cloud. And then there's also Dash UI, which is an interface for the Dash panel this year, which will supposedly be running those onboard models, or at least interpreting them for the driver, whichever we seem useful, and then also whatever other interface the Dash may need to have. Questions?
What's the end-to-end latency assuming like your network speed?
Or
like can't like sensor to like your dashboard.
To cloud?
Yeah, like your
it doesn't change. It hasn't changed from last year, right?
What is that latency?
Yeah, do you have a number?
Why are you asking me this? Well, we haven't tested with actual data, so we don't know what this actual latency is. Supposedly it's below 250 milliseconds. Again, it's end-to-end latency is not really something that you can quantify as a mean or an average because it has a weird skewed distribution. So below 250 milliseconds is what I'm saying. So that would just be from data on the car to you're seeing it on your computer through the cloud, if that makes sense.
Not on the car, the dashboard.
That's a bit different, right? Because one, you have to cherry pick which models that you want to use, right? It'd probably be considerably less unless you're actually running models. Again, so if it's going to the cloud, you're just streaming your data. You don't want to do too much to the data on the car, right? You want to make sure all the critical stuff works. You are saving the time that you don't have to send it over LTE. Again, we're not quite so sure what we want to send just yet.
They want some sort of temperature or something like
Yeah.
that, so I'm thinking, you know.
So it'd presumably be shorter as long as we're not running any complicated model, which we wouldn't want to do anyways, right? Because again, you're saving all the time that it takes to send to the cloud. Everything's just local.
Are there other displays on the dashboard then that indicate things like charge level and brake temperature or chart at least battery temperature or something like
It
that?
hasn't currently been developed this year. We're currently working on a couple things, which I will get to eventually. If I don't answer your question, you can come back to it. In years past, again, we haven't really had, it's typically just been speed and like a couple key settings or parameters, if you want to call them. Again, the actual display of the dashboard and what's going to be on the dashboard hasn't really been considered, but also the TCM is a Jetson, and so we have way more compute power than we would reasonably need. And so we also have a lot of options onto what we could display. It's just a matter of considering what we want to display and then how to interface it. Yes.
What's the actual interface between the Jetson and the CAN bus?
The CAN service, you mean, or the CAN controller?
The controller, yeah. Like how does it talk to the controller?
You want to ask Andre?
The Jetson talks to so there's basically a TCM CAN PCB and the Jetson talks to it over SPI. And so it's basically ingesting two CAN lines into our microcontroller, converting it to SPI, and then The Jetson acts as a slave device where the microcontroller triggers the packet being sent over. And it's significantly higher than the bit rate of both of the lines combined, so we get as short of latency as possible.
Do you know what the total expected throughput is gonna be?
Ideally, it is over what are CAN-FD and CAN lines, so 9 megabits per second. And I believe last year's design was around 12 stable, so it should not get it shouldn't be a problem, if that makes sense. Where we have data essentially not getting sent to the Jetson. And since both lines are not going to be ran at 100% load, there's still quite a large margin, quite a large overhead to that also.
Why are you not using the CAN controller on the Jetson itself?
There's only one CAN controller, it's CAN 2.0. And so we cannot have 2 CAN lines because one of our CAN lines is FD. And also there is a very small amount of documentation on getting that CAN controller up and running. I did experiment with it, but I never got it properly working.
Okay, so to reiterate, main changes, model service, and then we're running Apache on the car. And then hopefully those changes will make our actual data validation, right, in terms of we have the correct data, we have all our data better, but also it would power a lot of model building and also kind of acquiesce the design judges when they come and they ask us their questions, which I'll get to in a second. So Michigan 25, again, kind of weird scaling. So the latter half is going to be less infrastructure and design focused and centric and more so what I'm planning to do with data. I think this team has a lot of potential, but as it currently stands, we're kind of just those guys in the corner. And I feel like we should try and integrate a lot more with the other sub teams to answer a lot of those questions. Okay, in any case, we show up to Michigan 25 and we have our data acquisition judge and he goes over our stuff and he addresses what you said, and it's this system is something you can just get pre-built out of the box. And so he basically addressed that and he said, but what do you do with the data? And when we didn't have a response to him because we had spent all this time developing the system because we had to for our sponsor, we didn't have an answer and we presumably didn't get scored well. And for specifically the EV competition, the design rubrics are lots less managed. So this is taken from the ICE rubric. And this is kind of where I found my answer, where they better, under the systems category, explain what exactly we got docked for. Did we utilize the data? Did we test equipment? Again, for the EV competition, it's kind of just bullet points. But you can assume or presume, I don't think you should assume, but the judges that are volunteering at the competition will probably have volunteered at the combustion competition just prior. And so if they're operating under a certain set of standards, they're probably going to follow them through. But in any case, we also have our dashboards to the right, which is what we showed at competition. But do our data systems just show off? And do we actually utilize our data? Okay, so part of this is one, we own the car to cloud pipeline. This is more so for scope. I'm sorry if I've gone in a bit of a mumble, but historically, we've owned the car to cloud pipeline, the dashboarding, real-time analytics, the data warehousing, which I put an asterisk there this morning because it has become readily apparent to me that this team has access to a lot of data and it's relatively isolated within each sub-team. And so I think this year particularly, we should start working towards a more central version of data. Because there is data that I have heard that people have that I would have loved to have had. And I can say the same probably for other sub-teams, that one sub-team has data that another sub-team could have greatly benefited from, but it's on someone's local machine or private drive, and there's just no central place for it. And of course, there's analysis. Particularly this year, I want to focus on maximizing points in the design competition. So this goes into strategy, this goes into data validation and model correlation, which I'll get into later. And there's also filtering, smoothing, and uncertainty quantification. Okay, so for static events, This is kind of just design judge appeasing. I'll get into what exactly we will do for those later. But this is more so, we tell the judges, we did this, we have this application to do this. They ask you what you did with the data, and then we show them directly how it's used, where it goes, who needs it, who uses it, and then how it's put back into the card pipeline. So that has to do with modeling and correlation testing. There's statistical testing of parameters. So we're making a lot of assumptions, particularly with regards to parameters. There's also parameters that we have to estimate, right? And so there's statistical tests you can do to validate those parameters and perhaps flag the ones that are not what you might presume. And then there's the dynamic events, which are a bit harder to strategize for. I remember when I first joined this team, as someone who's interested in data, my main interest in data was strategy. How do you use the data? And the hardest thing to say was you can have this specific strategy, but the more and more this occurs, the more you can maybe iron out little things you can win here, little things you can win there. So the main part of that would be strategizing for the dynamic events, which this year we're starting with endurance. So that would mainly, I don't know if I talk about that later. I don't think I do. We have an ARCA this year to kind of control or manage thermals. So we're going to look into that. And then there's debugging, of course, which isn't really a strategy, but it is something we can do with the data in real time. And there's outlier detection, which is the same in the same books. Okay, so in terms of uncertainty quantification, as I showed in the 24 SoCal data, the data you get isn't entirely accurate, right? So it is some truth, but it's also not 100% reliable. And so there are ways to quantify the uncertainty. And what I mean by that is, instead of assuming one value is true, you can instead say you believe the data to be in some range of values, which I think would be a lot more beneficial, particularly if you're plugging it back into analysis. If you know that some parameter that you need to use was within a range, you can take the max of the range and say, at worst, it was this, or you can take the average, who knows. I think it's a lot more valuable than what we currently have. There's also ways to put it back into models, get better data. So probabilistically, there's Kalman filtering, which makes a critical assumption that your data has Gaussian noise, which isn't necessarily correct. It is probably one of the most common, no pun intended, filters out there. But that is something we'll look into. There's also analytical uncertainty quantification, which I'm also not going to get into. But if you have the models, you can put in your models, you can put in your actual data. The residuals probably won't be Gaussian, but you assume that anyways. And then there are ways that you can extract uncertainty from that. Filtering, smoothing, this is a point where we're judged on. Again, common filtering, common smoothing is stuff we can do. We can say that to the design judges, we did this. We smooth the data like that. Post-processing, again, there's more truth you can find from sensor fusion, particularly with post-processing. Once the data is digitized, there's not much you can do to improve the quality, but you can improve your trust of the data or the trust of the values that you're measuring individual. And these are things that would be incorporated in model service, which again is just probably going to be an API endpoint for whatever models are incorporated or that we initially build. Okay, so when I say validation, the design rubric for various subteams, again, you can tell that this is the EV rubric because it's just bullet points that they don't actually give you like specific things they're going to check you for. They say, have you validated this? Have you validated that? Well, this is something we can do. We can test the parameters that we don't know. We can measure the parameters that are discrete, that are certain. But this would also require some central organization where we keep track of these parameters and their dependencies, that kind of stuff. And then this would also be important so we can flag the parameters that violate what we previously believed about those parameters. And then finally, there's correlation, which is another huge part of, I think, everyone's design rubric. You have a model and you correlated it. And so part of having this model service would be, as soon as we get the data, we can give you some Pearson's correlation coefficient, and then bam, you have your model correlation. And you can see, is something wrong? Do we need to adjust the model? Is something wrong with the car? Who knows? But it's there for you to use, and then you can show it off to the design judges, and hopefully we win back some more points. I think that's all. Nick?
Yeah, so, I mean, this is all like super cool, but I guess the biggest problem was in 2024, we had a working car and we had no data, so we learned like almost nothing. So like this is all like after we have data. So have you solved the problem guaranteeing that if the car runs, we will have data to learn?
Well, the main, like, what do you mean, from data dropouts?
Well, yeah, like, cause you said like earlier you had a problem with your timestamps not lining up. So like, I guess
Or
like,
the
what are you doing
timestamps not
to
lining up isn't necessarily a critical problem, it's just something that you might want to address later in analysis. In terms of data dropout, that was immediately rectified with one, a local database, and two, Epic Shelter to sync that data. And then in terms of the actual quality of the data, from my understanding, the sensors that are critical to the accumulator have improved and their positions also improved, as well as more sensors in general, right? Again, most of the data that we were able to make or wanted to make use of was from a phone that was loosely duct taped to the bottom of the car, which is going to be directly replaced with IMUs and other forms.
Right, but like, I don't know, it might just be worth, like, you know, once the systems, like electronics team is done with the suspension travel sensor or whatever, like just kind of getting familiar with like, okay, this is the polling rate, this is what we're expecting over CAN, and like just like having a test bench.
Yeah, I think that would
I'm
be.
surprised that you didn't get any data at competition.
I think that would be implied that we start testing with actual sensors as soon as we get them, not wait for the.
Do you rely on the other instrument, the other stuff, or can you just read stuff off the CAN?
Or so we have a centralized CAN spreadsheets, which kind of.
I mean, in the vehicle, so I'm just thinking in terms of like, as soon as the sensor is gets put together.
Yeah.
Can you start your testing of just, you know, uploading it, making sure that, because, you know, you're really only gonna be able to do your statistical tests and stuff once you've got like the honest to God data and stuff like that, but just making sure that as instruments are online, you know, get put together, that you, because it's the only way for you to really start testing your, you know, your whole data pipeline in some way. So I'm just wondering, can you like work off the raw CAN buses, or do you need other instrumentation to be done first before, I guess, not instrumentation, computation to be done?
So particularly for analysis, this again is for a full car system. If we wanted to test analysis,
Data acquisition.
Yeah, the easiest solution from my perspective would just be store that data somewhere and then use that data for analysis. And then maybe later we can correlate it with something and then synchronize it or.
I'm even before all of that, like, can you start testing your data acquisition system, your data acquisition and recording system?
Yes, so we currently have empty bench, or I don't necessarily know what you mean by testing, so we can validate that.
So somebody's got, I don't know, some wheel speed sensor, or maybe a temperature sensor.
Yeah, so
that's ready to go, you can plug that in and you can watch it go up into the cloud.
Yeah, so that would be, it would have to be associated with the CAN packet, but assuming that we know what the CAN packet looks like, the system can just interpret it and then send it to the cloud.
Yeah.
But you're talking about MP Bench, but that's like a software.
No, just that, I'm not talking about MP Bench.
Yeah.
Just for that specifically, assuming we know what the data is supposed to look like, so on our end, we'd have to go, I guess, to the data sheet, and then we'd have to like know what the CAN packet's going to look like, which we have a generalized CAN spreadsheet. There's also currently an IRCA, there's a bit of a tangent, that's currently happening to make that process easier. If we have a sensor we want to test, on our end, we just need to know what that looks like. So we need to know what the CAN packet looks like, what ID it's associated with, and then what data it's associated with, which is something that can be like hard-coded in like 30 minutes.
Exactly, and that was my question, is like, are you like ready to go as soon as you get some piece of hardware that you can actually start turning the key on, doing your end of the stuff?
Yeah.
You know, how much do you need to start that? That's, I guess, the question.
Yeah, we just need the data sheets and the CAN ID essentially.
Is there anybody who's got a sensor that's that close to being ready to go?
Someone has your sensors and that was working with last year's system, which hardware wise is the same as this year's system. So,
Yeah.
testing was done there, and the can to cloud pipeline work is we were just adding it. Just this is all part of it.
Of all the hearts I've broken in the last 2 days, there's none of them break more than ours. This is not the way to do this. You have to get racing system and work with that. This is such a massive project that I cannot imagine doing this with anything less than Formula 1 team. And this, I did data systems for years and years, and it's a huge job. It is a huge job. With everything, with all the hardware and with all the stuff off the shelf, it's a huge job. It's what you're doing and everything. I just do not think it's even remotely feasible.
Or it's already implemented.
No, it's not. It's not on a car. It's not working.
The data, this acquisition system I'm talking about is fully implemented. The thing we're missing are the actual sensors. This has like fully been developed and fleshed out. I can open the repo if you want. Like the main thing that's prototyped is all the analysis that will happen, right? The way we get data from the car to the cloud is done, right? So we have essentially, quote unquote, a foolproof way BK can verify if he wants to get data measured from the sensors however he wants and then put it in the cloud. They're just tiny little optimization things we can do. Again, this is a system that we were paid to implement.
It doesn't matter. It doesn't matter. Like, I'm sorry, man.
I don't quite understand what you mean. Like, what part of this isn't feasible?
Bring all of this together and being able to use the information to make your race car go to do what you want to do, it's not gonna happen.
Again, that doesn't make sense to me because it already has happened. And it's already been true.
I'll stop.
Yes.
I will say I also noticed that like there's no data systems on the timeline. And I didn't notice any like specific deadline. So I think like in the past, we have had a lot of struggles with data acquisition along with all the analysis. Like there's all of those things that have to be done, which they've never been done. So I think it'd be good to maybe like start small and just make sure you can do the whole process for like one system first, so like one sensor. But even then, I feel like you need to plan out how you're gonna accomplish all of these things, because like when the sensor team is presenting, there's like 20 different sensors and each of them may have their own problems. I think one thing is maybe the test module, like they are planning on running that soon. Like they're going through the recipe things, I think, Peyton. So you may have a chance to use a few temperature sensors or pressure sensors.
Is this for the analysis or for the data system itself?
Well, I mean, like the whole process has not been done. Like, well, I feel like in the presentation,
it essentially, okay, so it has been done. Again, there is a computer on the car. So this was the data that we got from SoCal shootout, right? So we have whatever sensors, then we have a CAN spreadsheet that associates the sensors with this is all just data that we're picking from the car. The main problem with SoCal was we didn't have the added layers of redundancy, right? Now we have 3 layers of redundancy. So if we send it to the cloud, we don't just lose the data. The data is stored locally on the car, and it's also updated from the car to the cloud when it's able to, right? Like this is essentially the same.
I think what Thomas is trying to say is you need to have a timeline and a testing plan for when you're gonna like as soon as the sensor is ready. Other people are saying as soon as the sensor is ready, you need to get that sensor and make sure it works in the system, right?
Yeah.
You can't leave it until like Michigan or wherever the first actual car run is, right? Because then it's too late to debug stuff.
Yeah, and so the main thing there is just organization with what we have previously used as a central CAM spreadsheet. Just a better idea of what that's going to look like. Right, so our main issue previously was that every time someone adds a new sensor to the car, or every time someone edits the CAN spreadsheet, we have to rewrite all of our signal definitions, not all of them, but we have to make sure that they maintain the same, which is kind of the benefit of empty bench and having all of our unit tests and benchmarking already in place. But there's one of Daniel's IRCAs this year is focused on making that a more accessible process so that you could just integrate sensors as soon as possible. And then from them, we can export what our structs are supposed to look like. And the other thing too is if we have a set of sensors that we know we want to test, so particularly with cooling, because we know that test bench is going to be ready soon, that is something that we could just hard code for now and just write a separate service. So if you remember, from this slide, which slide is it? This slide, yes. So we have different ingest services. If we wanted to do a smaller test service, you just write a new ingest service. Again, all this contains is the model definitions of the signals that you're interpreting. So if we wanted to do a data test with the test run, we just write an ingest service with those specific signals. And it's essentially busy work because all you're doing is hard coding what the sensor values are supposed to look like into a model.go. And then that just goes to our pipeline, and then we scale, deserialize, then scale, and then send that or save that data into a database.
Okay, it's starting to sound like you're starting a company here. I feel like this section is kind of predicated on if we wanted to do this, we could do this. But there are some things that we could have done already. I see it's like a big grand plan to build all this infrastructure.
This infrastructure already exists. This is from last year.
Okay, but where is any testing data? We have sensors that we could be trying, and we could be building, a test bench.
So that's then a organizational issue with the team, because we have been waiting and ready for data for the past 2 years. So if someone wants to test sensors, by all means, come to me.
So if I gave you a thermistor right now, what would it take for you to read this thermistor into the database?
Well, is that data being sent over CAN?
No.
Well, then we
Test
just,
bench, for example.
well, this is for the full car reading off CAN data. If you want data in the cloud, all you need to do is read that data and then send it to the cloud. You don't need the system.
Are you saying the cooling test bench needs a CAN system?
No,
It does.
you can just measure the data and post it into the cloud. That's an easy option.
Upload on a computer.
Yeah. And that can just be.
That's not testing the data acquisition system that the sensors on the car would, but it's not one-to-one.
This system is built for reading off the sensor data from the CAN bus to the cloud.
So what is the first test case of that? Because the test bench isn't going to replicate that.
It should.
It could.
Okay.
Are there sensors that are already coupled to acquisition systems that post to CAN? And that's what it sounds like. Last year's car does have some sensors that can write to CAN.
Yeah.
So are there thermometers on those?
The only place we had thermometers was ACU, but we had a GPS that was sending over CAN that we have data from. We have accelerometers that we're sending over.
I'd like to introduce you to somebody that needs that data.
I mean,
so
I think we have data in GR25. It's just 26 that we still need to throw the bench together essentially.
Wait, GR25 collected no data.
We had the GPS data from when we were at Owen's house.
Oh, yeah, that's true.
Yeah, so no on-car data, but we did test the full pipeline.
The other thing, or the last thing I want to throw in, we have a central data base on S3, our data lake, if you would call it. this infrastructure, the one that stores all the data as signals, is specifically tailored to getting all the data off the car. If we're running individual tests, if we're running testing individual sensors, it makes much more sense just to host or collect that data through normal means and just send it to the cloud and then store it in the same data lake. So at least it has a central location. There's no need for it to go through this system.
Except to just have, the whole, to validate that the sensor and the box that's gonna translate that to the CAN, that part works, so that you're like, so that as things being brought up, that they'll integrate, there won't be any hidden things about, oh, I guess we didn't, interline that correctly or whatever, but that's the thing I'm just thinking of is obviously this says you need that for what you did, for what you've got here, for you to work, you have to have a module to put something on CAN. And until you have that, there's nothing for you to do. So, I'm just saying, if they've got something sitting around, then you can at least start building your infrastructure for what kind of, you could start doing your noise analysis on this,
Yeah.
right? You can look and see, is it Gaussian, is it something Lorentzian, is it whatever, you can start doing those sorts of things. I mean, there's statistics that, that you can start on to start building your tools.
Yeah. Again, this system is just to get data to the cloud. Like in the real time, we're racing the car. It works with all the sensors. Again,
and then what do you do with that? But the other question is, what do you do with that data? So you've got tools, you're not going to do analysis online, at least maybe you are, I don't know, that's going to feed back immediately to the car. I'm not seeing, that feedback loop, but that means actually is that you're like, oh, we need to make some changes here and here and here. This at least gives you something, to work with. Because you can't even start understanding your noise, things like that, until you've got instruments that are putting out data.
Yeah.
That you can upload. I mean, your bailiwick is not converting sensor data into usable. Your bailiwick is converting digested data on the CAN bus, storing it, doing whatever, building your analysis tools that are going to live on AWS or whatever. That's what it seems like to me, right? I mean, that's sort of where you begin, is you don't start until CAN bus. That's like you need the CAN information. Somebody else has got to turn the sensor into a talking robot.
Okay, I think we're a bit over time, but I do, just a little bit. I do, again, want to emphasize that Mapache specifically is getting data from the car to the cloud. Data team does we want to move in the direction of actually analyzing data and doing stuff with the data, which is a different pipeline entirely. That's from the cloud to analysts. I don't know why I said it like that. But the main thing with that is we've never had data to do that with.
Right.
So often people come to the team and then we scare off all the data science majors and then we're only left with the computer engineers and then we get this.
Yeah. And so I understand that. And that's why I'm saying that if you can start getting some data up there that people can play with, I mean, at least, it's a start that you can start doing stuff with it. And, what can you do with an isolated instrument? There's not a lot you can do with an isolated instrument. You can noise analysis on it. I'm not sure what else you can do with an isolated instrument. But at least it's something, and it goes back to the bullet points of trying to get points, right? What's the low-hanging fruit? Your part of this is not really fit into a rolling car, right? So what is your low-hanging fruit for points? Your low-hanging fruit was getting the data, making tools, feeding it back, things like that. So, what can you do on that bullet point list to get the low-hanging fruit, even if the car's not rolling?
Yeah.
And that was the only thing I was saying, is trying to get people to bring you instruments that are ready to go, that you can start uploading, at least get, the only useful thing I think that I can envision you being able to do without car information is noise analysis from sensors. Different sensors have different noise profiles, things like that. Understanding that at least gives you the plus minus parts of your data analysis. It is useful. It's not the most useful thing, but I don't think that there's anything else that you can do at this point that would feed back into useful data until the car is rolling.
Yeah.
I think one thing that you should like do like immediately is like we have the GPS from last year, right? Just plug it into the TCM and like put it in someone's car and drive around.
Yeah. That was on one of my like first general meeting slides. I think it just got buried.
Gotta bring that up again.
Yeah. Okay.
Yeah, be noisier.
Yeah.
Complain
I
more.
will try. Thank you.
With that, we're coming to the end of CDR. So thank you for everyone for coming for the past 2 days. Thank you all of our guests. I think all the members got some really good information and have a lot of work to do in the next coming weeks. So we'll be working very hard on that. So yeah, thank you so much. I don't know if we have any extra pizza, but we do. You're free to take them. So yeah, thank you so much.
No, you guys did go on.
Thank you, everyone. Thank you. There's been a lot of really, really good work done from everyone, and I love seeing everything that everyone has done, and it's the presentations that you've given have been great, and you know, I hope that our feedback has helped you guys to understand places where you should concentrate and you know, things that are going to allow you to reach those base goals that you have and can leave Michigan with your head held high.
Yeah.
It's great to see.
Yeah, go for a rolling car, get the low hanging fruit, you know, make sure that you're just dead nuts focused on getting the car rolling. And asking, you know, the types, you've seen all the kinds of questions that we've asked you guys. Ask yourselves those same questions, right? Everybody's their own worst enemy, and so we all know how to ask hard questions. We all know all of our own weaknesses. So don't be afraid to ask yourself that question and address it. Yeah, and get help. That's the other thing is I see, you know, that's like really important. If you need help with something, you need expertise on something, man, don't be afraid to. It's the worst thing that I'm terrible at getting help with stuff that I need for you know, a project or whatever. So don't be afraid. Go get it. Go get that help. Do that.
Absolutely. All the alumni are here to help you guys. So good job, guys, on CDR, and looking forward to seeing the car.
Thank you, Nick.
Thank you.
All right. Very cool. Thank you, everyone.
All right.
Thank you. I'll be tomorrow. Yeah, I think probably 12:30 everywhere. You can meet. Do you know any of the buildings out here?
Have no idea anything.
I'll send you one.